Hello there, and welcome to The Midnight Scientists. I am so glad you've chosen to spend these next quiet moments with me. Before we begin our journey, if you find a sense of peace in these gentle explorations of science, a quiet like or subscribe is a wonderful, silent way to show your support. It helps our sleepy community grow, and it is as effortless as a slow, deep breath. Now, wherever you are, find your place of rest. Perhaps you're nestled in a cozy bed, the sheets cool against your skin. Or maybe you're reclining on a soft couch, a beloved pet purring gently on your chest. You might even be swaying in a hammock with the vast, silent tapestry of the stars above you. I hope this gentle journey into the heart of the atom will help you to unwind, to breathe a little more slowly, and to let your thoughts soften, floating like motes of dust in a moonbeam, gently into sleep. I'd love to imagine where in the world you might be listening from tonight. It's a beautiful thought, seeing this little community of curious minds stretching across the globe like a quiet, invisible constellation, all of us connected by a shared moment of calm. I do hope this story doesn't prove to be too interesting. You see, it is a delicate balance we seek. If you find yourself awake until the very end, well, you will at least know a great deal more about the atom than when you began. And if you drift away somewhere around the discovery of the electron, that is perfectly fine too. Either way, we are in no rush tonight. This episode is all about whispers, specifically the soft, persistent whispers of the atom. From ancient Greek philosophers dreaming of invisible particles to the ethereal dance of quantum mechanics and its subatomic poetry, we are going to ease our way through more than 2,000 years of ideas, of experiments, of quiet surprises, and occasional muffled explosions. But do not worry. Tonight, there will be no stark lab coats, no tests to be taken, and no jarring alarms. There is only curiosity and calm. So let us take one last deep breath together. Settle in and let us follow the trail of tiny things, things far too small to ever see, yet somehow they hold up the entire universe. And as always, this video is created for relaxation and educational purposes only. It is not intended as medical advice or a substitute for professional care. Long before the hum of particle accelerators and the stark elegance of quantum equations, there were sandals on dusty paths, the rustle of papyrus scrolls, and the endless deep blue sky of the Mediterranean. Here, around 2,500 years ago, Greek thinkers were already pondering questions that still echo in our minds today. What is the universe truly made of? Can something truly become nothing? And if you break a rock in half, and then break that half again and again and again, do you ever reach a piece so infinitesimally small that it cannot be broken any further? Into this sun-drenched world of inquiry stepped a philosopher named Leucippus and his more famous student, Democritus. Together they offered a radical, beautiful answer. Yes, they said, there must be a smallest possible piece of matter. They called it atomoi, a word meaning uncuttable. These atomoi, they imagined, were tiny, eternal building blocks that made up everything, from the stone beneath their feet and the wine in their cups, to the flesh of their bodies and the fire in their hearts. This was not just a poetic metaphor, it was a profound physical claim about the very structure of reality. According to their vision, atoms were solid, indivisible, and varied only in their shape, their size, and their ceaseless motion. Some might be smooth and round, tumbling over one another like polished river stones. Others might be jagged and hooked, catching and clinging to each other. Their collisions and their combinations, they believed, gave rise to all that we see and all that we experience. What's more, Democritus didn't just imagine these tiny particles floating in isolation. He also proposed the existence of the void, a great, silent, empty space in which these atoms could move freely. To a modern ear, this might sound obvious. Of course, things move through space. But at the time, the idea of pure emptiness was deeply controversial. Many believed that nature abhorred a vacuum, that a universe with true nothingness in it was heresy, or at the very least, highly suspicious. Democritus took this invisible world with the utmost seriousness. He believed that even the soul was composed of atoms, special ones, smooth and spherical, that zipped through the body like quicksilver, animating it with thought and feeling. He didn't just theorize atoms for the sake of science. He thought they could explain perception, thought, and even happiness. For Democritus, true knowledge was about aligning the mind with the deeper, invisible patterns of nature. He was said to be so cheerful and confident in his ideas that later writers nicknamed him the laughing philosopher. But not everyone was laughing. While Democritus was imagining a universe of atoms and voids, other powerful thinkers were casting a far more skeptical gaze. Plato, for instance, was not fond of the atomist's stark materialism. He preferred to believe in ideal forms, perfect, abstract blueprints that existed in a realm beyond the physical world. Reality, in his view, was just a fuzzy, imperfect imitation of these higher truths. The notion that everything could be reduced to spinning lumps of matter didn't quite fit with his more spiritual and mathematical worldview. Then there was Aristotle, whose influence would dominate Western science for nearly 2,000 years. Aristotle rejected the idea of the void outright. He believed that nature was continuous, a seamless fabric, not composed of discrete particles separated by emptiness. Instead of atoms, he proposed that all matter was a blend of four fundamental elements: earth, air, fire, and water. These were not made of smaller parts, but were forms shaped by four essential qualities: hot, cold, wet, and dry, constantly transforming one into another. Rather than a mechanical universe of bouncing particles, Aristotle imagined a world filled with purpose and essence, with everything striving toward its natural, proper place. Aristotle's vision was elegant, intuitive, and most importantly, easy to teach. His writings were meticulously preserved, copied, and revered long after the works of Democritus had faded into the dust of forgotten libraries. In fact, not a single complete work of Democritus survives to this day. What we know of him comes mostly from quotes and summaries written by others, many of whom did not agree with him. And yet, there is something so enduring, so resonant about the atomic idea. It may have been pure speculation, but it was startlingly modern. At a time when most explanations relied on the whims of gods or metaphysical forms, the atomists tried to explain the world in purely physical terms. No divine puppeteers, no magical essences, just tiny bits of stuff moving through silent space. Even their metaphors were ahead of their time. They imagined atoms as constantly in motion, swirling like dust motes dancing in a sunbeam. They believed the differences in materials, why iron is hard and honey is sweet, came from the shape and arrangement of the atoms themselves. That is not so far from how we understand things today. Of course, none of it was based on experiment. There were no microscopes, no chemical analyses, no data or diagrams. This was a philosophy of pure deduction and imagination, not measurement. But sometimes, imagination gets surprisingly close to the truth. The atomists laid down a conceptual foundation that would echo through history,
quietly waiting for the tools that could finally test it. It's tempting to romanticize these early thinkers as lonely geniuses, staring at the sea and dreaming of molecules. But they were also part of a lively intellectual ecosystem. Greek city-states were buzzing with debates, lectures, and wandering philosophers. Ideas spread via ship and scroll, and disagreements were as common as olives. What mattered wasn't just having a theory, it was defending it, arguing it, refining it. Democritus and Leucippus may not have won the popularity contest in their own time, but they left behind a remarkably resilient idea that everything, your hand, the stars, the very air between them, might be made of the same tiny, indivisible stuff. An idea that would soon vanish into history's shadow for many long centuries, only to rise again with an unexpected and undeniable force. And so, nestled within ancient Greece, among stone temples and philosophical squabbles, a whisper began. A whisper that the universe, for all its grandeur, might be made of invisible pieces dancing through the void. After Democritus and Leucippus whispered their ideas about atoms into the ancient world, the universe went oddly quiet on the subject. Not because the idea was disproven, but because, for most people, it simply wasn't useful. For nearly 2,000 years, the atom would retreat into the background, a forgotten dream, while other theories about the nature of matter took center stage. Most of them shimmering with a curious mix of mysticism, philosophy, and a faint touch of sulfur. This was the era of alchemy. Not chemistry, not yet, but its strange and symbolic ancestor. Alchemy was a curious blend of experimentation, spirituality, and metaphor, practiced across the Islamic world, medieval Europe, China, and India. It was part science, part philosophy, and part a quest for personal transformation. The most famous goal of the alchemists, of course, was the transmutation of base metals, like lead, into pure gold. But that was only the shiny surface of a much deeper pursuit. Alchemy was also about purification, immortality, and understanding the hidden essences of things. The alchemists weren't entirely wrong in wanting to transform matter. In a way, they sensed that materials could change form, combine, separate, and evolve. Ideas that would eventually become central to modern chemistry. But lacking the tools of today, they worked with intuition, patient observation, and deeply symbolic systems. Instead of atomic weights and periodic trends, they had elaborate diagrams, mystical correspondences, and an enduring faith in the number 4. Ah, yes, the number 4. For many centuries, matter was explained through the lens of the 4 classical elements: earth, air, fire, and water. This framework, inherited from Aristotle and refined through various traditions, dominated Western and Islamic thought alike. These elements weren't considered atoms or particles, but rather fundamental types that made up all things. Wood, for example, might be seen as mostly earth with a bit of fire, while steam might be seen as mostly air with a splash of water. Everything was a cocktail of these elements, shifting and transforming in response to heat, moisture, and the occasional celestial alignment. It might sound quaint now, but it wasn't an entirely foolish idea. The concept that matter is composed of fundamental types, trying to balance and interact, is not so far removed from how we think about elements today. The difference, of course, is that modern chemistry classifies matter based on its atomic structure, not on how damp or dry it seems. Still, in the absence of microscopes and molecular models, the 4-element theory provided a surprisingly flexible way to explain the world. You could use it to interpret illness, weather, moods, and metallurgy, all in one go. The influence of Aristotle loomed large in all of this. His rejection of the void meant that the idea of atoms floating through empty space had little traction. And because Aristotle's works were so influential, especially once adopted by medieval scholars, the atomic idea was largely shelved in favor of more continuous, qualitative models of matter. Add to that the philosophical discomfort with imagining invisible particles, and atoms found themselves exiled from respectable thought. But even as atomic theory lay dormant, something important was happening quietly in the wings. People were starting to sort and classify substances. Alchemists and early natural philosophers began documenting the properties of different metals, minerals, and acids. They observed how substances reacted, combined, and changed color. Though they lacked a unifying theory like atomic structure, they were gathering data, sometimes muscly, often poetically, but data nonetheless. In the Islamic Golden Age, scholars such as Jabir ibn Hayyan, often Latinized as Geber, advanced alchemical practice by systematizing it. Jabir is credited with developing early forms of distillation, crystallization, and evaporation. He believed that all metals were composed of different proportions of mercury and sulfur, a theory that wasn't quite right, but it edged closer to the notion that different materials have distinct internal structures. Then later in the European Renaissance, alchemists like Paracelsus brought their own flair to the field. Paracelsus introduced the idea that chemistry could be used to treat disease, shifting the focus from gold making to medicine. He also expanded the elemental system by introducing salt as a third principle alongside sulfur and mercury. Not the table variety, but a symbolic essence of solidity and fixation. Alchemy was growing more complex with its own language, rituals, and an increasingly experimental attitude, though still wrapped in mystery. Despite the mystical overtones, these early practitioners were developing lab techniques and chemical processes that would eventually prove invaluable. Glassware evolved, reactions were cataloged, mixtures were separated. The idea of transformation was being explored not just symbolically, but practically. In the East, Chinese alchemy had its own rich history, often tied to Taoist philosophy and the search for immortality. Practitioners worked with cinnabar, mercury, and other substances believed to grant longevity or enlightenment. Although the spiritual goals differed, Chinese alchemists also observed chemical reactions and changes in matter, contributing to the broader human understanding of material transformation. So while the atomic model gathered dust, the world didn't stand still. Through hands-on work, accidental discoveries, and the occasional philosophical detour, people were gradually assembling a patchwork understanding of substances and how they behave. The atom wasn't back in the spotlight yet, but the stage was quietly being set.
Looking back, it's easy to smile at the idea of lead turning into gold or an elixir granting eternal life. But within those ambitious dreams was a deeper yearning to understand the fundamental nature of matter and life. Alchemists believed that the world held secrets, and that through careful observation, symbolic reasoning, and maybe a little luck, those secrets could be unlocked. In their own way, they were listening for whispers too, just not yet from atoms. For almost 2 millennia, then, the atomic theory slumbered. It hadn't been disproven, it had simply been set aside in favor of more immediate, intuitive frameworks. Matter was changeable, mysterious, and filled with essence and purpose. Invisible particles had little room in a universe built on qualities, humors, and hidden correspondences. Still, here and there, in smoky labs and on handwritten notes, glimmers of structure began to appear. The tools were crude, the theories fuzzy, but a slow, steady curiosity kept inching forward. It was only a matter of time before someone, somewhere, would dust off the ancient idea and ask the question anew. What if everything really is made of tiny, invisible things? By the 17th century, the ancient model of air, fire, water, and earth was beginning to show cracks. Curious minds across Europe were poking, heating, sealing, and occasionally exploding things in their quest to understand what the world was truly made of.
And one of the great puzzles that caught their attention was air. This invisible, seemingly weightless substance that filled the space around them. What was it, exactly? Was it a kind of nothing? Or was there more to it than met the eye? Turns out there was a lot more. At the center of this intellectual gust was Robert Boyle, an Irish natural philosopher with a penchant for careful measurement and a surprisingly robust tolerance for unpleasant smells. Boyle didn't buy the classical idea that air was simply an ethereal essence. To him, air was a substance, a real physical something that could be weighed, compressed, and studied. With the help of his friend and collaborator, Robert Hooke, he built elaborate air pumps and began experimenting with vacuum chambers. Now, to appreciate just how revolutionary this was, imagine a world where people weren't even sure a vacuum could exist. Aristotle, still clinging tightly to the intellectual stage, had declared that nature abhors a vacuum. But Boyle, ever the curious skeptic, decided to find out for himself. When he removed the air from a chamber using his pump, he noticed some fascinating things. Candles went out, animals struggled to breathe, and the usual sounds of life vanished into an unnerving silence. Whatever air was, it wasn't nothing. It had substance, it had power. Boyle and Hooke's experiments helped usher in the idea that air was made of particles, tiny bits of matter with space between them. These particles could move, collide, and push against the walls of a container, and that pressure, they found, changed depending on how much space the particles had to move in. Squeeze the container and the pressure rises. Let it expand and the pressure drops. This wasn't just a fun party trick with bell jars. It was the beginning of a profound shift in thinking. Boyle formalized the relationship between pressure and volume into what's now known as Boyle's law. If the temperature remains constant, the pressure of a gas is inversely proportional to its volume. In other words, if you have the volume, you double the pressure. It was one of the first mathematical laws to describe how matter behaves in a measurable, predictable way. And unlike earlier philosophical theories, Boyle's work was grounded in repeatable experiments. He wasn't just speculating about the invisible, he was measuring its effects with instruments and equations. This was a major turning point. Science was beginning to pull away from metaphysical musings and move toward empirical, testable knowledge. Instead of imagining what air might be, Boyle and his colleagues were capturing it in glass tubes and making it do tricks on command. Robert Hooke, meanwhile, was no mere assistant. A polymath with a sharp mind and a sometimes sharper temper, Hooke made contributions that ranged from biology to architecture. In the world of gases, he played a key role in refining the air pump and conducting experiments that showed how living creatures depended on air. He even proposed early ideas about combustion and respiration, suggesting that something in the air was consumed in both processes, a hint, perhaps, of oxygen, though that discovery would come later. What really began to click in this period was the realization that gases behave like matter in motion. Rather than treating air as a uniform, ghostly substance, scientists started to think of it as a swarm of tiny particles zipping around and bouncing off surfaces. These movements could explain pressure, temperature, and even the behavior of different gases under different conditions. The idea of particles in motion wasn't entirely new. Democritus would have smiled. But now it was being backed up with tools, math, and experiment. Air was not an invisible magical element. It was a dynamic collection of particles, and those particles obeyed rules. Boyle also took great care to distance himself from alchemical traditions. He famously wrote The Skeptical Chemist, a book that questioned the traditional elemental framework and argued for a more modern, analytical approach. In it, he proposed that substances were composed of corpuscles, or small bits of matter, which combined in various ways to form the materials we observe. It was a kind of proto-atomic theory, still speculative, but more grounded than the old symbolic models. One of the beautiful things about this period is that science was still half experiment, half theater. Imagine candlelit labs filled with bubbling flasks and brass instruments, with curious gentlemen and powdered wigs debating over whether air had weight. Spoiler alert, it does. Boyle demonstrated this by trapping air in containers and comparing their weights on a scale. That was a big deal. Until then, many believed that since air was invisible, it must be weightless. Not so. As more scientists joined the fray, gases began to reveal their secrets. Hydrogen, oxygen, nitrogen, all these components of air would eventually be isolated and named. But for now, the key insight was simply that air was something that could be compressed, measured, and crucially, understood. And just like that, the study of matter began to evolve into something sharper, cleaner, and more quantitative. Instead of mystical essences and symbolic correspondences, people were working with pressure gauges, barometers, and air pumps. Chemistry was starting to stretch its legs, ready to walk away from its alchemical adolescence and step into a more experimental adulthood. By showing that even something as invisible as air had structure and behavior, Boyle helped lay the groundwork for modern chemistry and physics. He didn't solve all the mysteries of matter, but he cracked the door open just enough for the light to get in. And once people realized that even something as invisible as air had structure and behavior, it was only a matter of time before they'd turn their gaze to other, even smaller things. In the bustling streets of 18th century Paris, amid powdered wigs, philosophical salons, and the distant rumble of revolution, a man named Lavoisier was quietly changing the course of science forever. He wasn't chasing gold or a divine elixir. He wasn't dreaming of invisible atoms or wrestling with metaphysical fire. What he was doing with remarkable precision was weighing things carefully, obsessively, and in doing so, he helped transform chemistry from a mystical art into a true science.
Antoine Lavoisier is often called the father of modern chemistry, and not just because he had excellent handwriting or a strong jawline. He brought clarity, structure, and above all, measurement to a field that had been muddled for centuries with vague terminology and loose reasoning. Where alchemists had spoken of phlogiston and essence, Lavoisier spoke of oxygen, mass, and conservation. But to understand how radical that was, it helps to appreciate the scientific mess he inherited. At the time, one of the dominant theories about combustion, how things burn, was the phlogiston theory. According to this idea, every combustible material contained a mysterious substance called phlogiston. When something burned, it was thought to release its phlogiston into the air. A flame, therefore, wasn't a chemical reaction, it was just phlogiston leaving the building. There were some problems with this theory, such as the fact that certain metals gained mass when they were burned rather than losing it, as you'd expect if phlogiston was flying away. But instead of ditching the theory, many tried to explain this away by suggesting that phlogiston had negative weight. Yes, negative weight, like an invisible balloon hiding in your coal. Lavoisier didn't buy it. He had a different approach, one rooted in experimentation and relentless accuracy. He believed that the only way to understand a chemical reaction was to know exactly what went in and exactly what came out. No guesswork, no metaphysical fudge. And so he built himself a laboratory, not just any lab. His was the scientific equivalent of a grand ballroom filled with polished copper instruments, balances sensitive enough to detect the difference in a single grain of sand, sealed glass vessels, and elaborate gas collection setups. He spared no expense, which was convenient since he was also a wealthy tax collector. His wife, Marie Anne, was a brilliant collaborator who not only illustrated his experiments, but also translated scientific papers from English to French and helped edit his work. If you ever imagined chemistry as a solo pursuit of grimy beakers in a dungeon, Lavoisier's gleaming lab would have felt like a breath of fresh, measured air. One of his most important discoveries came from studying combustion more closely than anyone before him. He observed that when a metal like mercury was heated in air, it formed a calx, a powdery substance that we now know is an oxide. But here's the twist. The calx weighed more than the original metal. Instead of assuming that phlogiston had vanished, Lavoisier suspected that something had joined with the metal.
Using closed vessels and carefully controlled air volumes, he demonstrated that a portion of the air was consumed during the process. That missing portion, he realized, was not a void or a loss, but oxygen binding to the metal. From this, he formulated one of the most important principles in all of science, the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. It only changes form. Burn a log, and it might seem to vanish, turning to ash and gas. But if you could capture everything, the smoke, the soot, the leftover carbon, the total mass would remain exactly the same. This might sound obvious today, but it was revolutionary at the time. The idea that chemical processes followed precise, accountable rules down to the milligram was a major leap forward. Lavoisier's insistence on measurement did more than just tidy up a few theories. It changed the way chemistry was done. Before him, many reactions were described qualitatively. This powder smells sweet, that one turns blue, this mixture gets warm. Lavoisier pushed for a quantitative approach. How much heat? How much weight? How much gas? Chemistry started to shift from a descriptive art to a mathematical science. Instead of swirling symbols and esoteric labels, Lavoisier called for a new language based on observable facts. And he didn't stop at oxygen. Lavoisier was instrumental in identifying and naming several key elements. He helped establish the modern understanding of hydrogen and nitrogen, and played a central role in compiling the first systematic list of elements. Gone were the days of earth and fire. Now there were real substances, each with measurable properties and predictable behaviors. In 1789, he published the Traité élémentaire de chimie, elementary treatise of chemistry, which many considered the first modern chemistry textbook. It introduced a systematic chemical nomenclature and clearly outlined chemical reactions using equations. It's hard to overstate how much this book changed the game. For the first time, chemistry students could learn from a structured, logical system rather than being handed a mysterious collection of symbols and recipes. He also coined the term oxygen from the Greek for acid former, based on his ultimately incorrect belief that all acids contained oxygen. Not every guess was perfect, but his overall method, observe, measure, repeat, was solid gold. There's a poetic irony to Lavoisier's life, because while he brought order and reason to the science of matter, the world around him was descending into chaos. The French Revolution was gathering steam, and Lavoisier's role as a tax collector made him a target. Despite his scientific fame, he was arrested and sentenced to death. In 1794, at the age of 50, he was executed by guillotine. The mathematician Joseph Louis Lagrange remarked afterwards, "It took them only an instant to cut off that head, and 100 years may not suffice to produce another." Lavoisier's death was a tragic loss to science, but his work endured. His approach set the stage for generations of chemists to come. The laboratory became a place of precision, not potions. Reactions were balanced like equations. Substances were named, classified, and tested. Matter had rules, and those rules could be learned, tested, and taught. Most importantly, he gave us confidence that the physical world could be understood through careful observation, that you could weigh air, count invisible gases, and find order in the flicker of a flame. Through his experiments, matter began to feel real in a way it hadn't before. Not just the stuff of dreams or elements, but measurable, quantifiable, knowable. Lavoisier didn't invent the atom, but he carved a path straight toward it. By insisting that every chemical process followed the same laws, no matter how dramatic or subtle, he helped lay the intellectual foundation for seeing matter as a system of parts and patterns. In the glow of his laboratory lamps, weighed on brass ales and sealed in glass, the chemistry of the future had quietly begun. In the misty hills of early 19th century England, where factories were multiplying and chimneys coughed coal smoke into the sky, a quiet school teacher named John Dalton was busy resurrecting a 2,000-year-old idea. He wasn't doing it with flashy experiments or fiery demonstrations. No explosions, no dramatic lectures, just notebooks, numbers, and a deep fascination with the invisible.
Dalton, born in a modest village in Cumbria in 1766, was the kind of scientist who liked to count things. He had a passion for measuring the world and a deep love for dry precision. As a Quaker, he wore plain clothes, spoke plainly, and lived plainly. But his ideas were nothing but plain. He started his scientific career studying the weather. Obsessed with clouds and pressure, he recorded thousands of weather observations, one raindrop at a time. But in trying to understand the atmosphere, Dalton became deeply interested in gases, not just their behavior, as Boyle had explored, but what they were made of. Why did different gases behave so differently from each other? Why didn't they all mix in evenly like tea and sugar? Dalton noticed that when gases like nitrogen and oxygen were present in the same space, they didn't always blend into a uniform fog. They stayed oddly distinct. He began to wonder, maybe these gases weren't smooth and continuous. Maybe they were made of tiny, separate particles, particles that had weight, particles that were different from one gas to another. In short, maybe Democritus had been right all along. What Dalton did next was both bold and beautifully logical. He revived the ancient idea of atoms, but this time he brought data, lots of data. Dalton proposed that all matter is made of indivisible atoms and that all chemical elements are composed of their own unique kind of atom. Hydrogen atoms are not the same as oxygen atoms. Sulfur atoms are different again. These aren't just philosophical particles floating through the void, they're specific, measurable entities with real weight and behavior. Even more importantly, Dalton introduced the idea of atomic weight. He proposed that each type of atom has a specific mass, and that chemical reactions are simply rearrangements of these atoms. When two elements combine, their atoms form compounds in fixed whole number ratios. For example, one atom of hydrogen might combine with one atom of oxygen, or two, or three, but never with half an atom. It was like the chemistry version of Lego, with atoms snapping together in predictable, countable ways. This idea helped explain why compounds always contain the same proportions of elements. Water, for instance, always has the same ratio of hydrogen to oxygen. It's not a coincidence, it's arithmetic. Dalton showed that this wasn't just a curious pattern, but a fundamental truth about how atoms behave. To make these ideas easier to understand, Dalton began drawing little circles to represent atoms. He used different symbols to represent different elements: a plain circle for hydrogen, a circle with a dot for oxygen, a circle with a cross for iron, and so on. It was simple, almost childlike, but profoundly effective. These were the first atomic diagrams in modern science, a symbolic language for the invisible world. His diagrams and ideas were published in 1808 in a book called A New System of Chemical Philosophy. The title wasn't exactly catchy, but the contents were revolutionary. Chemists now had a framework for understanding why substances combined the way they did. It wasn't alchemical whim or elemental essence, it was atomic ratios and mass. Dalton's atomic theory rested on a few basic postulates. First, all matter is made of indivisible atoms. Second, all atoms of a given element are identical in mass and properties. Third, compounds are combinations of different kinds of atoms. Fourth, chemical reactions involve the rearrangement of atoms, not their destruction. And fifth, atoms cannot be created or destroyed in a chemical reaction. Some of these ideas would eventually be revised. It turns out atoms can be split, and isotopes mean not all atoms of an element are truly identical. But for the early 19th century, this was a stunningly useful model. It made chemistry predictive, not just descriptive. Dalton's work didn't just explain what chemists were already observing, it gave them a way to organize it. By assigning weights to atoms and identifying how they combined, he laid the groundwork for something extraordinary, a deeper classification of elements.
Soon, other chemists began to adopt and refine his ideas. They improved the accuracy of atomic weights, developed better techniques for isolating elements, and started noticing patterns. Certain elements had similar properties. Some reacted the same way. Others seemed to repeat at regular intervals when listed by mass. The periodic nature of elements was slowly coming into focus. Dalton didn't live to see the full emergence of the periodic table, but his atomic theory lit the path that led to it. By giving atoms distinct identities, he transformed chemistry from a messy collection of recipes into a rational science. Elements became more than just names in bottles. They were defined by their atomic character, their weight, their bonds. It's worth noting that Dalton wasn't a celebrity in his time. He never held a prestigious academic post. He kept teaching at a small Quaker school in Manchester and continued his meteorological observations until the end of his life. But his ideas quietly reshaped the world. Today, every chemistry student learns about atomic weights, molecular ratios, and Dalton's laws of proportion. They may not know that he also studied colorblindness, now sometimes called Daltonism, or that he was terribly fond of long walks. But they know his dots. His little atomic sketches launched a revolution, not with a bang, but with a scribble. Perhaps the most charming thing about Dalton was his devotion to logic. He didn't invent atoms because it was fashionable. In fact, most scientists at the time still preferred more fluid theories of matter. But Dalton, armed with his experimental results and a stubborn sense of reason, followed where the numbers led. If matter behaved in consistent ratios, there had to be a reason. If different elements combined in simple whole numbers, there had to be a pattern, and that pattern, he believed, was made of atoms. The power of his theory lay in its beautiful simplicity. It explained chemical reactions without needing mysterious forces or hidden fluids. It treated substances like puzzles made from tiny parts, parts that you could count, weigh, and rearrange. For the first time, matter wasn't just observed, it was modeled. It had structure. It had math. Dalton's world was still one of hand-blown glassware and flickering lamps. There were no electron microscopes, no lasers, no particle accelerators. But even without ever seeing atoms, he showed us how to think about them. His ideas were clear enough to hold, small enough to picture, and solid enough to build on. And so, thanks to a quiet teacher with a sharp pencil and a sharper mind, atoms became more than a whisper. They became a language, a way to describe the universe one particle at a time. In the snowy heart of 19th century Russia, wrapped in furs and surrounded by stacks of chemical data, Dmitry Mendeleev was doing something unusual for a scientist. He was playing a kind of intellectual solitaire with the elements. It was the late 1860s, and chemistry was still a bit of a Wild West. Scientists had discovered dozens of elements by now, but the list was messy, an ever-growing collection of substances without clear relationships or structure. It was like owning a dictionary where the words were tossed in at random. And Dmitry Ivanovich Mendeleev, with his thick beard and sharper-than-average curiosity, decided to bring order to the chaos. Dmitry Ivanovich Mendeleev was no stranger to perseverance. Born in a small Siberian town in 1834, the youngest of at least 14 children, yes, 14, he was raised in the kind of environment that breeds either despair or relentless determination. He chose the latter. After his father lost his sight and passed away, and his mother's glass factory burned down, his mother still managed to get him to university by dragging him across the country. Literally, she took him by horse and carriage from Tobolsk to St. Petersburg so he could enroll in school. As far as supportive parenting goes, that's a hard act to follow. By the time he became a professor, Mendeleev was deeply immersed in the puzzle of the chemical elements. More and more were being discovered, but their relationships remained unclear. Some elements behaved similarly to others, Lithium, sodium, and potassium all reacted violently with water, for example, but nobody had found a master key to explain the patterns. Some tried grouping them by atomic weight, others looked at reactivity, but the arrangements were inconsistent and left a lot of questions hanging. Mendeleev had a different strategy. He approached the problem like a card game. In fact, he used actual cards, one for each known element, on which he wrote the element's properties, atomic weight, chemical behavior, density, and more. Then he shuffled and arranged them over and over, searching for a pattern that made sense. It was like a scientific version of Tetris, only with hydrogen and chlorine instead of blocks. Eventually, a remarkable rhythm began to emerge. Mendeleev noticed that if he arranged the elements in order of increasing atomic weight, certain properties repeated at regular intervals. Soft metals, reactive halogens, noble gases, they all showed up in a kind of musical loop. It was as though the elements were singing in harmony, each voice returning after a predictable number of steps. This led him to construct what would become known as the periodic table, a grid where elements were placed not just by weight, but by their chemical behavior. Elements in the same column or group shared similar properties. The alkali metals formed one family, the noble gases another, and the transition metals marched across the center like a well-trained army. But Mendeleev didn't stop there. He noticed something even more profound. Some elements didn't quite fit the pattern if arranged strictly by atomic weight. Instead of forcing them into awkward spots, he moved them boldly. He swapped elements like tellurium and iodine, even though their weights were out of order, because their properties lined up better that way. This was a risky move. It meant trusting the pattern more than the numbers, but it paid off. Most impressively, Mendeleev left deliberate gaps in his table, empty spaces. These weren't mistakes, they were predictions. He boldly declared that elements should exist in those spaces, even though nobody had discovered them yet. And he didn't just shrug and move on. He described the properties those missing elements would likely have, their weights, densities, oxides, and affinities. One such predicted element, which he called Eka aluminum, Eka meaning one beyond in Sanskrit, would later be discovered and named gallium. Its properties matched Mendeleev's forecast almost perfectly. Another, Eka silicon, turned out to be germanium. One by one, the gaps in his table were filled, not by guesswork or luck, but by the structure he had seen hiding in plain sight. This predictive power gave the periodic table a credibility few scientific models ever achieve. It wasn't just a retrospective summary, it was a forward-looking map of the elemental world. Mendeleev had turned chemistry into a guided tour rather than a scavenger hunt. At first, not everyone was convinced. Many chemists were skeptical of the rearrangements and the empty spaces. But as the predicted elements were discovered and their properties matched the forecasts, Mendeleev's reputation soared. He had done what no one else had managed. He brought a deep and elegant order to the fundamental building blocks of matter. What's particularly charming about Mendeleev's approach is how intuitive it was. He didn't start with a grand theory or a complex formula. He started with index cards, careful observation, and a refusal to give up on the idea that nature must have some kind of logic. He believed the elements were telling a story, and he was determined to listen until he could understand the plot. Of course, Mendeleev wasn't working with the modern understanding of atoms. The concept of protons and electrons hadn't yet been nailed down. He didn't know about atomic number, the count of protons that uniquely identifies each element. That would come later. But his faith in the periodicity of properties was strong enough to override even the official numbers. And when atomic number was eventually discovered, it turned out to explain why the table worked. It wasn't atomic weight that determined placement, but atomic number. And Mendeleev had, through intuition and logic, gotten it mostly right anyway. Beyond his contributions to chemistry, Mendeleev was a bit of a polymath. He worked on everything from oil refining to agricultural reform to the standardization of vodka. He even tried to devise a unified theory of everything, though that part didn't quite pan out. Still, his versatility reflected the same spirit of curiosity that made his table possible. He wanted to understand how things fit together, whether they were atoms, molecules, or economic policies. Mendeleev's periodic table is now taught in every chemistry classroom around the world. It has grown and evolved over time. New elements have been discovered, new rows added, but the bones of his structure remain. It's a rare scientific creation that still stands strong over 150 years after its invention. The table has become not just a reference, but a symbol of scientific order, predictability, and beauty. There is something deeply satisfying about the idea that the universe has a rhythm and that we can learn to hear it. That the elements, those raw ingredients of stars and stones and soup, can be arranged into a coherent pattern that stretches across time and space. Mendeleev didn't just give us a way to memorize chemical facts, he gave us a way to see them, lined up like dancers in a cosmic waltz. And it all started with a game of cards, a stack of notes, and a refusal to accept that nature could be so disorganized. In a world growing more complex by the day, Mendeleev showed that even the smallest pieces can reveal a grand design if you're willing to look closely, trust your instincts, and maybe shuffle the deck once or twice.
By the late 19th century, atoms had settled comfortably into the role of fundamental building blocks, indivisible, solid, and reliable. Dalton had given them mass and identity, and Mendeleev had organized them into a neat, elegant table. Chemists and physicists alike were growing rather fond of the idea that the atom was the final stop on the journey inward. A tidy little sphere, behaving itself politely, forming bonds and reactions without too much fuss. And then, something strange began to flicker out of glass tubes and into the minds of puzzled scientists. A curious, ethereal, glowing beam, seemingly emerging from nowhere and refusing to follow the rules. These were the cathode rays, and they would crack open the atomic world in ways nobody saw coming. Cathode rays first showed up in experiments with vacuum tubes, sealed glass chambers from which most of the air had been removed. When a high voltage was applied between two metal electrodes inside the tube, a mysterious greenish glow appeared. The glow always seemed to originate from the negative electrode or cathode and shoot across the tube in a straight line. These rays could make fluorescent materials light up, cast shadows, and even spin tiny paddle wheels placed in their path. Clearly, they weren't just light. They had momentum. They were something. But what? Exactly. Some scientists thought the rays were a kind of wave, maybe a strange light wave bouncing around inside the tube. Others suspected they were particles. But if so, particles of what? Atoms were supposed to be indivisible, whole, unbreakable units. What kind of particle could come out of one? Enter Joseph John Thomson, or JJ to his colleagues, a Cambridge physicist with a brilliant mind and a delightfully understated demeanor. Thomson didn't set out to shatter the atomic model. He was just trying to understand the behavior of these curious rays. But as it often goes in science, a simple question turned into a revolutionary discovery. Thomson's key insight came from bending the rays. He built an apparatus that allowed him to apply electric and magnetic fields to the beam of cathode rays. If the rays were made of charged particles, then the fields should deflect them. And they did, beautifully. The rays curved under the influence of the fields, just as a stream of charged bullets would. From the degree of deflection, Thomson was able to calculate something extraordinary: the ratio of the charge of these particles to their mass. And the result was astonishing. These particles were about 2,000 times lighter than a hydrogen atom, the lightest known atom at the time. That meant they couldn't be atoms at all. They were something inside the atom, something smaller and clearly charged. Thomson had just discovered the electron. It was the first subatomic particle ever identified, and it completely shattered the idea of the atom as indivisible. The solid sphere was no longer so solid after all. The atom had an inner life, a structure. There were bits within it, and those bits could move. To explain this strange new reality, Thomson proposed a model of the atom that looked, well, a bit like dessert.
He imagined the atom as a kind of soft, positively charged sphere, like a cake or a cloud of pudding, with the negatively charged electrons embedded throughout, like raisins. This became known as the plum pudding model, a name that stuck despite sounding like something from a Victorian cookbook. It was a strange image, but it made sense at the time. If atoms were electrically neutral, and now we knew they contained negatively charged electrons, then there had to be some positive charge in there too to balance things out. Thomson's model pictured this positive charge as a kind of diffuse goo, with the electrons floating in it like fruit in jelly. Not everyone was thrilled about comparing atoms to pudding, but the model had real strengths. It accounted for the existence of electrons, it explained why atoms didn't have an overall electric charge, and it introduced for the first time the idea that atoms could have internal parts, discrete entities with their own properties. This was a huge shift. For over 2,000 years, atoms had been considered the most fundamental bits of matter. You couldn't go smaller. You couldn't look inside. But here was a Cambridge physicist saying quite cheerfully that not only could atoms be split, but they had structure, complexity, and behavior. The atomic world had cracks, and in those cracks, the light of new understanding was beginning to shine. Of course, the plum pudding model wouldn't last forever. It had its flaws. It couldn't explain how atoms emitted light. It couldn't account for the full range of observed phenomena in chemical reactions. But it served a crucial purpose. It opened the door. Once electrons were discovered, scientists began to wonder what else might be hiding inside the atom. If there were negatively charged particles, where was the positive charge located? Was it really spread out like pudding, or was it more concentrated? Was there a center? Were electrons just floating, or did they move in patterns? But before the atom could be rebuilt, it had to be broken open. And that's what the cathode ray experiments did. They cracked the shell of the atom, showing that the neat, indivisible spheres of Dalton's world were in fact teeming with motion and mystery. Thomson's work didn't stop with electrons. He went on to explore ions, isotopes, and mass spectrometry, making vital contributions to fields that hadn't even been named yet. He was knighted, awarded a Nobel Prize, and eventually became the president of the Royal Society. Not bad for a man who had once struggled with mathematics and almost became a railway engineer. And perhaps the most poetic part of the story, one of Thomson's students, a young physicist named Ernest Rutherford, would go on to propose an entirely new model of the atom, one that left the plum pudding behind in favor of orbits and nuclei. But even Rutherford never forgot the importance of his mentor's work. Without Thomson's electron, there would be no need to rethink the atom in the first place. The discovery of the electron was like opening a trap door in the floor of physics. Suddenly, there was a whole new level of reality beneath our feet, a level where particles zipped and spun, where charges clashed and combined, where mass and energy played by strange new rules. The atom was no longer the final answer. It was the beginning of a deeper question. And it all started with a flicker in a glass tube, a ray from nowhere, carrying with it the hint that even the smallest things might not be so simple after all. Picture this. It's the early 1900s, and you're in a lab with sheets of gold so thin they're practically see-through. A mysterious radioactive source sits on the table, and an idea is in your head that atoms are like a cosmic dessert, soft blobs of positive charge with electrons floating inside like raisins. That was the state of atomic theory, courtesy of J.J. Thomson's plum pudding model. Now, enter Ernest Rutherford, a New Zealand-born physicist with a booming voice, a taste for bold ideas, and a fondness for smashing things to see what happens. Rutherford had already made a name for himself exploring radioactivity, but now he had a new question. What does the inside of an atom really look like? To find out, he designed one of the most famous experiments in all of science. It was elegant, simple, and utterly explosive in its implications. Rutherford and his colleagues, Hans Geiger and Ernest Marsden, fired tiny particles called alpha particles at an ultra-thin sheet of gold foil. Alpha particles, for reference, are positively charged and relatively hefty as subatomic particles go, more like bowling balls than ping pong balls. According to the prevailing model, those alpha particles should have zipped straight through the gold like peas through fog. After all, the plum pudding atom was supposed to be a soft, diffused cloud of positive charge, offering little resistance. So imagine everyone's surprise when some of those alpha particles didn't pass through at all. A few bounced back, not just deflected a little, but bounced straight back toward the source. Rutherford famously compared it to firing a cannonball at a piece of tissue paper and having it ricochet. The team was stunned. These weren't rare flukes either. While most of the particles passed through as expected, a measurable number were deflected at large angles and some even reversed course. Something inside the atom was solid, dense, and powerful enough to knock an alpha particle off its path. This changed everything. From these surprising results, Rutherford proposed a bold new model. Atoms weren't squishy balls of pudding. They were mostly empty space, with almost all of their mass concentrated in a tiny central region, which he called the nucleus. This nucleus, he reasoned, must be positively charged since it repelled the positively charged alpha particles. The electrons, then, must be whizzing around the central nucleus, held in place by the electric attraction between opposite charges. It was a shocking idea, literally and figuratively. The atom, long considered indivisible and uniform, was suddenly full of structure, and most of it was, in fact, nothing at all. That's right. Almost all the mass of an atom is crammed into an unimaginably small center, while the rest is empty space. If the nucleus of a hydrogen atom were the size of a marble, the electron would be orbiting nearly a football field away. The atom is a ghost with a solid heart. The nuclear model of the atom was born. This shift wasn't just a scientific footnote, it was a revolution. It explained the gold foil results with precision, and it opened up a whole new understanding of atomic behavior. The nucleus, as Rutherford described it, held protons, the positively charged particles he had indirectly discovered through this work. He suspected there might be other particles lurking there too, but that mystery would take a few more decades to unravel. Of course, the nuclear model raised some questions of its own. If electrons were orbiting the nucleus like planets around the sun, what was keeping them from spiraling inward and crashing into it? Classical physics suggested that an accelerating charge, like an electron moving in a circle, should emit energy and lose speed. That would make atoms fundamentally unstable, which clearly wasn't the case. Your face, your tea, and the table beneath it are all holding together just fine. But even with that lingering puzzle, Rutherford's discovery laid the foundation for the next century of atomic exploration. He had peeled back the curtain and shown that the atom wasn't a uniform sphere. It had parts, it had architecture, it had a dense center and distant edges. It was, in essence, a tiny solar system, one where electrostatic forces replaced gravity and particles played cosmic roles on a miniature stage. The experiment itself was a masterclass in simplicity and genius. Using just a radioactive source, gold foil, and a fluorescent screen to detect the flashes of scattered particles, Rutherford and his team revealed the hidden structure of the invisible. They didn't need massive machines or advanced computing, just patience, precision, and a willingness to be surprised. Rutherford himself had a talent for turning that surprise into insight. He was famous for his wit and his insistence on clear thinking. Once, when a student was unsure about a complicated mathematical problem, Rutherford replied, "Don't let me hear anyone use the word can't unless they're talking about the laws of physics." He was a man of conviction and curiosity, a perfect combination for someone digging into the heart of matter. And he didn't stop with gold foil. His later experiments explored nuclear reactions, leading to the discovery that atoms could change their identity by altering their nuclei. In essence, Rutherford cracked open not just the structure of the atom, but the secret of the elements themselves. He laid the groundwork for nuclear physics, atomic energy, and the discovery of new particles. The gold foil experiment marked a turning point. It wasn't just that the model of the atom changed, it was that the way scientists thought about atoms changed. No longer simple and indivisible, atoms were revealed to be dynamic, structured, and most astonishingly of all, mostly empty. The solid world was made of insubstantial things. Tables, trees, and toes were mostly space, stitched together by invisible forces. It's one of the great ironies of physics. The more we zoom in, the more we find absence where we expected substance. But in that absence lies power. The nucleus, tiny and dense, holds nearly all the atom's mass. The electrons, distant and lively, define its volume and behavior. And in between, a vast stillness, like the quiet between stars. Rutherford's model would be refined over time. Others would come along to explain the motion of electrons, the nature of the nucleus, and the rules that governed atomic structure. But the core insight, that atoms have a dense center and are mostly space, remains as true today as it was on the day those alpha particles first bounced off a golden sheet. What began as a simple experiment with some gold foil and a few radioactive specks turned into one of the greatest surprises in science. In a room filled with flashing detectors and falling particles, a new vision of the atom was born, one that would change our understanding of matter forever. And to think it all came from something as gentle as a flicker on a screen, and a scientist bold enough to ask, why did that bounce? By the early 1930s, the atom was beginning to resemble a rather crowded cocktail party. We had electrons zipping around in orbits, a tiny but hefty nucleus sitting in the center, and inside that nucleus, positively charged protons rubbing shoulders and pretending they got along. And yet something still didn't quite add up. Physicists had been puzzling over the atomic nucleus for years. If protons carried positive charge, and if like charges repel each other, then what on earth was holding them together in such close quarters? It was like trying to stack a bunch of magnets all facing the same way and expecting them to stay put. Nature didn't seem to mind, but physicists did. And then there was the mystery of atomic mass. When scientists tallied up the mass of an atom based on the number of protons and electrons, the numbers never quite matched what they measured experimentally. There was always a little extra weight. Not just a huge amount, but enough to raise an eyebrow. Clearly, something was hiding in the nucleus. Something with mass but no charge. Something that could add heft without adding a push or a pull. Entered James Chadwick, a quiet and determined British physicist who looked less like a particle smasher and more like someone who might help you find a good book in a quiet library. But make no mistake, Chadwick was on the hunt for a ghost. For years, physicists had speculated that a neutral particle might exist, but proving it had proven elusive. In 1932, Chadwick finally caught it. The breakthrough came when he revisited a puzzling experiment by Frederick and Irene Joly Curie, who had bombarded beryllium with alpha particles and noticed that it emitted an unusual but highly penetrating radiation. They assumed it was gamma rays, very high-energy electromagnetic waves. But the energy levels seemed oddly high, too high, almost suspiciously so. Chadwick suspected something else entirely. What if this wasn't electromagnetic radiation, but a stream of actual particles? Particles that had no electric charge and yet had enough mass to knock other atoms around. He tested the idea by letting the mysterious radiation hit various targets like hydrogen and nitrogen and measuring the recoil. Based on the results, it became clear. This radiation consisted of particles about the same mass as protons, but with no charge. He had found the neutron. It may not have had the theatrical sparkle of discovering the electron or the dramatic surprise of the gold foil experiment, but the neutron turned out to be absolutely essential. It completed the picture of the atom's nucleus. Now it made sense why the mass of atoms was often more than the number of protons alone could explain. Those extra particles weren't hiding, they were simply neutral. With the neutron added to the mix, the atom's nucleus became a more comfortable, albeit busier place. Protons still repelled each other with their positive charges, but neutrons acted as a kind of nuclear buffer. They added mass and stability, helping to glue the nucleus together through what we now call the strong nuclear force. It's one of the four fundamental forces of nature, and it's the one that's responsible for keeping the atomic nucleus from flying apart in a flurry of electrostatic anxiety. The neutron was also key to understanding isotopes. Chemists had long known that some atoms of the same element could behave identically in chemical reactions, but have different masses. These were called isotopes, and now we knew why. They had the same number of protons. That's what made them the same element, but different numbers of neutrons, giving them different atomic masses. For example, carbon usually has 6 protons and 6 neutrons, carbon 12. But there's also carbon 13 with an extra neutron, and carbon 14, which is radioactive and famously used in dating ancient artifacts. Thanks to neutrons, atoms came with variations. Same element, different flavor. Chadwick's discovery also opened the door to a new era of nuclear physics. Neutrons, unlike protons or electrons, could penetrate atomic nuclei without being repelled or deflected by electric charge. That made them ideal tools for poking and prodding atoms, splitting nuclei, and initiating chain reactions. In fact, the neutron would soon become the star player in nuclear fission. When scientists later bombarded heavy elements like uranium with slow-moving neutrons, the atoms didn't just absorb them, they broke apart. And when they did, they released enormous amounts of energy along with more neutrons to keep the reaction going. This chain reaction would lead to both nuclear power and nuclear weapons, for better or for worse. But at the core of it all was the humble neutron, silently slipping into nuclei and turning matter into energy. As discoveries go, the neutron is almost an anti-celebrity. It doesn't sparkle like the electron or shout like the proton. It doesn't carry charge. It never shows up in electric currents. It just sits there, solid and stoic, adding weight and binding protons like a patient sibling holding hands at the dinner table to stop a food fight. Yet, despite its quiet nature, the neutron plays a vital role in everything from atomic stability to stellar physics. In the hearts of stars, where atoms are fused under immense pressure, neutrons are constantly being shuffled and exchanged. In neutron stars, those ultra-dense remnants of collapsed supernovae, matter is compressed into a sea of neutrons so tightly packed that a single teaspoon would outweigh a mountain. Chadwick, for his part, didn't bask in celebrity. He was awarded the Nobel Prize in Physics in 1935, and he continued his work during a turbulent time in history. During the Second World War, he became involved in the British atomic bomb project and later joined the Manhattan Project in the United States. Though a reserved man, he understood the significance of his work and the dual-edged sword it represented. The neutron may have arrived later to the atomic party, but it changed everything. It made the nucleus complete. It made isotopes understandable. It made nuclear reactions controllable, or sometimes uncontrollable. Without it, atoms wouldn't stick together properly. Nuclear reactors wouldn't function, and carbon dating wouldn't tell us how old ancient bones are. Even our understanding of particle physics and quantum mechanics would be incomplete without accounting for the neutron's subtle mass and its participation in fundamental forces. It's funny how much can depend on something that doesn't even have a charge. In the end, the discovery of the neutron added the final major puzzle piece to the classic image of the atom: electrons buzzing around a dense nucleus made of protons and neutrons. It gave structure and symmetry to our understanding of matter, and it laid the groundwork for decades of new questions. Because in science, every answer tends to generate at least 3 new questions. And while the neutron answered the mystery of atomic mass and nuclear cohesion, it also hinted at deeper layers yet to come. What held the protons and neutrons together? What were neutrons made of? Could they be split further? The journey inward was far from over. But for that moment, in the early glow of Chadwick's careful measurements, the atom finally felt, if not complete, then at least a little less mysterious. With the neutron in place, the atomic family finally had its quiet middle child. No flash, no fuss, just weight, balance, and the glue that holds the heart of matter together. At first glance, light seems like the most familiar thing in the universe. We wake up with it, we read by it, we bask in it, and we flick switches expecting it to appear on command. Light is comfort, clarity, sunrise, and science fair. But the more scientists tried to understand light, not just use it, but understand it, the stranger it became. By the turn of the 20th century, light was starting to act in ways that no one could quite explain. It flickered between two identities, sometimes a wave, sometimes a particle, sometimes both, sometimes neither. Like a magician who never reveals the trick, light refused to play by the old rules. Back in the 19th century, most physicists were pretty confident about what light was. Thanks to the work of James Clerk Maxwell and others, light was understood as a wave, an electromagnetic wave to be precise. It could be reflected, refracted, and diffracted. It had wavelength and frequency. It traveled through space like ripples through water, except it didn't need a medium. Waves were smooth, continuous, and reliable. Everything was great, until it wasn't. Enter Max Planck, a German physicist who was about as skeptical of revolutionary science as you could get. He was calm, methodical, and very fond of classical physics. But in the late 1800s, he found himself tangled into a very non-classical problem, the ultraviolet catastrophe. This was the unsettling prediction that, according to classical theory, a black body, an idealized object that absorbs and emits all frequencies of radiation, should emit infinite energy at ultraviolet and higher frequencies. In other words, if the math were right, every warm object in the universe should be blasting us with deadly rays all the time. Spoiler, this was not happening. Planck didn't set out to overhaul physics. He just wanted the math to work. In a move he described as an act of desperation, he made a peculiar assumption. What if light energy wasn't emitted in a smooth, continuous stream? What if it came in discrete packets, little bundles he called quanta? He introduced a new constant, now known as Planck's constant, to describe the size of these energy bundles. According to his formula, the energy of each quantum is proportional to the frequency of the light. Higher frequency, higher energy; lower frequency, lower energy. Suddenly, the math lined up perfectly with experimental results. The ultraviolet catastrophe was avoided. Everyone exhaled, except Planck wasn't entirely sure what he'd just done. He didn't know if quanta were real or just a mathematical trick. But then came a young patent clerk with a fondness for trains and thought experiments, Albert Einstein. Yes, that Einstein. He took Planck's idea and ran with it. In 1905, he proposed something radical. Light doesn't just act like it's made of particles, it is made of particles. He called these particles light quanta, though we now know them as photons. Tiny, indivisible packets of light energy traveling through space not as a smooth wave, but as discrete pulses. Einstein wasn't just speculating for fun, he was trying to solve another physics puzzle, the photoelectric effect. This is what happens when light shines on certain metals and causes them to release electrons. According to the wave theory of light, increasing the brightness should eventually knock electrons loose no matter the color. But that's not what scientists observed. Instead, low-frequency light, no matter how intense, failed to eject any electrons. Meanwhile, high-frequency light, even if dim, did the trick immediately. Einstein's photon theory explained it beautifully. Each photon carries a specific amount of energy, and only photons with enough energy can liberate an electron. Brightness didn't matter. Frequency did. For this elegant solution, Einstein was awarded the Nobel Prize in Physics. Not for relativity, mind you, but for figuring out that light, the wave, was also a particle, or at least something that behaved like one. With Planck and Einstein leading the way, physicists were forced to accept a strange new reality. Energy was quantized, light came in packets, the universe at its most fundamental level had a grainy texture. The dream of a smooth, continuous world was beginning to crumble. But things only got weirder from there. As experiments grew more precise, light continued to confound expectations. It still produced interference patterns, a hallmark of waves. Shine light through two slits, and you still get the familiar bands of brightness and darkness that suggest overlapping wavefronts. But send photons through those slits one at a time, and you still get interference. It's as if each photon is interfering with itself, as though it travels through both slits at once, like a ghost unsure of its path. This behavior gave rise to one of the most baffling concepts in modern physics: wave-particle duality. Light, and later electrons and other particles, seem to exist in a strange limbo, sometimes acting like particles, sometimes like waves, and never committing fully to either until someone was watching. Not metaphorically watching, but measuring. Observation, it turned out, changed everything.
This duality wasn't just philosophical, it was demonstrable and deeply unsettling. In a universe governed by classical laws, particles and waves are distinct entities. But quantum theory tossed that clean division out the window. Suddenly, particles could spread out like waves. Waves could collapse into particles. Certainty was replaced with probability. The universe no longer ticked like a predictable clock. It shimmered with ambiguity. Even light speed became part of the enigma. It always travels at the same speed in a vacuum, about 299,792 kilometers per second, no matter your frame of reference. This constancy, which underpins Einstein's theory of relativity, is beautiful but bizarre. It means that the faster you move, the more space and time bend to keep the speed of light unchanged. The more you learn about light, the more it seems to be nature's ultimate shapeshifter. And all of this, the photons, the quanta, the duality, emerged from experiments with glowing filaments, shining metals, and radiation that didn't quite behave. The tiniest nudges in experimental results cracked open the door to a deeper reality, one where the classical rules no longer applied. Physicists weren't just discovering new facts, they were uncovering a new framework. Quantum theory was still in its early days, but the implications were already staggering. It wasn't just light that behaved this way. Electrons, protons, entire atoms, all were found to follow the same fuzzy logic. The universe at its smallest scale was built on uncertainties, probabilities, and strange patterns that defied classical intuition. But it all began with light, with the glow of heated metals, the flicker of photons, and the peculiar realization that the most familiar thing in the world might also be the strangest. Light, once thought to be a simple wave, turned out to be a quantum creature, both wave and particle, neither fully one nor the other, depending on how you asked. And in embracing that weirdness, physics found a new language, one that would go on to explain everything from atomic structure to the birth of stars to the nature of information itself. All because light decided it didn't want to be just one thing. It wanted to be both. In the early decades of the 20th century, the atom had become a rather confusing place. Electrons had been discovered, the nucleus had been mapped out, and thanks to Rutherford's gold foil experiment, we knew the atom was mostly empty space. But no one could quite explain how everything fit together. Classical physics insisted that electrons orbiting a nucleus should spiral inward and crash, like doomed satellites. And yet, atoms miraculously stayed whole. The universe, thankfully, was not spontaneously collapsing into itself. That was the puzzle facing a young Danish physicist named Niels Bohr. He had a soft-spoken manner, a gentle wit, and a mind that delighted in paradoxes. Bohr was the kind of person who could ponder contradictions over coffee and then calmly rewrite the rules of atomic structure between sips. While working with Rutherford in Manchester, Bohr became obsessed with one particularly mysterious clue: the strange and beautiful patterns of light given off by atoms.
If you pass an electric current through hydrogen gas, for instance, it doesn't glow with a smooth rainbow of colors. Instead, it emits light at very specific wavelengths, distinct lines of red, blue-green, and violet. These aren't smudges, they're razor-sharp frequencies, like musical notes played by an invisible instrument. Each element has its own unique spectral fingerprint, a barcode of light that tells you exactly what kind of atom you're looking at. This phenomenon had been known for decades, but no one could explain why it happened. Why would atoms, when excited, emit only certain colors and not others? What was determining the structure of this atomic song? Bohr had an idea, one that would blend classical mechanics, new quantum ideas, and a dash of creative audacity. He proposed that electrons didn't orbit the nucleus at just any distance. Instead, they occupied specific energy levels, what he called quantized orbits. Only certain orbits were allowed, like the rungs on a ladder. An electron couldn't just hover between them. It could jump from one level to another, sure, but only by absorbing or emitting a specific amount of energy, usually in the form of light. If this sounds familiar, it's because Bohr was taking a cue from Planck and Einstein's quantum work. Just as light came in packets, Bohr suggested that an electron's energy did too. Each orbit corresponded to a specific energy level. When an electron dropped from a higher orbit to a lower one, it released a photon with energy equal to the difference between those levels. That photon had a very specific frequency, hence the sharp spectral lines. Bohr's model made a stunning prediction, the exact wavelengths of hydrogen's spectral lines. Using his equations, he calculated the frequencies of the emitted light, and they matched the experimental data perfectly. The theory didn't just explain what was happening, it predicted it. Suddenly, the atomic spectrum wasn't a mystery, it was a roadmap. Bohr's model brought order and logic to a realm that had been stubbornly weird. The atom wasn't a random jumble of parts. It had structure, rhythm, and hierarchy. Electrons weren't whizzing around chaotically, they were dancing in defined patterns, leaping between levels like acrobats. There was a certain elegance to the whole thing, a symmetry that physicists found deeply satisfying. Bohr had taken the unruly quantum behavior of particles and turned it into a model that could be visualized, calculated, and taught. His atom looked like a tiny solar system, with electrons orbiting a nucleus much like planets around the sun, except with hard boundaries and sudden jumps.
Of course, there were caveats. Bohr's model worked beautifully for hydrogen, the simplest atom with only one electron, but began to fall apart with more complex atoms. It couldn't fully explain why electrons didn't radiate energy while orbiting or why their paths didn't slowly decay. And it didn't incorporate the full weirdness of quantum mechanics, like wave-particle duality or Heisenberg's uncertainty principle. But at the time, it was a massive leap forward. Bohr's model gave physicists a bridge between classical intuition and quantum reality. It wasn't the final answer, but it was a functional map, a guide through the haze. It showed that energy in atoms was quantized, not continuous. It explained spectral lines, and it hinted at the deeper structure of matter, where motion and energy weren't just analog values, but came in steps. And let's be honest, it was also just incredibly satisfying. There's something deeply appealing about electrons zipping around in clean orbits, dropping photons like breadcrumbs as they descend. It turned the chaotic image of the atom into something almost musical, with discrete notes and harmonic rules. Bohr's contribution didn't stop with the atom. He would go on to be a towering figure in the development of quantum theory, helping lay the philosophical groundwork for how scientists interpret the bizarre behavior of the subatomic world. He was a mentor to many, including Heisenberg, and often found himself at the center of debates about what quantum mechanics really meant. One of Bohr's most famous sayings is,
Anyone who is not shocked by quantum theory has not understood it. He believed in the strange, not as an exception, but as a foundation. And yet, his own model, the neat planetary atom, was perhaps his most grounded and intuitive contribution. It gave people a way to see the invisible. It's also a reminder that in science, progress often comes in layers. Each model brings us closer to the truth, but none is the final word. Bohr's atom would eventually be refined and replaced by more accurate quantum mechanical models, where electrons aren't points in orbit, but clouds of probability. Still, the Bohr model remains a crucial milestone, a moment when imagination, mathematics, and experiment lined up just long enough to illuminate the atom's inner architecture. It's fitting that light played such a central role in this story. Bohr used light to understand atoms, and atoms, in turn, use light to speak their secrets. Every spectral line is a whisper from an electron, telling us where it has been and what it left behind. And thanks to Bohr, we know how to listen. In classrooms around the world, students still draw Bohr's atom, circles for orbits, dots for electrons, knowing that it's a simplified picture, but a powerful one. Because sometimes, even in the complex landscape of quantum physics, a simple sketch can point the way to a deeper truth. And sometimes, the universe really does behave like a planetarium full of particles, leaping through space and singing in light. By the mid-1920s, physicists were starting to feel a bit seasick. The classical world of predictable laws and tidy trajectories was steadily being replaced by something far stranger. Atoms were no longer miniature solar systems with electrons neatly orbiting their nuclei. Instead, the deeper scientists looked, the more it seemed that reality itself was fuzzy, fluid, and oddly non-committal. Enter Werner Heisenberg, a brilliant young German physicist with a sharp mind and a healthy skepticism for things that couldn't be measured. He was the kind of person who found comfort in equations, not metaphors, and preferred mathematical clarity over philosophical hand-waving. But even Heisenberg, the logical pragmatist, would soon find himself confronting one of the strangest and most unsettling truths in modern physics. Heisenberg was trying to understand the behavior of electrons, not just where they were, but how they moved. Classical physics told him that, in principle, you could know both an object's position and its velocity with perfect precision. After all, that's how we navigate the world. If you know where a car is and how fast it's going, you can predict where it will be a few seconds later. Easy. But atoms, as it turned out, weren't interested in being easy. As Heisenberg worked through the math of quantum mechanics, he realized something astonishing. The more precisely you tried to measure an electron's position, the less precisely you could know its momentum, its speed and direction, and vice versa. This wasn't due to faulty instruments or human error. It was a fundamental property of nature. Heisenberg's uncertainty principle was born. Formally, it states that the product of the uncertainty in position and the uncertainty in momentum is always greater than or equal to a very small number, Planck's constant divided by 4 pi. In plain English, you cannot know both where a particle is and how fast it's going with perfect accuracy at the same time. The universe won't let you. This wasn't just weird, it was revolutionary. It meant that the behavior of particles at the quantum level couldn't be described with classical certainty. You couldn't draw a neat little diagram of an electron zipping around a nucleus. Instead, you had to talk in terms of probabilities, likelihoods of finding an electron somewhere within a cloud of possibilities. In a way, it was like trying to track a buzzing mosquito in a dark room with a flashlight. The moment you shine the light to see where it is, you've already disturbed it. Your act of observing changes its behavior. The better your flashlight, the more disruptive your search becomes. For Heisenberg, this wasn't just a quirky footnote, it was a fundamental shift in how we think about reality. Classical mechanics had taught us that the universe was like a clock. Complex, yes, but ultimately predictable. Quantum mechanics said no. The universe was more like a jazz performance, structured but improvisational, governed by rules but always dancing around uncertainty.
Some physicists found this deeply unsettling. Einstein famously wasn't a fan. God does not play dice with the universe, he declared. He couldn't accept a theory that seemed to abandon cause and effect in favor of probabilities. But Heisenberg and others held their ground. It wasn't about God playing dice. It was about acknowledging that nature, at its core, plays by rules we're still learning to understand. And in this new world of uncertainty, measurement itself became a delicate art. To study atoms, you couldn't just poke them and see what happened. You had to use inference, mathematics, and a healthy respect for the fact that your tools were part of the system. The observer was no longer separate from the observed. This idea gave rise to a new kind of physics, one where wave functions described particles not as objects in space, but as clouds of probability. An electron wasn't here or there, it was likely to be in one place, less likely to be in another, and virtually impossible to pin down with absolute certainty. Only when you made a measurement, when you actually looked, did the wave function collapse and reveal a single outcome. And even then, that outcome is just one possibility among many. It's a bit like flipping a coin and only finding out whether it landed heads or tails once you lift the cup. Until that moment, it exists in a kind of superposition, not both, not neither, but something stranger. Heisenberg's principle didn't just apply to electrons, it applied to everything. In theory, it applies to you, me, your coffee cup, and your socks. It's just that for big objects, the uncertainties are too small to notice. You can know both the position and speed of a baseball pretty accurately. But for tiny particles, electrons, photons, and their subatomic friends, the uncertainties dominate. This realization didn't break physics, it expanded it. It forced scientists to think differently, to abandon the old metaphors and embrace the math. It gave rise to quantum mechanics, a theory that would go on to explain semiconductors, lasers, superconductors, and more. It opened the door to quantum computing, where particles can hold multiple states at once, and to quantum encryption, where information can be fundamentally protected by the laws of physics. But perhaps more than anything, Heisenberg's uncertainty principle taught us humility. It reminded us that even the most precise instruments and the most brilliant minds have limits, not because we're not clever enough, but because the universe is built that way. At the smallest scales, reality isn't about knowing, it's about predicting probabilities and accepting the dance of chance. And yet, from that uncertainty comes structure. Atoms form stable configurations. Molecules behave predictably. Stars burn with reliable light. Somehow, out of this quantum blur emerges the solidity of the world we live in. It's a paradox that still stirs the minds of physicists, that certainty, order, and beauty can arise from a foundation that is fundamentally uncertain. Heisenberg himself understood this deeply. He didn't see the uncertainty principle as a flaw, but as a revelation. It didn't make nature less real. It made it more alive. The atom was no longer a simple machine. It was a dynamic, ever-shifting expression of probability, energy, and possibility. And with that insight, the way we measured atoms and thought about them changed forever. From sharp lines to soft clouds, from precision to probability, the journey into the atom had taken us to a place where being unsure wasn't a weakness, but a new kind of understanding, a recognition that even in the deepest parts of matter, a little uncertainty can go a very long way.
In the misty world of quantum mechanics, where particles behave like waves and certainty slips through your fingers like smoke, came a man with a head full of equations and an idea that involved a very unfortunate cat. His name was Erwin Schrödinger, and he was about to give quantum physics one of its most iconic images and one of its most powerful mathematical tools. Let's start with the equation. Schrödinger's equation is, to put it simply, the heart of quantum mechanics. It does for subatomic particles what Newton's laws did for falling apples and swinging pendulums. It tells you how a quantum system evolves over time, how its state changes, how its energy behaves, and how its probabilities shift. But instead of tracking the motion of solid objects, it describes something much more subtle: the wave function. The wave function is not a wave in the traditional splashy surf sense. You can't surf on it or see it ripple across a pond. It's a mathematical expression that encodes everything we can possibly know about a quantum system: where a particle might be, how fast it might be moving, what energy it might have. All of these are wrapped up in a single complex value function. It's like a map, but one made entirely of potential outcomes. When you square the wave function, you get a probability distribution, a sort of heat map of where the particle is likely to be found. This is not because the particle is hiding somewhere and we just don't know where. According to the quantum worldview, it genuinely does not have a definite position until it's measured. Until that moment, it exists in a superposition, a smeared out state of possibilities. Schrödinger wasn't just trying to come up with abstract math. He wanted a visual, intuitive way to understand how particles behaved at the quantum level. Building on the ideas of de Broglie, who had suggested that particles could behave like waves, Schrödinger proposed that if electrons had wave-like properties, perhaps their behavior could be modeled using a wave equation. That wave would represent the electron's probability cloud, not its physical path. He formulated his equation in 1926, and it quickly became one of the cornerstones of modern physics. With it, scientists could predict the allowed energy levels of electrons in atoms, the shapes of atomic orbitals, and the behavior of subatomic particles with startling accuracy. The Bohr model of the atom had shown where electrons could be. Schrödinger's model showed why they were there and how they moved within their allowed energy levels. Instead of neat planetary orbits, the electron became a fog of probability, hovering in shell-like regions around the nucleus. Each orbital wasn't a path, it was a zone of likelihood. And this wasn't just a clever metaphor. These shapes could be calculated, visualized, and tested against experimental data. The quantum cloud was real, even as it was invisible. But quantum mechanics never likes to leave things too tidy. As Schrödinger worked with his wave function, he began to wrestle with a growing discomfort. While his equation worked brilliantly, its implications were strange, even disturbing. According to the prevailing interpretation at the time, the wave function doesn't just describe potential outcomes, it is the system, right up until a measurement is made. Measurement collapses the wave function into a single outcome. Before that, the system exists in a liminal state of overlapping possibilities. This is where Schrödinger's cat entered the story. In an effort to highlight what he saw as a paradox, or perhaps even a flaw in the prevailing view, Schrödinger proposed a now famous thought experiment. Imagine placing a cat in a sealed box. Inside the box is a vial of poison, a tiny bit of radioactive material, and a Geiger counter. If the radioactive atom decays, the Geiger counter detects it and breaks the vial, releasing the poison and ending the cat's career in one rather dramatic moment. If the atom does not decay, the cat stays alive. Now here's the twist. Radioactive decay is a quantum event. It's governed by probability. According to quantum mechanics, until someone opens the box and checks, the atom exists in a superposition of decayed and not decayed. And if the atom is in superposition, so is the mechanism, the poison vial, and yes, the cat. That means, in theory, the cat is both alive and dead at the same time.
not in a ghostly way, but in a real physical superposition. Only when someone observes the system by opening the box does the wave function collapse into one outcome or the other. Schrödinger didn't propose this to support the theory, he was horrified by it. He intended the cat scenario to be absurd, a kind of wake-up call to show just how weird and troubling the implications of quantum theory could be when extended to everyday objects. After all, nobody actually sees half-alive, half-dead cats wandering around. Reality seems to choose an outcome even when nobody's looking. But instead of killing the theory, Schrödinger's cat became its mascot. Physicists embraced the paradox, debated it, and built entire schools of interpretation around it. Some believe that observation really does collapse the wave function. Others propose that all outcomes actually happen, just in separate branching universes. In one world, the cat lives, in another, it doesn't. This became the foundation of the many worlds interpretation. Still others tried to build more deterministic models or hidden variable theories in an attempt to restore a sense of classical order. But no matter the interpretation, the math stayed the same. Schrödinger's equation continued to work, guiding quantum mechanics through decades of breakthroughs, inventions, and philosophical debates. It's worth noting that Schrödinger himself wasn't just a one-hit wonder. He contributed to a wide range of topics in physics and biology, and he remained a thoughtful, sometimes restless voice in scientific philosophy. His cat may have become the most famous quantum feline in history, but his wave equation was the true legacy. It gave scientists a powerful tool to predict how particles behave, how atoms form bonds, and how matter holds itself together. At its heart, Schrödinger's work revealed that particles, like electrons, are not dots moving along a line, but clouds of possibility. They can interfere with themselves, tunnel through barriers, and defy the logic of classical motion. They are not here or there, they are somewhere in a statistical sense, until we ask the question directly. And once we ask, the universe answers, but only with one outcome. In the quantum world, reality is not fixed in advance. It unfolds moment by moment, shaped by interaction, observation, and chance. Schrödinger's wave function didn't just describe atoms, it rewrote our understanding of what it means to exist. So whether you picture the atom as a cloud, a blur, a probability field, or a purring feline in a box of quantum doom, know this: the world beneath the surface is richer, stranger, and far more delicate than it appears. And every time we open a box, literal or mathematical, we're not just observing the universe, we're participating in its unfolding. By the time physicists had gotten comfortable with electrons as clouds of probability and cats as thought experiments, the atom was already whispering a new secret. There were still more layers hiding beneath the surface. The once simple building blocks of matter, once thought to be indivisible, had become dense hubs of complexity. It was like discovering that your neatly arranged desk drawer actually contained another drawer inside it, and inside that, a whole colony of mysterious gadgets chatting in code. The story of the atom was evolving again. Quantum mechanics had explained a great deal, and Schrödinger's wave functions were doing an excellent job at describing how electrons behaved in atoms, but the forces that held the atomic nucleus together, those were still a little opaque. Protons, after all, are all positively charged. According to the laws of electromagnetism, they should repel one another violently. It would be like trying to keep a pile of north-pointing magnets crammed into a tiny space. Nature doesn't usually allow that kind of party. And yet, there they were, snuggled together in the nucleus, not flying apart. Clearly, there had to be something else at play, some stronger glue, some force more powerful than the electromagnetic one. Enter the strong nuclear force. It's the mightiest of the four fundamental forces of nature, but also the most elusive. Unlike gravity or electromagnetism, which act over long distances, the strong force only works at incredibly short ranges, about the width of a proton. But within that minuscule range, it dominates. It binds protons and neutrons together in the nucleus and refuses to let them drift apart. To understand how this force operates, physicists needed a new framework, one that went beyond particles as points and imagined them instead as ripples in underlying fields. This was the birth of quantum field theory. Quantum field theory, or QFT for short, is where things really start to feel like a blend of physics and poetry. Instead of treating particles as tiny objects that move through space, QFT says that every type of particle is actually an excitation, a little ripple or vibration in a field that fills all of space. Electrons are ripples in the electron field, photons are ripples in the electromagnetic field. Everything is fields all the way down. This shift in perspective wasn't just a philosophical tweak. It changed how physicists calculated interactions. Fields can create and annihilate particles. They can overlap and interfere. And within this field-based reality, strange new possibilities emerged. Particles that appear and vanish, momentarily borrowed from the vacuum itself. These are known as virtual particles, and they play a crucial role in how forces are transmitted. Imagine two particles interacting, say two electrons repelling each other. In QFT, this isn't because they directly push on each other like billiard balls. Instead, one electron emits a virtual photon, a messenger particle that zips over to the other electron, delivering the message, "Hey, scoot." The photon is virtual because it exists for a brief moment, just long enough to mediate the force and then disappears. The same logic applies to the strong force, except instead of photons, the messengers are called gluons. Yes, gluons. The name is delightfully literal. Gluons are the particles that carry the strong force, binding quarks together inside protons and neutrons. And yes, quarks. Because it turns out that even protons and neutrons, those supposedly elementary particles, aren't elementary at all. They're made of even smaller particles.
Each proton or neutron is composed of three quarks, held together by the relentless grip of gluons. These quarks come in flavors: up, down, strange, charm, top, and bottom. And for some reason known only to the whimsical minds of physicists, these are the official terms. A proton contains two up quarks and one down quark. A neutron has one up and two down quarks. The gluons that bind them don't just stick them together like cosmic glue, they also constantly swap between the quarks, changing their color charge, a quantum property that has nothing to do with actual colors, but helps keep track of how the strong interaction behaves. The result is a chaotic, jittery ballet of particles exchanging force-carrying messengers at blistering speed, all confined within a space smaller than a single atom. The sheer strength of the strong force is staggering. It's about 100 times stronger than the electromagnetic force and 10,000 times stronger than the weak nuclear force. But it's picky. Outside the atomic nucleus, its influence drops off to nearly zero. It's like a bodybuilder who refuses to lift anything outside his own kitchen. But the strong force isn't the only game in town. Alongside it, physicists discovered a whole zoo of particles: muons, pions, kaons, neutrinos, and more. Some were stable, many were fleeting, and all were pieces of the same quantum puzzle. This expanding collection became known as the particle zoo, and for a while it was more chaotic than enlightening. It was as if nature had opened her handbag and dumped out a tangled collection of subatomic receipts, keys, and loose change. The breakthrough came with the development of the Standard Model, a theoretical framework that organized these particles into categories and explained how they interacted. According to the Standard Model, all matter is made of a small set of fundamental particles: quarks, leptons, like the electron, and force carriers, like photons and gluons. Everything else, atoms, molecules, cats, galaxies, is just combinations of these tiny bits. It's hard to overstate how successful the Standard Model has been. It explains nearly all known particle interactions with incredible precision. It predicted the existence of particles long before they were discovered, and in 2012, it was crowned with the discovery of the Higgs boson, the particle associated with the Higgs field, which gives mass to other particles. But even with its successes, the Standard Model isn't the final story. It doesn't explain gravity. It doesn't tell us why the fundamental constants have the values they do. It doesn't account for dark matter or dark energy, which seem to make up most of the universe. In many ways, it's a map of familiar territory with big question marks just beyond the edges. Still, what the Standard Model and quantum field theory have taught us is nothing short of astonishing. That particles are just ripples in fields, that forces are carried by particles flickering in and out of existence, that protons, once thought indivisible, are seething bundles of smaller entities held together by the strongest force known to science. Atoms, it turns out, are not simple at all. They are symphonies of fields, dances of probabilities, and collisions of energy and structure. They are galaxies of motion in miniature, held together not by static bonds, but by constant humming activity. Even in the calmest piece of matter, say the end of your nose, there are trillions upon trillions of gluons flitting between quarks, virtual particles bubbling in and out of reality, and fields humming beneath it all. What began as a search for the smallest pieces has led to a layered, dynamic universe. A universe where the deeper you look, the less things look like things and more like interactions, energies, and patterns that never quite sit still. The zoo is strange. The forces are hidden. The fields are everywhere. And yet, from all this invisible chaos comes the tangible world: tables, trees, stars, you. A universe built from whispers and wiggles, held together by rules we are only just beginning to understand. By the early 20th century, scientists had taken the atom apart in theory, teased out its pieces with equations, and mapped out the strange forces that held it all together. But there was still one thing they hadn't done: crack the atom open and see what came flying out. That would soon change. It turns out that atoms, those tiny bundles of organized chaos, are also stores of extraordinary energy. Not energy in the warm and cozy, light a candle sort of way, but energy capable of reshaping landscapes, lighting cities, or leveling them. Nuclear physics would bring about some of humanity's greatest advances and its darkest moments, all thanks to what happens when you split or fuse the very heart of matter. Let's start with the split: nuclear fission. Fission is what happens when the nucleus of an atom, typically a heavy one like uranium or plutonium, becomes unstable and breaks apart into smaller nuclei. When this happens, a tremendous amount of energy is released, along with a few loose neutrons. These neutrons can then strike other atoms, causing more fission, releasing more energy and more neutrons in turn. This chain reaction can unfold in the blink of an eye or be carefully controlled. The key here is that the mass of the resulting particles after fission is slightly less than the mass of the original atom. That lost mass hasn't vanished. It's been converted into energy, as predicted by Einstein's famous equation E equals mc squared. Since c, the speed of light, is a very large number, even a tiny amount of mass can produce a staggering amount of energy. The first experimental demonstration of fission came in 1938 when German scientists Otto Hahn and Fritz Strassmann bombarded uranium with neutrons and noticed unexpected byproducts. Physicists Lisa Meitner and Otto Frisch quickly realized that the uranium nucleus was splitting, fissioning, into smaller elements, and they calculated the massive energy released in the process. It was a groundbreaking moment. They hadn't just discovered a new kind of reaction, they'd stumbled upon a new kind of power. Suddenly, the atom was no longer just a conceptual playground for theorists. It was a battery, a grenade, a sun in miniature. As the Second World War loomed, The implications of fission were obvious and terrifying. If you could build a device that triggered a sustained chain reaction, you could unleash unimaginable destruction. That race led to the Manhattan Project, a secret Allied effort to build an atomic bomb before Nazi Germany could. It brought together some of the greatest minds in science, including Oppenheimer, Fermi, Szilard, and many others, working in remote laboratories under intense secrecy. In 1945, the world saw the results. Two bombs, nicknamed Little Boy and Fat Man, were dropped on the Japanese cities of Hiroshima and Nagasaki. They killed over 100,000 people instantly, with many more dying in the aftermath. Entire neighborhoods were flattened in seconds, their energy released not from fire or gas, but from the splitting of atoms. It was power on a scale that humanity had never known before, and a warning etched in ash and silence. The use of atomic bombs brought an end to the war, but also a deep moral and philosophical reckoning. What had once been a symbol of pure scientific curiosity, the quest to understand the atom, had become a weapon of mass destruction. The paradox of nuclear physics was born. The same discoveries that offered limitless energy also threatened total annihilation. But even in the shadow of destruction, the pursuit of nuclear knowledge continued. Scientists and engineers turned their attention to peaceful applications of fission, particularly in generating electricity. In a nuclear power plant, the chain reaction is carefully controlled using moderators and control rods that absorb excess neutrons. Instead of releasing the energy all at once, as in a bomb, the process is slowed to a steady simmer. The heat produced by fission boils water, which turns turbines, which generates electricity. Clean, efficient, and carbon-free, at least in terms of emissions.
Of course, it's not without its downsides. Nuclear power plants produce radioactive waste that remains hazardous for thousands of years. Accidents, though rare, can be catastrophic, as seen in Chernobyl and Fukushima. And the line between civilian and military nuclear technology is razor thin. Still, for all its risks, nuclear power remains one of the most efficient ways to produce large amounts of electricity without burning fossil fuels. But fission is only half the nuclear story. Let's now talk about fusion, the process that powers the sun. Fusion is the opposite of fission. Instead of splitting heavy atoms apart, fusion involves forcing light atoms, like hydrogen, to combine into heavier ones, such as helium. This process also releases energy, and a lot of it. Fusion is what makes stars shine. In the sun's core, under intense heat and pressure, hydrogen nuclei collide and fuse, releasing the energy that bathes our planet in light and warmth. Scientists have long dreamed of replicating this process on Earth, and for good reason. Fusion fuel is abundant. Hydrogen is everywhere. It produces no long-lived radioactive waste. And unlike fission, there's no chain reaction runaway effect. Fusion is self-limiting. If something goes wrong, it simply stops. But there's a catch, a big one. Fusion requires temperatures of over 100 million degrees Celsius, hotter than the core of the sun. Containing something that hot is, well, tricky. You can't build a container out of metal or ceramic. Everything would melt. Instead, scientists use magnetic fields to suspend the hot plasma in mid-air inside devices called tokamaks and stellarators. These look like enormous futuristic donuts, humming with magnetic force and scientific ambition. Despite decades of effort, controlled fusion for power generation has remained tantalizingly out of reach. We've achieved fusion in the lab, short bursts, experimental pulses, but not yet in a way that produces more energy than it consumes. Still, progress continues, and international projects like ITER in France aim to crack the challenge in the coming decades. We have, however, achieved fusion in a more dramatic form, the hydrogen bomb. Unlike an atomic bomb, which uses fission, a hydrogen bomb uses a fission reaction to trigger a fusion reaction.
The result is an explosion hundreds or even thousands times more powerful than the bombs dropped on Japan. It's fusion weaponized. And it's why the Cold War was so terrifying, because once both superpowers had hydrogen bombs, mutual destruction became a very real possibility. And yet, nestled within all this danger is incredible promise. Nuclear physics has revolutionized medicine. Radioisotopes are used in imaging, diagnostics, and cancer treatment. Tracers help track chemical pathways in the body. Radiation therapy targets tumors with pinpoint precision. The very forces that can destroy cities are also saving lives in hospitals around the world. In geology and archaeology, radiometric dating allows us to measure the ages of rocks, fossils, and ancient artifacts with astonishing accuracy. In industry, radiation is used to sterilize equipment, scan welds, and improve crop varieties. The benefits ripple far beyond power plants and physics labs. Still, the paradox remains. Nuclear physics is a field of astonishing elegance and terrifying potential. It reveals the universe's deepest secrets and reminds us that knowledge is never neutral. With each breakthrough, we are faced with choices: how to use what we've learned, and whether our wisdom can keep pace with our power. We split atoms to understand the world, and in doing so, gave ourselves the power to destroy it or to sustain it, depending on which direction we choose. Nuclear physics asks hard questions, not just about nature, but about ourselves. What kind of species splits the atom and wonders what to do next? What kind of mind unlocks the forces of the sun and then builds both bombs and hospitals with it? We're still learning how to live with that power, still learning how to balance curiosity and caution, ambition and restraint. But one thing is certain: once we opened the atom, we could never close it again. In every reactor core, in every medical isotope, in every fusion experiment striving to light our future, the heart of the atom continues to burn. And we, the curious apes who dared to look inside, must decide how that fire is tended. Not so long ago, atoms were whispered about in dusty lecture halls and scribbled into the margins of notebooks by curious minds who dared to imagine the invisible. They were theoretical constructs, abstract ideas, philosophical guesses wrapped in Greek robes or sketched out by chalk-stained hands. But today, atoms are no longer just imagined. They're engineered, manipulated, coaxed, prodded, and read like an open book. In a strange twist of history, the tiniest building blocks of the universe now sit at the heart of some of our most advanced technologies. The atom, once elusive, is now a familiar tool in the modern scientist's kit, and the world built around you hums with its influence. Take a deep breath, stretch your arms, and look around your room. Somewhere nearby, likely within reach, there's a device that depends on semiconductors: your phone, your laptop, your tablet, your microwave. Semiconductors are the reason modern electronics exist. And semiconductors are only possible because we've come to understand atoms not as solid billiard balls, but as quantum objects whose behavior is delicately shaped by energy levels and electron configurations. Silicon is the most famous of these materials, thanks to its unique ability to conduct electricity only under certain conditions. Engineers learned how to dope silicon, introducing tiny amounts of other elements like phosphorus or boron to tweak its electronic properties. This is not casual chemistry. It's the careful crafting of atomic neighborhoods. Entire cities of transistors are etched into slivers of silicon so small they make a grain of rice look like a skyscraper. And each transistor is a tiny gate flipping between states, guiding the flow of electrons that power everything from streaming music to landing spacecraft. All of it is possible because we've learned how atoms behave when packed together, how electrons jump between energy bands, how atomic scale impurities can alter conductivity in profound ways. We didn't just imagine the atom, we learned how to program it. The marvels don't stop with phones and laptops. Step into a hospital and you'll find another world of atomic wonder quietly at work. Magnetic resonance imaging, MRI, relies on the magnetic properties of atoms in your body, particularly hydrogen. Your body is mostly water, and water is full of hydrogen. When you lie inside an MRI machine, a powerful magnetic field lines up the tiny magnetic fields of the hydrogen nuclei, like compass needles. Then a burst of radio waves flips them. As the nuclei relax back into alignment, they release signals that are picked up and turned into incredibly detailed images of your soft tissues. It's not magic, it's nuclear physics. But don't worry, there's no radiation involved. The nuclear in MRI refers to the nuclei of atoms, not anything explosive. It's a stunning example of how knowledge of atomic spin and energy states has been harnessed not for destruction, but for diagnosis. And speaking of medicine, atoms have taken on yet another role as messengers and healers. In nuclear medicine, radioactive isotopes are used to trace the pathways of molecules in the body. Want to know how fast a tumor is growing or whether a patient's thyroid is overactive? Introduce a carefully chosen isotope, track its decay, and measure its signals with detectors. It's like sending in atomic reporters, each one whispering back vital information before fading into the background. In some cases, these isotopes aren't just observers, they're also treatment. Radioactive iodine, for example, is used to destroy overactive thyroid tissue. Other therapies target cancer cells with beams of radiation or implant radioactive seeds directly into tumors. The energy locked in the nucleus, once feared for its destructive power, is now a precision instrument in the fight to preserve life. But perhaps the most thrilling frontier in our relationship with atoms is how we're starting to build with them. Literally. Welcome to the world of nanotechnology. Nanotechnology operates at the scale of nanometers, a billionth of a meter. That's roughly the width of a few atoms placed side by side. At this scale, matter doesn't behave the way you'd expect. Gold, for instance, turns red or purple. Carbon can be transformed into tubes stronger than steel or sheets more conductive than copper. Forces that are negligible in the macroscopic world, like van der Waals interactions or surface tension, become dominant. Gravity, by comparison, almost disappears. Researchers are designing drugs that can seek out specific cells, materials that repair themselves, and fabrics that repel stains, not through chemistry, but through nanoscopic surface structures. In laboratories around the world, engineers are manipulating individual atoms using tools like scanning tunneling microscopes, which let you feel the surface of a material one atom at a time. It's craftsmanship at the scale of molecules. And while nanotech continues to develop, the horizon is already widening further into quantum computing. Traditional computers work in binary. Everything is either a 1 or a 0, on or off. But quantum computers, built on the rules of quantum mechanics, use qubits, quantum bits that can exist in multiple states at once, thanks to superposition. A qubit isn't just 1 or 0, it's both, until measured. Even more powerful is entanglement, a bizarre phenomenon in which qubits become linked so that the state of one instantly influences the state of another, no matter how far apart they are. This opens the door to computations that are staggeringly fast, solving problems that would take classical computers longer than the age of the universe to finish. And what are these qubits made of? Sometimes trapped ions, sometimes superconducting circuits, sometimes photons. Always atoms, or the quantum fields that govern them. The smallest units of the universe marshaled into a new kind of thinking machine. Quantum computers are still in their infancy. They're delicate, error-prone, and famously finicky, but they represent a new way of engaging with the atom, not as a particle or a wave, not even as a metaphor, but as a computational tool. We're not just observing quantum weirdness, we're beginning to use it. In all of this, atoms are no longer the end point of inquiry. They're not just the fundamental building blocks we hope to find at the bottom of everything. They're platforms, gateways, dynamic participants in technologies we're still learning to invent. Our understanding of them has moved beyond what they are and into what they can do. We now think in terms of probability clouds, tunneling effects, quantum coherence, and spin states. Atoms are not just objects, they're possibilities. They're invitations to think differently about matter, energy, and information. They are little puzzles we can shape, tools we can wield, and canvases we can paint with forces invisible to the eye.
Even in areas like agriculture and food preservation, atomic techniques are quietly at work. Radiation can sterilize medical equipment, kill bacteria in food, and even help trigger genetic changes in crops to boost yield and resilience. In archaeology, carbon dating based on radioactive decay lets us look into the past with unprecedented clarity. And in space exploration, atomic clocks using the oscillations of cesium or rubidium atoms allow for navigation so precise that your GPS knows if you took a wrong turn at the coffee shop. Those same atomic principles make up the beating heart of interplanetary probes, guiding them through the silent void with exquisite accuracy. So, here we are, floating on a planet wrapped in technology that hums with atomic elegance. From the chips in our phones to the isotopes in our scans, from nanobots in the lab to the glimmering future of quantum processors, we live in a world built from the inside out, a world where atoms are no longer mysteries to unravel, but materials to sculpt. We've come a long way from Democritus and his invisible bits of matter drifting in the void. The atom has become both more real and more abstract, more solid and more slippery. It's not the end point of understanding, it's the entryway into a deeper, more powerful, and often stranger engagement with the universe. We've learned to listen to atoms, to speak their language, and to dream in their patterns. And now we're beginning to build our future with them, one quantum possibility at a time. After all our chapters, experiments, equations, explosions, and quiet revelations, we come full circle to the atom. That ancient idea, once imagined as a perfect, indivisible seed of matter. From the musings of Greek philosophers to the edge of quantum computing, the atom has remained both a cornerstone of our understanding and a bottomless well of mystery. We started with the word atomos, meaning uncuttable. But as it turns out, the atom is anything but solid and final. We cut it, and inside we found a nucleus. We cracked the nucleus and discovered protons and neutrons. We probed further and found quarks, gluons, fields, and fluctuations. And just when we thought we were at the bottom, the floor gave way again, revealing that even the very space between things hums with activity, virtual particles flashing into and out of being like fireflies in the dark. The atom is no longer a thing. It's a story, a pattern, a wave of possibilities dancing through time and space, a cloud of maybe shaped by probabilities and held together by forces we've learned to describe but not fully explain. What once seemed like the final word in matter has become the starting point for questions deeper and stranger than the minds of ancient philosophers could have ever dreamed. It is humbling, really. We used to picture atoms as little marbles, tiny, indestructible, perfect. Now we see them as smudges of likelihood, bits of energy, interactions between invisible fields. Even a single electron is no longer in a place, it's probably somewhere until you look. And even then, it's not so much there as it is a result of the act of asking. And yet, despite all this uncertainty, all this quantum ambiguity, the world holds together. Atoms form molecules. Molecules form cells. Cells build forests and cities and curious humans who sit quietly and wonder where it all came from. We are made of this same dust, this same energy, these same fields. You and the pillow beneath your head are woven from the same invisible threads. What a tender thought, really, that we are not merely in the universe, we are the universe in a very local, very sleepy form. The atom teaches us that the smallest things are not always simple, that what's invisible is not empty, that mystery is not a failure of understanding, but a quiet invitation to keep exploring. From ancient alchemists dreaming of hidden essences to modern scientists firing particles through vast underground tunnels, we've been asking the same questions over and over. What is this world made of? What holds it together? What's beneath the surface? And how deep does the rabbit hole go? Maybe that's the most beautiful part. The questions haven't changed, even as the answers have become richer, more complex, more delicate. We're still peering into the unknown, still brushing up against wonder, still learning to ask with both curiosity and care. And now, as the day slows and your breath softens, let the thought of the atom settle around you like a blanket. Know that every breath you take is a choreography of atoms, oxygen gliding through blood, carbon flowing from cell to cell, tiny messengers of matter doing their ancient work. You are made of the star's leftover pieces, fused in furnaces billions of years ago, scattered across galaxies, and gathered now in this quiet moment of rest. What a gentle, impossible thing to be composed of particles forged in the heart of exploding suns, and to lie here, listening, wondering, drifting. So, as your eyes grow heavier and your thoughts begin to wander, remember what we asked at the very beginning. What is this world made of? What strange secrets sleep beneath the surface of matter? And the answer, perhaps, is that the universe is made not of things, but of whispers, of vibrations, of fields, of dreams too small to see, but too essential to ignore. The universe is not a machine, it's a quiet song, and atoms are its notes. Sleep well, fellow traveler of the small and strange. May your dreams be full of hydrogen and stardust, uncertainty and wonder. And may you wake tomorrow still asking questions, still listening for the soft hum of the atom beneath everything. Good night from the Midnight Scientists.
Hello, and a soft welcome to the Midnight Scientists. If you have found your way to this quiet corner of the universe, you are likely seeking a gentle current to carry you away from the day. And what better way to drift than with a slow, calming dive into the silent, invisible world of chemistry? Tonight, we will not be dealing with loud reactions or jarring discoveries. Instead, we will journey into the quiet elegance of atoms bonding in the velvet dark, to the barely audible hum of molecules in their constant, gentle motion. Our exploration is about the invisible forces that shape everything you touch, taste, and tiptoe around in the stillness of your room. My voice will be your steady guide, and I will do my best to keep our path soothing and smooth. But I must offer a fair warning. The universe is a place of profound and gentle fascination. I hope this journey is not so interesting that it keeps you wide-eyed and alert. But if it does, well, at least you'll drift toward your dreams a little wiser than before. Before we begin our gentle descent into this molecular world, if you find comfort in this kind of calm, curious content, a gentle press of the like button or a quiet subscription would be truly appreciated. It helps this little sanctuary of science remain a cozy and peaceful place. And if you feel so inclined, feel free to share in the comments where in the world you're listening from and what time the clock shows for you right now. It is a quiet joy to see how far these sleepy science stories travel across the night. Now, settle in, let your body grow heavy, let your breath find its own slow, natural rhythm. Allow the thoughts of the day to become distant clouds floating gently away. Tonight, we are going to explore why things react, bond, or sometimes just sit there in perfect stillness, doing absolutely nothing at all. Oh, and while we will be touching upon the chemistry within our bodies and brains later on, please remember that nothing in this video is intended as medical advice. It is simply friendly, fact-checked bedtime science. Imagine holding something in your hand, anything at all, a smooth stone, a soft feather, perhaps even the cool weight of a silver spoon. Now, in your mind's eye, imagine dividing that object in half, and then in half again, and again, and again, until you couldn't possibly divide it any further. You would eventually arrive at something so fundamentally tiny that it ceases to be the object you started with. It becomes something else entirely, an atom. Atoms are the silent, ancient architects of all matter. Everything that surrounds you, the pillow beneath your head, the soft fabric of your blanket, the mug you sipped from hours ago, the very screen you might be looking at, is woven from these tiny particles. In fact, you are made of atoms. You are a walking, talking, and occasionally yawning constellation of organized stardust. And while the atoms themselves are impossibly small, the science that governs them is anything but. Let us begin at the very, very beginning, in the quiet heart of it all. An atom is composed of three main types of particles: protons, neutrons, and electrons. If an atom were a miniature solar system, the protons and neutrons would be huddled together at the center, a dense and steady sun, forming what we call the nucleus. The electrons, in turn, would be the speedy, distant planets zipping around the nucleus in regions we call orbitals. Though in truth, it's not quite like planets orbiting a star. In the strange and gentle world of the quantum, electrons behave more like soft clouds of possibility than precise moving dots. They exist in fuzzy, indistinct regions where they are likely to be, but we can never know exactly where they are at any given moment. They are elusive, quiet things, like a whisper you can't quite place. The nucleus, on the other hand, is dense and central. Protons carry a positive charge, neutrons carry no charge, and together they form the heavy, stable heart of the atom. It is the number of protons that defines what element an atom is. For instance, any atom with just one proton is always hydrogen. Any atom with 6 protons is always carbon. If you add or remove a proton, you are no longer dealing with the same element. It's a fundamental identity, a name tag assigned by the universe itself. Neutrons, while electrically neutral, serve a crucial purpose. They are the quiet diplomats of the nucleus. Without them, the positively charged protons would push each other apart with immense force. Neutrons act as a gentle buffer, a calming presence that glues the nucleus together in a state of peaceful stability. And then we have the electrons. These are the sprightly, nimble ones. They carry a negative charge and exist in various energy levels or shells around the nucleus. The farther an electron is from the nucleus, the more energy it holds, like a kite flying higher and higher in a gentle breeze. Electrons are the social messengers of the atomic world, constantly darting, shifting, and occasionally leaping to higher energy states when they absorb a bit of energy, perhaps from heat or light, before releasing it again as they fall back into a state of rest. But here is where the story becomes even more intriguing. Atoms are almost entirely empty space. If an atom's nucleus were the size of a single pea placed in the middle of a vast cathedral, the nearest electron would be a tiny speck of dust floating somewhere near the high ceiling. This means that everything you perceive as solid, your own body, the bed you are resting on, is composed of minuscule particles suspended in vast, silent voids of nothingness. Matter feels solid not because it's packed tightly with substance, but because of the invisible forces that hum between these particles. It's like standing in a room full of invisible, soft walls. You cannot see them, but you can feel where they begin and where they end. Each atom is incredibly small, about 1/10,000,000th of a meter across. To offer a sense of scale, a single grain of sand contains more atoms than there are stars in the known observable universe. And yet, every single one of those countless atoms plays by the same fundamental rules, following the same quiet choreography of attraction, repulsion, and bonding. When these atoms come together, they form molecules, which can then build just about everything: gases, liquids, solids, stars, and you. But even on its own, a single atom tells a fascinating story. Take helium with just 2 protons, 2 neutrons, and 2 electrons. It's light, unreactive, and a bit aloof. It prefers not to bond with other atoms, content to float solo, quite literally. Then you have oxygen, a far more social type, always looking to pair up, ready and willing to form bonds that are essential to nearly every breath you take. You could almost imagine these atoms at a quiet cosmic gathering. Helium would be off in a corner, perfectly content in its solitude, while oxygen and hydrogen are on the dance floor, gracefully combining to form water. Of course, not all atoms are stable. Some are radioactive, their nuclei a bit too heavy or unbalanced for their own good. They decay over time, gently breaking apart and releasing energy in the process. It's a slow, transformative end for something so tiny, and yet this process powers everything from the core of our planet to distant stars. Even instability has its own quiet role to play in this vast atomic drama. What is truly remarkable is how predictable and orderly all of this is. Through centuries of quiet observation and experimentation, we can now understand how atoms behave with incredible accuracy. We can map their configurations, predict their interactions, and even gently guide them to build entire new materials. It is the universe's ultimate blueprint, one that requires no instructions, just a deep and patient understanding of the rules. These atoms, with all their unique personalities, make up the periodic table, that beautifully ordered grid of elements. Each square represents a different kind of atom, a different character in the story of the universe. Some are gregarious and bond easily. Others are solitary and reserved. Some are heavy and slow. Others are light and reactive. The table is more than a scientific chart. It's a cast of characters for the fundamental play of existence. And though we have come to understand so much, atoms remain filled with a gentle wonder. They obey the strange, dreamlike rules of the quantum, where particles can exist in multiple states at once, and where the simple act of observing something can change its behavior. It is science at its most poetic and its most deeply perplexing. Atoms do not think or feel, of course. They have no awareness that we are speaking of them now. But if they did, perhaps they would be amused to know that these tiny, invisible bits of existence are the stars of the entire show. Quietly, invisibly, they shape everything, including the thoughts we are thinking, the dreams we are dreaming, and the very breaths we are taking right now. So here we are, nestled in a world built from countless tiny somethings, most of which is empty space, all dancing to laws they have followed for billions of years. And yet, somehow, in all that stillness and emptiness, life emerges, consciousness emerges, you emerge, and it all begins with the atom, the smallest something that makes up everything. Now that we've met the quiet, steady heart of the atom, let's turn our attention to its more energetic and unpredictable companions, the electrons. These tiny, zippy, wonderfully elusive particles are somehow responsible for nearly every chemical interaction you've ever witnessed. Electrons may be the lightweights of the atomic world, nearly 2,000 times less massive than a single proton, but what they lack in heft, they more than make up for in influence and energy. Electrons don't behave in ways we might intuitively expect. In fact, the deeper you drift into their world, the more strange and dreamlike things become. If protons and neutrons are the dependable, stoic guardians of the nucleus, electrons are more like fleeting thoughts or flashes of inspiration. They are constantly moving, impossible to pin down, and are the source of all the drama and connection in the chemical world. Let's begin with the basics. Electrons carry a negative electric charge, and they are drawn toward the positively charged protons in the nucleus, much like a night-flying moth is drawn to a soft, distant light. This gentle attraction is what keeps them from drifting off into the void, but it doesn't mean they settle down quietly. Electrons are in constant motion, and their behavior is best described not by a neat, predictable orbit, but by something far more ethereal, the probability cloud. In our everyday world, you can describe exactly where an object is and where it is going. But electrons belong to the quantum realm, where concepts like location and momentum are soft and hazy. Instead of a clear path, scientists describe an electron's presence as a fuzzy cloud of probability, a region where it is most likely to be found at any given moment. The denser the cloud, the higher the chance the electron is hovering in that spot. It's a bit like searching for a sleeping cat in a quiet house. You don't know its exact location, but based on past experience, you know it's probably curled up in a patch of moonlight by the window or nestled in the warmth of a soft blanket. These clouds, known as orbitals, come in different shapes and sizes. Some are simple spheres, some are shaped like dumbbells, and others possess even more intricate, beautiful forms. Orbitals are grouped together in layers called shells, which are arranged around the nucleus like the delicate layers of an onion. Each shell can hold a specific number of electrons. The first, innermost shell holds up to 2, the second holds up to 8, the third up to 18, and so on. Electrons, seeking stability, prefer to occupy the lowest available energy levels first, only moving to higher shells when the lower ones are full or when they absorb a little extra energy. And here is where the story of connection truly begins. An atom's desire to interact with the world depends almost entirely on its outermost electrons, also known as the valence electrons. These are the electrons in the atom's highest energy shell, and they are the ones that will reach out and interact with other atoms. If an atom's outer shell is completely full, it tends to be stable, serene, and unreactive. It is content, like someone who is already comfortably wrapped in a warm blanket with a soothing cup of tea. But if that outer shell is incomplete, the atom becomes restless. It starts looking for ways to gain, lose, or share electrons to find that state of contentment. And this is where all the bonding begins. Consider the noble gases, like helium or neon. Their outer shells are perfectly full. As a result, they barely interact with other atoms. They are the quiet introverts of the chemical world, perfectly happy in their own company. Then you have elements like sodium, which has just one lonely electron in its outer shell. That electron is loosely held, ready to find a new home, allowing the atom to achieve a more stable, complete inner shell. On the other side of the periodic table, you find chlorine, which is just one electron short of a full outer shell. It would love nothing more to welcome an extra one to complete its set. When sodium and chlorine meet, it is a perfect match. Sodium gracefully donates its extra electron to chlorine. In doing so, both atoms achieve the stability they were seeking. Together, they form sodium chloride, ordinary table salt. And just like that, a quiet connection is formed. This gentle drive for a full outer shell, often called the octet rule, is the primary motivation behind why atoms form bonds. They will do almost anything, share electrons, give them away, or accept them just to find that peaceful, stable configuration. Sometimes it's a fair and mutual sharing, as in covalent bonds, where atoms contribute electrons equally. Other times, it is more of a complete and graceful transfer, as in ionic bonds, where one atom gives up an electron entirely and another accepts it. Energy also plays a beautiful role in the life of an electron. When an atom absorbs energy from light or heat, its electrons can become excited. An excited electron absorbs this energy and makes a brief energetic leap to a higher shell, farther from the nucleus. It doesn't stay there for long, however. Electrons, like all things in nature, seek the lowest, most stable energy state. And so, before long, the excited electron will fall back to its original lower energy level. As it does, it releases that extra energy, often as a beautiful, tiny flash of light. Electrons are also the reason metals possess their characteristic shine and ability to conduct electricity. In a piece of metal, the outer electrons aren't tied to any single atom. Instead, they can move freely throughout the entire structure, forming a kind of communal cloud, a silent, flowing river of charge. These free-moving electrons reflect light, giving metals their beautiful luster, and they allow an electric current to flow smoothly through them. In the grand story of chemistry, electrons are the ultimate matchmakers, the quiet diplomats, and the gentle instigators of change. Their behavior determines whether atoms will bond, what kind of bond will form, how strong that bond will be, and how easily it can be broken. The number and arrangement of electrons affect how substances look, feel, and behave. Whether something is a gas, a solid, or a liquid depends, in part, on how tightly electrons hold atoms together. Whether something is shiny or dull, conductive or insulating, it is the electrons that are quietly pulling the strings. Even the colors we see are a result of electrons interacting with light. The pigments in a ripe red strawberry appear that way because their electrons absorb most other colors of light but reflect the red wavelengths back to our eyes. The deep blue of the evening sky, the soft green of new leaves, it is all a silent story told by electrons absorbing, emitting, and interacting with light in their own beautifully peculiar ways. What is perhaps most mind-bending is that we still do not fully understand them. Electrons are governed by the strange and wonderful rules of quantum mechanics, a field so counterintuitive that it often feels more like poetry than physics. Electrons can behave as particles or as waves, or sometimes as both at once. They can exist in multiple places until observed. They are slippery, mysterious, and utterly essential to the chemistry of life. In the end, though they are unimaginably small, electrons are the restless hearts of all atoms, always in motion, always influencing the world around them. From the bonds that hold our world together to the sparks of thought that flicker through our minds, electrons are responsible. They are the quiet agitators, the energetic instigators, the invisible artists behind the patterns of reality. Each thought that drifts through your mind right now is an electrical signal, carried by electrons fluttering through your neurons like tiny, fleeting flashes of consciousness. Small, yes. Shifty, definitely. But without them, the universe would be a very dull and very dark place indeed. If atoms have personalities, then chemical bonds are their relationships. Some are clingy and inseparable, some are generous and giving, and some prefer a more free-flowing, communal arrangement.
But no matter how different they seem, all bonds form for the same fundamental reason: to achieve a state of greater stability. Atoms are constantly seeking a lower, more peaceful energy state, and forming a bond is the surest way to get there. It is a quest not of emotion, but of a deep, logical desire for balance. Let's begin with the most classic of atomic pairings, the covalent bond. Picture two people quietly sharing a warm blanket. It's not a struggle, but a fair, mutual sharing that benefits both. That is the essence of covalent bonding. Two atoms each contribute an electron to the relationship, and together they share the pair. It's a peaceful, stable arrangement where everyone contributes and everyone benefits. Covalent bonds are especially common among nonmetals. Oxygen and hydrogen, for example, come together to form water by sharing electrons. Each hydrogen atom brings one electron to the partnership, and oxygen brings two of its own to share. Together, they complete their outer shells, fitting together like perfect, interlocking puzzle pieces. This bond is not just functional, it is foundational. The structure of water, created by these shared bonds, gives it all of its unique and life-sustaining properties, all thanks to atoms politely sharing. But not all relationships are built on sharing. Sometimes one atom desires an electron so strongly that it simply accepts it from another. This is where ionic bonds come into play. Instead of sharing, one atom gracefully donates an electron and the other gratefully accepts it. In this process, both atoms become electrically charged ions. The atom that loses an electron becomes positively charged, while the one that gains an electron becomes negatively charged. These oppositely charged ions are then drawn to each other by a powerful electrostatic attraction, like two magnets gently clicking into place. We saw this with sodium and chlorine. Sodium has one lonely electron it is eager to give away to find stability. Chlorine is just one electron short of a full shell and longs to complete its set. Sodium hands over its electron, and chlorine triumphantly accepts it. They transform into a sodium ion and a chloride ion, stick together, and become sodium chloride, or as it's known in kitchens around the world, table salt. In ionic bonding, there is no sharing. It is a full and complete transfer. The resulting ions are strongly attracted to one another, forming solid, crystalline structures. These are the neat, geometric stacks that make salt crystals sparkle so beautifully under the light. Then there is a third, very different kind of social dynamic. Picture a quiet, communal library where everyone has placed their books on a central table for all to share. No one keeps track of which book belongs to whom. They are all available for the good of the community. That is metallic bonding in a nutshell. In metals, the atoms don't just bond with their immediate neighbors. Instead, their outer electrons become delocalized. They are free to wander throughout the entire metallic structure, forming a sea of electrons that flows between the positively charged metal ions. This shared electron sea is what gives metals their characteristic properties. Because the electrons can move so freely, metals conduct electricity with ease. This same fluidity is responsible for their shiny, reflective surfaces and their ability to be shaped without breaking, a property known as malleability. But why do atoms go to all this trouble? The simple answer is energy. Every atom seeks to be in the lowest possible energy state, and bonding is one of the best ways to achieve that. When atoms form a bond, they release energy, moving from a higher energy solo existence to a lower energy bonded state. It is the atomic equivalent of finally sinking into a comfortable chair after a long day. At last, everything is calm and stable. The outermost electrons, those valence electrons, are the matchmakers in this whole scenario. Atoms are most reactive when their outer shells are incomplete. A hydrogen atom with just one electron wants to find a partner. A fluorine atom missing just one is eager to pair up. These needs are what drive atoms to seek out others, forming connections that satisfy both. Sometimes these bonds are incredibly strong. Diamonds, for instance, are a lattice of carbon atoms held together by a rigid, three-dimensional network of covalent bonds. This structure is what creates one of the hardest materials known to humanity. On the other hand, some bonds are quite gentle, like the attractions between water molecules. These are called hydrogen bonds. They are not full-fledged chemical bonds, but they are strong enough to give water its high boiling point and its remarkable surface tension, allowing insects to walk across its surface as if on a thin, invisible film. The strength of a bond is influenced by an atom's electronegativity, a measure of how strongly it pulls on electrons in a bond. An element like fluorine is famously greedy. It has the highest electronegativity and will pull shared electrons closer to itself in any covalent bond. On the other hand of the spectrum, atoms like cesium are far more relaxed about electron custody. When bonds form, energy is usually released in a process called an exothermic reaction. When bonds are broken, energy must be absorbed, which is an endothermic reaction. That's why lighting a fire requires an initial spark. You need to input energy to break the bonds in the wood. But once they break and new, more stable bonds form in the resulting smoke and ash, a flood of energy is released as heat and light.
The world around you is held together by these countless, invisible bonds, each one a result of atoms seeking peace and stability. Your own body is a vast, ongoing symphony of chemical bonding. Proteins fold into precise shapes. DNA strands are held together by gentle attractions. Even your thoughts are made possible by ions moving across cell membranes. At the end of the day, bonding is chemistry's way of creating order from chaos. Whether atoms share evenly, transfer outright, or contribute to a communal pool, the goal is always the same: lower energy, greater stability, and the potential to build something new. A gas becomes a liquid, a spark becomes a flame, all because of the endless ways atoms can link, rearrange, and hold on to one another. It is a silent, ceaseless dance of give and take, of holding hands and sometimes letting go. Energy is the quiet heartbeat of every chemical reaction. It's the invisible currency traded between atoms as they form or break bonds, reshape themselves, or transform into something entirely new. But even the most reactive substances usually need a gentle push to get started. This little nudge is what chemists call activation energy, the minimum amount of energy required to initiate a reaction. Without it, even the most promising combination of ingredients would simply sit together in an awkward silence, like two people at a quiet party waiting for someone else to speak first. Consider a matchstick. It contains all the necessary ingredients for fire: chemicals eager to react, oxygen in the air, and a wooden stick ready to be transformed. And yet, nothing happens. That gentle friction provides the activation energy needed to kickstart the reaction. A little heat is introduced, molecules begin to vibrate more vigorously. Old bonds start to stretch and break, and new ones quickly form. In the blink of an eye, combustion begins. But without that initial spark, the match would remain perfectly still. That's because molecules, in their natural state, prefer to remain as they are, unless something comes along to jostle them out of their comfort zones. Activation energy is that gentle, or sometimes not so gentle, nudge. You can picture activation energy as gently pushing a boulder over a hill. The boulder represents your reactants, resting comfortably at the base. To get to the other side, the product side, the boulder must first be pushed uphill. That uphill effort is the activation energy. Once the boulder reaches the peak, it can roll down the other side with ease. Similarly, once a reaction overcomes its energy barrier, it tends to proceed without much additional effort. Some reactions need very little energy to begin, while others require a great deal. This is why certain chemicals can sit safely on a shelf for years, while others might burst into flame at the slightest provocation. It's not just about what the molecules can do, but how much energy it takes to convince them to do it. Now, let's explore what happens after a reaction gets started. Once those initial bonds begin to shift, energy is either absorbed or released. This brings us to two important types of reactions: endothermic and exothermic. Endothermic reactions are those that absorb energy from their surroundings. It's like the reaction needs a steady diet of heat to keep going. The classic example is photosynthesis, the process by which plants use sunlight to convert carbon dioxide and water into glucose.
Without that constant stream of solar energy, the entire process would grind to a halt. Another example of an endothermic process can be found in instant cold packs. These contain water and a separate pouch of a salt like ammonium nitrate. When the two are mixed, the dissolving process absorbs heat from the surroundings, rapidly lowering the temperature. The cold you feel isn't something being created by the reaction, it's the sensation of heat being drawn away from your skin. On the other side, we have exothermic reactions, the warm, generous types that release energy into their surroundings, usually as heat or light. Combustion is the most dramatic example. When you light a candle, you are watching hydrocarbons in the wax react with oxygen to produce carbon dioxide, water vapor, and a steady, satisfying release of heat and gentle flame. Fireworks, explosions, and even the metabolism of food inside your body are all driven by exothermic reactions. In fact, your cells are like tiny, polite combustion chambers. When you eat, the sugars in your food are broken down in a controlled, step-by-step series of exothermic reactions. This releases the energy your body uses for everything from blinking to dreaming. You don't burst into flame, thankfully, because the energy is released in small, manageable doses, carefully regulated by enzymes. Some reactions can go either way. Water evaporating from a surface is endothermic. It absorbs heat to escape into the air as vapor. But when that vapor condenses back into liquid, as dew on the morning grass, it releases that heat in an exothermic process. These reversible reactions create a sort of energetic dance, shifting depending on the surrounding conditions. Interestingly, many reactions that seem explosive are really just very fast. A pile of dry leaves slowly decomposing over many months is a chemical reaction. The same leaves set ablaze transform in seconds. Both processes involve rearranging the same atoms, but one takes a leisurely, quiet path, while the other charges ahead in a fiery burst of exothermic enthusiasm. Catalysts can influence this process by lowering the activation energy. These are substances that speed up a reaction by providing an easier path, making it simpler for reactants to reach that tipping point. They are the quiet matchmakers of the chemical world, gently encouraging bonds from behind the scenes without getting involved themselves. Enzymes in your body are biological catalysts that make the chemistry of life possible. Without enzymes, the reactions in your body would be so sluggish that you couldn't survive. Digestion would take years instead of hours. Catalysts don't provide the energy themselves, they simply make the journey smoother and faster. The idea of activation energy also helps us understand why some substances are unstable. If a molecule is already perched precariously in a high-energy state, it may only need the smallest nudge to collapse into something more stable, releasing energy in the process. This is the case with many reactive chemicals. They've already paid most of their activation energy fee and are just waiting for the door to open. So many safety measures revolve around controlling this energy threshold. Volatile chemicals are stored in cool, dark places to minimize the available energy. It's why medicines are often refrigerated and aerosol cans carry warnings about heat. It all comes down to managing energy on a molecular level. In a way, all chemical reactions are just nature's method of reorganizing atoms to find a more comfortable energy level. It's not unlike adjusting your pillows before you fall asleep, shifting things around until everything feels just right. Whether it's the gentle warmth of a hand warmer, the cool sensation of a cold pack, or the soft glow of a candle, you are witnessing the quiet play of energy, moving, transforming, and occasionally bursting forth. It is never random. There is always a reason, and that reason almost always involves just the right amount of energy, arriving at just the right moment. Acids and bases are the great mood setters of the chemical world. When they enter a solution, things tend to become quite lively. They can make metals fizz, change the color of liquids, or turn simple cabbage juice into a beautiful chemistry experiment.
And while we often think of them as opposites, they are really just two sides of the same reactive coin, both defined by how they interact with water and, more specifically, with two very important ions, hydrogen ions, H+, and hydroxide ions, OH-. To understand them, let's start with pure water. Water, though it seems perfectly neutral and peaceful, is in a constant, quiet state of flux. At any given moment, a tiny fraction of water molecules spontaneously separate into H+ and OH- ions. Then, just as quickly, they recombine to form water again. It's a delicate, balanced equilibrium, like a calm, whispered conversation in a room full of molecules. Now, an acid is any substance that increases the concentration of hydrogen ions, H+, when added to water. You can think of it as a generous donor, always handing out H+ ions to the solution. On the other hand, a base is a substance that either removes those H+ ions or adds hydroxide ions, OH-. In essence, acids tilt the balance toward more H+, while bases tilt it toward more OH. This balance is measured using the pH scale, which typically ranges from 0 to 14. A pH of 7 is considered perfectly neutral. This is the pH of pure water, right in the middle. Anything with a pH below 7 is acidic, and anything above 7 is basic or alkaline. The lower the number, the more acidic the solution. The higher the number, the more basic. It's important to remember that the scale is logarithmic, which means each whole number represents a tenfold difference. So, a solution with a pH of 4 is 10 times more acidic than one with a pH of 5. Lemon juice with a pH around 2 is quite acidic. Vinegar sits around pH 3. On the other side of the scale, baking soda is mildly basic, around pH 9, while household bleach can be highly alkaline with a pH of 12 or 13. At these extremes, both strong acids and strong bases can be quite corrosive. Chemically, what makes an acid so reactive is its tendency to release those hydrogen ions. These tiny, positively charged particles, once freed in a solution, can interact with other molecules in all sorts of ways, altering their structures, speeding up reactions, or even damaging tissues. Bases, meanwhile, either absorb those free hydrogen ions or contribute hydroxide ions that neutralize them. This constant tug of war over H+ ions is at the heart of countless chemical processes. Acids and bases are everywhere. In your stomach, hydrochloric acid helps digest food by breaking down proteins. Your body then releases bicarbonate, a mild base, to neutralize that acid as the food moves on. In cooking, acids like lemon juice or vinegar add brightness and flavor. They can also tenderize meat by denaturing its proteins. Bases are less common in the kitchen, but they have their uses too. Baking soda, a base, reacts with an acid, like buttermilk, to release carbon dioxide gas, causing dough to rise and become light and fluffy. One of the most satisfying demonstrations of this chemistry is neutralization. When an acid and a base meet in just the right amounts, they react to form water and a salt. This can happen subtly or, as with the classic vinegar and baking soda volcano, with a great deal of enthusiastic bubbling. That fizz is the release of carbon dioxide gas, a harmless, visible sign of a peaceful resolution between chemical opposites. The way acids and bases affect reactions goes far beyond simple fizzing. They can change the structure of molecules and act as catalysts or inhibitors. In living organisms, this sensitivity to pH is crucial. The enzymes in your body are highly dependent on pH. If their environment becomes too acidic or too basic, they can lose their shape and stop working. This is one reason why your body works so hard to maintain your blood pH in a very narrow, stable range, around 7.4. Just a small shift can cause serious health problems. pH also plays a significant role in the environment. Acid rain caused by pollutants in the atmosphere can lower the pH of lakes and soils, harming plant and aquatic life. Similarly, ocean acidification, caused by the absorption of excess carbon dioxide from the air, affects the ability of marine creatures like corals and shellfish to build their protective shells. These might seem like small shifts, but in systems finely tuned over millions of years, they can have cascading effects. In industry, acid-base chemistry powers everything from wastewater treatment to the lead-acid batteries in cars. In cleaning products, bases help to dissolve grease and grime. It's not magic, it's just hydrogen and hydroxide ions doing their usual quiet dance. Indicators are another charming part of this toolkit. These are substances that change color depending on the pH. Litmus paper turns red and acid and blue and moist. Even red cabbage juice can act as a natural pH indicator, shifting through a beautiful rainbow of colors depending on a solution's acidity. But behind all the colorful transformations lies a deep and elegant system that governs countless processes in our bodies, our environment, and our technology. At its heart, acid-base chemistry is all about balance, the push and pull between giving and taking, between too much and not enough. One offers, the other accepts, and in just the right proportions, they find peace, a stable, neutral place where the fizzing stops and the chemistry settles down, at least until someone adds a little more lemon juice. Temperature and pressure might seem like things you simply adjust on a thermostat or check in a weather report, but in the world of chemistry, they are master manipulators. They are the invisible forces that can coax molecules to dance, collide, and react, sometimes slowly and gently, other times with explosive speed. They are the ultimate party planners for the molecular world, setting the scene and the energy level for reactions to begin. To understand how this works, we can turn to one of the most important ideas in chemistry, the kinetic molecular theory. At its heart, this theory states that all matter is made of particles in constant, ceaseless motion. Even in something that appears perfectly still, a block of ice, a wooden table, your own fingertips, the atoms and molecules within are vibrating, jiggling, and bouncing in place. The hotter a substance is, the faster its particles move. The cooler it is, the slower and more gentle their jiggle. Imagine a quiet, spacious room full of people slowly wandering. They might rarely bump into one another. But if you were to play some lively music, the energy in the room would rise. People would start moving faster, and the chance of collisions would increase significantly. The same is true for molecules. Heat is a form of energy, and when you add it to a system, its particles gain kinetic energy. They move faster, they collide more often, and they collide with greater force. Since chemical reactions happen when molecules collide in just the right way with enough energy, heating a substance dramatically increases the likelihood that a reaction will occur. This is why food cooks faster in a hot oven and why milk spoils more quickly on a warm day. Heat, quite literally, gets things moving. However, not every collision results in a reaction. Molecules must collide with sufficient energy, the activation energy, and at the correct orientation. It's like tossing two puzzle pieces at each other. Only when they hit in just the right way will they snap together. The added energy from heat helps more of those collisions to be successful ones. Now, let's bring pressure into the picture. Pressure is all about how tightly particles are squeezed together. This is especially important for gases, where molecules are naturally far apart and moving freely. If you increase the pressure, you are forcing those molecules into a smaller space, cramming them closer together. With less room to roam, collisions become far more frequent, which in turn increases the rate of reaction. Think of it like a crowd at an outdoor concert in a wide open field versus the same crowd packed into a small club. In the club, people will be brushing shoulders constantly. In chemistry, those shoulder bumps are opportunities for reaction, and pressure makes them happen more often. Temperature and pressure don't just affect the speed of reactions, they can also influence which products are formed. Some reactions will only occur at very high temperatures or under extreme pressure. Others might even reverse direction if the conditions are changed. This is critically important in industrial chemistry, where fine-tuning heat and pressure can maximize the yield of a desired product. A famous example is the Haber-Bosch process, which produces ammonia for fertilizer from nitrogen and hydrogen gases.
On their own, these gases have little interest in reacting, but under high temperature and very high pressure, with the help of a catalyst, they are finally convinced to combine and form ammonia. This single, carefully controlled reaction is now responsible for a significant portion of the world's food supply. Temperature also changes the nature of substances themselves through phase changes. Solids melt into liquids, and liquids evaporate into gases as particles gain enough energy to overcome the forces holding them together. These transitions are physical, not chemical. The molecules themselves remain the same, but they demonstrate the powerful ability of heat to disrupt structure and enable new kinds of motion. Pressure has its own quirks as well. While it primarily affects gases, it can also influence reactions involving liquids and solids, especially if the reaction involves a change in volume. According to Le Chatelier's principle, if a reaction produces fewer gas molecules than it started with, increasing the pressure will favor the forward reaction, as the system tries to relieve that pressure. This interplay between heat and pressure appears in countless everyday experiences. A pressure cooker works by trapping steam, which increases the internal pressure and raises the boiling point of water. This allows food to cook at a higher temperature, making it faster and more tender. At the bottom of the deep sea, the immense pressure changes the way gases dissolve and how chemical reactions proceed, allowing unique forms of life to thrive near hydrothermal vents. In the lab, chemists manipulate these variables with great precision, but managing them is a delicate art. Too much heat can cause sensitive compounds to decompose. Too much pressure can become a serious engineering challenge. Sometimes the goal isn't speed at all, but control, allowing a reaction to proceed slowly and predictably to avoid unwanted side products. What's remarkable is how universal these principles are. Whether you are baking bread, studying volcanoes, or designing rocket fuel, the same basic rules apply. Heat adds motion. Pressure adds proximity, and together they influence the course of chemistry in ways both subtle and spectacular. So much of what we observe is shaped by these invisible forces acting on tiny particles. Molecules don't decide to react, they are guided by energy, movement, and proximity. Heat gives them the speed, and pressure gives them the squeeze. Together, they unlock the endless possibilities of transformation, one gentle collision at a time. In the neat and tidy world of textbooks, chemical reactions often look like one-way streets. You begin with reactants, you mix them, and products appear. The reaction is done. But in reality, chemistry is rarely so final. Many reactions can in fact go both ways. Molecules don't just combine and call it a day. They can also separate, rejoin, and sometimes drift back and forth between states endlessly. This is the world of reversible reactions, where the finish line is more of a gentle roundabout than a dead end. A reversible reaction is exactly what it sounds like, a chemical process that can proceed in both the forward and reverse directions. Reactants become products, but those very products can also break down to become reactants again. It's a chemical tug-of-war where both sides are pulling and neither ever wins. Instead of one side collapsing, the system settles into a state of balance, a kind of truce. This peaceful balance is called chemical equilibrium. Equilibrium doesn't mean that nothing is happening. On the contrary, the reaction is still occurring in both directions, but it's doing so at exactly the same rate. Imagine people walking up an escalator at the same speed as people are walking down it. The number of people at the top and the bottom remains constant, even though there is perpetual movement. This is a dynamic equilibrium. This concept is central to understanding how many natural processes work. It explains why some reactions never seem to go to completion and why changing the conditions can tip the balance one way or another. Chemistry, at its core, loves to find a balance between competing forces. Let's imagine a simple reversible reaction. Two colorless gases, hydrogen and iodine, react to form a deep purple gas called hydrogen iodide. At first, as the hydrogen and iodine are mixed, the purple gas begins to form. But as more and more hydrogen iodide accumulates, some of it starts to break back down into hydrogen and iodine. Eventually, the rate at which the reactants combine equals the rate at which the product splits apart.
The result is a mixture of all three gases, locked in a dynamic dance where the overall color and composition remains constant. This dynamic equilibrium concept is central to understanding how many natural processes work. It explains why some reactions never seem to go to completion and why changing the conditions can tip the balance one way or another. Chemistry, at its core, loves to find a balance between competing forces. Let's imagine a simple reversible reaction. Two colorless gases, hydrogen and iodine, react to form a deep purple gas called hydrogen iodide. At first, as the hydrogen and iodine are mixed, the purple gas begins to form. But as more and more hydrogen iodide accumulates, some of it starts to break back down into hydrogen and iodine. Eventually, the rate at which the reactants combine equals the rate at which the product splits apart. The result is a mixture of all three gases, locked in a dynamic dance where the overall color and composition remains constant. Equilibrium doesn't mean that nothing is happening. On the contrary, the reaction is still occurring in both directions, but it's doing so at exactly the same rate. Imagine people walking up an escalator at the same speed as people are walking down it. The number of people at the top and the bottom remains constant, even though there is perpetual movement. This is a dynamic equilibrium. This concept is central to understanding how many natural processes work. It explains why some reactions never seem to go to completion and why changing the conditions can tip the balance one way or another. Chemistry, at its core, loves to find a balance between competing forces. Let's imagine a simple reversible reaction. Two colorless gases, hydrogen and iodine, react to form a deep purple gas called hydrogen iodide. At first, as the hydrogen and iodine are mixed, the purple gas begins to form. But as more and more hydrogen iodide accumulates, some of it starts to break back down into hydrogen and iodine. Eventually, the rate at which the reactants combine equals the rate at which the product splits apart. The result is a mixture of all three gases, locked in a dynamic dance where the overall color and composition remain constant. This equilibrium is a delicate state, dependent on temperature, pressure, and concentration. This is where a helpful piece of chemical wisdom comes in, known as Le Chatelier's principle. It states that when you disturb a system at equilibrium, the system will shift in a way that counteracts the disturbance. It's surprisingly intuitive. Imagine a room with a thermostat set to a comfortable temperature. If someone opens a window and cold air rushes in, the heating system kicks on to bring the temperature back up. Chemical systems behave in a similar way. If you add more reactants to a system at equilibrium, the reaction will shift to use them up, producing more products. If you remove products, the system will shift to replace them. If you increase the heat, the system will shift in the direction that absorbs heat, the endothermic direction. It is constantly adjusting, trying to undo whatever change was introduced. Pressure works the same way, especially with gases. If you increase the pressure, the system will shift toward the side of the reaction with fewer gas molecules in an attempt to reduce the crowding. It's all a matter of balance, of molecules trying to find the most comfortable arrangement under their current circumstances. Equilibrium is especially important in biological systems. Our bodies rely on countless reversible reactions that must remain finely tuned. Take the oxygen-carrying protein hemoglobin. In the lungs, where oxygen concentration is high, the equilibrium favors binding, and oxygen attaches to hemoglobin. In the tissues, where oxygen levels are lower, the equilibrium shifts, and hemoglobin releases the oxygen where it is needed. It's an elegant, automatic adjustment that happens with every single breath. Another vital example is the carbonic acid equilibrium in our blood, which helps maintain our blood pH within a very narrow, stable range. Your body uses this reversible system, along with your lungs and kidneys, to remain in a state of perfect chemical harmony. In industrial chemistry, mastering equilibrium can mean the difference between success and failure. The Haber-Bosch process for making ammonia, for instance, is a reversible reaction. By carefully manipulating the temperature and pressure, chemists can shift the equilibrium to favor the formation of the desired product, ammonia. It's a constant balancing act between chemistry and efficiency. There is something poetic about equilibrium. It reminds us that nature often prefers moderation and compromise over extremes. The world isn't full of reactions that go in one direction and simply stop. Instead, it is full of reversibility, of systems that adjust, respond, and settle into a state where everything seems calm on the surface, even as there is constant motion underneath. Even in a bottle of vinegar on your kitchen shelf, tiny equilibrium shifts are still occurring. In the atmosphere, gases are constantly exchanging and reacting. Even in solid rocks, over vast geological timescales, minerals transform and equilibrium slowly drifts from one state to another. Equilibrium is a dynamic pause, a point where change doesn't cease, but rather balances itself out. It's the moment when the tug-of-war rope stops moving, not because the pulling has stopped, but because both sides are pulling with equal, gentle force. It is not peace through stillness, it is peace through motion. And remembering this, you start to notice balance everywhere, in chemical reactions, in ecosystems, and in the quiet rhythm of your own breath. Explosions are chemistry's most dramatic and sudden outbursts. They are the grand, showy spectacles that demand attention, fast, fiery, and loud. But behind the startling booms and brilliant flashes of light lies a surprisingly elegant principle: the extremely rapid release of energy from a chemical reaction. An explosion is simply chemistry happening at an incredible speed, often in a confined space, with very little regard for subtlety. At its core, an explosion is a sudden, rapid expansion of matter accompanied by a release of energy, as heat, light, and shock waves. The key ingredient is always speed, reactions that happen in milliseconds, unleashing enormous amounts of energy all at once. Most chemical explosions involve combustion, where a substance reacts quickly with an oxidizer like oxygen. Combustion isn't always explosive, but the gentle flame of a candle is a controlled, steady burn. But if you change the conditions, add more fuel, more oxygen, or confine it tightly, the very same chemistry can become explosive. Imagine a simple balloon filled with hydrogen gas. If you introduce a spark, the hydrogen will rapidly react with the oxygen in the air to form water vapor. This reaction is extremely exothermic, releasing a large amount of energy so quickly that the surrounding air expands almost instantly, creating a shock wave we hear as a loud and satisfying bang. The key to most explosions is this rapid oxidation. In a slow burn, like rusting, the energy is released gradually and dissipates. In an explosion, it's unleashed all at once, like a tightly wound spring suddenly being let go. Fireworks are a perfect example of how controlled explosions can be used to create beauty. Each firework is a carefully packed chemistry lab containing fuels, oxidizers, and color-producing metal salts. When ignited, the fuel burns rapidly, producing hot gases that propel the firework into the sky. When it bursts, different metal salts create the vivid colors: strontium for red, barium for green, and copper for blue. It is chemistry as a carefully choreographed ballet of light and sound. Then there are high explosives like TNT, trinitrotoluene. TNT is an example of a compound that contains both the fuel and the oxidizer within the same molecule. When detonated, it rearranges its own atoms with incredible speed, producing various gases and an enormous release of heat. What makes TNT interesting is its stability. It needs a smaller, more sensitive explosive, a detonator, to provide the precise jolt of activation energy required to start the reaction. Once started, however, the reaction propagates through the material in an instant. But explosions aren't always intentional. Sometimes they are the result of accidents, when the right ingredients come together under the wrong conditions. Believe it or not, even simple kitchen ingredients can be surprisingly energetic. Fine powders like flour or powdered sugar, when suspended in the air, can form a combustible dust cloud. The tiny particles have a huge surface area, making them highly reactive. If this cloud is confined and finds an ignition source, it can result in a dangerous dust explosion. Aerosol cans contain flammable propellants under pressure. If heated, the internal pressure can build until the can ruptures, releasing the flammable gas, which can then ignite. Even adding water to a grease fire can be disastrous. The water flashes into steam, expanding rapidly and ejecting the burning oil into a massive fireball. And then there's the classic reaction between baking soda and vinegar. While not truly explosive, it is certainly enthusiastic. The acid and base react to produce carbon dioxide gas, which expands quickly, causing the familiar bubbling and fizzing. It's a gentle reminder that even simple ingredients hold reactive potential. In other settings, explosive reactions are harnessed for practical use. Car airbags deploy using a controlled, rapid decomposition of a chemical like sodium azide. This reaction produces nitrogen gas, which inflates the airbag in less than a tenth of a second, providing a life-saving cushion. Explosions even play a role in the natural world. Volcanoes are perhaps Earth's most dramatic chemists, combining heat, pressure, and reactive gases to produce massive eruptions. It's a reminder that the Earth itself is always reacting, simmering, and sometimes bursting at the seams. Ultimately, explosions are not inherently bad. They are simply fast reactions, doing what reactions do, breaking bonds, forming new ones, and releasing energy. The challenge lies in managing them. Too slow, and the reaction fizzles out. Too fast, and it can become destructive. Chemists and engineers have learned to walk this fine line, harnessing this powerful chemistry to launch spacecraft, save lives, and create moments of breathtaking beauty in the night sky. The same principles apply whether you are lighting a candle or igniting rocket fuel. It's all about energy, molecules, and the rate at which change unfolds. Carbon is the undisputed cornerstone of life's chemistry. It isn't the flashiest element, nor the heaviest, nor the rarest, but when it comes to versatility and the sheer ability to build complex and beautiful structures, carbon takes center stage. It is the molecular shapeshifter, responsible for everything from the delicate wings of a butterfly to the complex strands of your own DNA. What makes carbon so special is its unique ability to form up to 4 strong, stable bonds at once. This might not sound like much, but in the microscopic world of atoms, 4 is a magic number. It allows carbon to form an incredible variety of structures: long chains, intricate branches, and stable rings. Carbon can bond with itself and with a wide range of other elements, creating a molecular architecture that is both sturdy and flexible. This has made it the foundation for all known life. The entire field of organic chemistry is dedicated to the study of these carbon-based compounds. Carbon's talent for bonding with itself, known as catenation, is the root of its versatility. No other element can rival it. Silicon, sitting just below carbon on the periodic table, tries its best, but its bonds are weaker and less stable. Carbon is the original, and life as we know it would not exist without it. Organic molecules are essentially carbon-based frameworks decorated with functional groups, small clusters of other atoms that define how the molecule behaves. Like different accessories on a simple black dress, these groups give each molecule a specific role and personality. Add an OH group, and you have an alcohol. Add a carboxyl group, COOH, and it's an acid. It's all carbon underneath, but with different attachments, it can play almost any part. Let's talk about structure, because carbon doesn't just form molecules, it builds architecture. The simplest forms are straight chains of carbon linked in a line, but these chains can branch, bend, or even loop back on themselves to form rings, like the hexagonal structure of cyclohexane. Some molecules are enormous, like proteins, which are long, folded chains of amino acids, or DNA, which twists into its famous double helix. Others are tiny, like methane, with just one carbon bonded to 4 hydrogens. But no matter the size, the rules are the same. Carbon at the center, holding everything together with its 4 bonding arms.
Those four arms also allow carbon to form double and even triple bonds with other atoms. In a double bond, two pairs of electrons are shared, creating a stronger and shorter connection. These multiple bonds change the geometry and reactivity of molecules, adding another layer of depth and complexity to organic chemistry. Then there's isomers, molecules that have the exact same chemical formula but different structural arrangements. Carbon is a master of creating isomers. It can take the same handful of atoms and arrange them in entirely different ways, leading to compounds with wildly different properties. It's a bit like rearranging the furniture in a room. The pieces are the same, but the result feels completely different. Life as we know it is essentially one long, beautiful carbon experiment. Proteins, lipids, fats, carbohydrates, and nucleic acids like DNA, the four great classes of biological macromolecules, are all carbon-based. The membranes that hold our cells together are built from lipids. Carbohydrates, like glucose, provide our bodies with quick energy. And DNA carries our genetic code in a molecule made almost entirely of carbon, hydrogen, oxygen, nitrogen, and phosphorus. All of these functions rely on carbon's ability to form bonds that are stable enough to build lasting structures, yet not so strong that they become rigid and inert. Life needs that delicate balance. It needs a scaffold that can support complexity but still allow for change, motion, and reaction. Beyond biology, carbon forms everything from the synthetic polymers in plastics to cutting-edge nanomaterials like graphene. The fuels we depend on, like gasoline and natural gas, are hydrocarbons, chains of carbon and hydrogen packed with stored energy. Carbon's versatility is also reflected in its pure forms, known as allotropes. As graphite, the carbon atoms are arranged in flat sheets, making it soft and slippery, perfect for the lead in your pencil. As diamond, the atoms are locked into an incredibly strong three-dimensional lattice, making it one of the hardest substances known. The difference is not in what they are made of, but in how their atoms are arranged. Same element, entirely different personality. And of course, carbon is the central figure in our planet's climate. Carbon dioxide, a simple molecule with one carbon and two oxygens, is a vital greenhouse gas. Its ability to trap heat has made it a focal point in our understanding of climate change and sustainability. Carbon is not just the stuff of life, it is the stuff of consequence. In the world of atoms, carbon is the quiet genius. It builds the molecules of life, the materials of modernity, and the cycles of nature. It bends, bonds, and links in ways that other elements can only dream of. It is the reason you are made of molecules instead of moon rocks. Every heartbeat, every breath, every thought comes down to this one element with four bonding arms, a love of structure, and an endless capacity for forming connections. Carbon isn't just an element, it is the storyteller of life. The word redox might sound like the name of a futuristic cleaning product, but in reality, it describes one of the most fundamental chemical processes in the universe. Short for reduction oxidation, redox reactions are all about the quiet exchange of electrons, those tiny, energetic particles that make atoms tick. Whenever something is burning, resting, charging a battery, or even digesting food, you can be sure that redox chemistry is running the show behind the scenes. At its core, a redox reaction is like a well-coordinated game of musical chairs for electrons. One substance loses electrons and another substance gains them. That's it. The trick is that these two processes, oxidation and reduction, always happen together. You cannot have one without the other. An electron doesn't just vanish. If one atom gives one up, another must be there to accept it.
Here are the definitions to hold on to. Oxidation is loss of electrons, while reduction is gain of electrons. You can remember this with the acronym OIL-RIG. It might sound counterintuitive that reduction involves a gain, but because electrons are negatively charged, gaining them reduces an atom's overall charge. Electrons are the energetic currency of atoms, and during a redox reaction, they are passed from one atom to another. Some atoms, like oxygen, are very good at pulling electrons toward themselves. Others, like metals, are more generous, readily giving up their electrons to achieve a more stable state. Let's look at a simple, iconic redox reaction, the rusting of iron. When iron is exposed to oxygen and water, it slowly transforms into iron oxide, the reddish-brown, flaky substance we call rust. In this process, the iron atoms lose electrons. They are oxidized. Those electrons are then picked up by oxygen atoms, which become reduced. The result is iron oxide, or rust. The rust isn't just a surface stain, it's a sign that a fundamental chemical transformation has occurred, one electron at a time. Other redox reactions are far more energetic. Combustion, for example, is just a very fast oxidation reaction. When you burn wood or gasoline, the carbon and hydrogen in the fuel are rapidly oxidized by oxygen, releasing a great deal of energy as heat and light. It's a chaotic and beautiful process, driven entirely by the rapid transfer of electrons. But redox isn't just about things breaking down or burning, it's also how your body generates energy. Inside your cells, a process called cellular respiration breaks down glucose from the food you eat. During this process, electrons are stripped from the glucose molecules and passed down a series of proteins in what is called the electron transport chain. This controlled flow of electrons powers the production of ATP, the cell's main energy currency. Oxygen is the final electron acceptor at the end of this chain, which is why we need to breathe. Without oxygen to catch those electrons, the entire system would grind to a halt. This carefully orchestrated flow of electrons is beautifully similar to what happens inside a battery. A battery is essentially a portable, contained redox reaction. Inside, you have two different materials, an anode that readily gives up electrons, it gets oxidized, and a cathode that eagerly accepts them, it gets reduced. When you connect the battery, electrons flow from the anode to the cathode through the circuit, powering your device. It is silent, reliable redox at work. Rechargeable batteries use reversible redox reactions. When you charge them, you are using electricity to push the electrons back to where they started, resetting the system. Photosynthesis is another vital redox process. In a green leaf, light energy is used to split water molecules. Electrons are pulled away from the water, oxidation, and are used to help convert carbon dioxide into glucose, reduction, storing the sun's energy in chemical bonds. It's essentially the reverse of cellular respiration. Instead of burning sugar to release energy, the plant uses energy to build sugar. In both cases, electrons are on the move. In the lab, redox reactions are used for things like electroplating, where a thin layer of metal is deposited onto an object to make it shiny or protect it from corrosion. Many water treatment systems use redox reactions to neutralize harmful contaminants. Even the little strips in a blood glucose meter use a tiny redox reaction to measure sugar levels. The substance that loses electrons is called the reducing agent because it causes the other substance to be reduced. The substance that gains electrons is the oxidizing agent because it causes the other substance to be oxidized. It's a kind of reciprocal chemistry where nothing happens in isolation. What makes redox reactions so compelling is that they are truly everywhere. They power life, industry, and nature. They can be slow and creeping, like rust on an old fence, or unimaginably fast, like a spark igniting a gas stove. They can be beneficial, like the energy we get from food, or destructive, like corrosion weakening a bridge. But they all come down to one simple, elegant process: electrons finding new homes. Every redox reaction is a story of change, of atoms adjusting their balance, and of systems shifting in a quiet, constant pursuit of stability. In the grand theater of chemistry, most of the attention goes to the big players, the atoms reacting, the bonds breaking, and the energy being released. But tucked quietly behind the curtain are the unsung heroes that make it all happen, faster, smoother, and with far less effort. These are the catalysts, the quiet helpers of the molecular world. They don't take center stage, they don't change themselves, But without them, many of the reactions essential for life and industry would move so slowly they might as well not be happening at all. At its core, a catalyst is a substance that speeds up a chemical reaction without being consumed in the process. It's a sort of molecular matchmaker, helping reactants find each other and encouraging them to get on with the business of bonding. Once the reaction is finished, the catalyst steps away, unchanged and ready to facilitate the next one. It is the ultimate enabler, efficient, discreet, and quietly indispensable. A catalyst works by providing an alternative pathway for the reaction, a shortcut with a lower activation energy. The result is that the reaction can happen more quickly and under milder conditions without needing to raise the temperature or pressure. It's like finding a secret side street to bypass a traffic jam. You reach the same destination, but the journey is much faster and requires less fuel. Catalysts come in many forms. In industry, metals like platinum and palladium are used to catalyze everything from making plastics to processing fuel. In your car's catalytic converter, these metals help transform toxic exhaust gases like carbon monoxide into less harmful substances like carbon dioxide. But the most elegant and astonishing catalysts of all are found inside your own body. They are called enzymes. Enzymes are biological catalysts made of proteins, and they are astonishingly good at their jobs. They can speed up reactions by factors of millions, turning slow, lumbering chemical processes into lightning-fast transformations. Without enzymes, your body would simply not work. Digestion, cell repair, energy production, all of it relies on enzymes working around the clock. Each enzyme is highly specific, usually working with only one particular molecule, called a substrate. The enzyme has a specially shaped pocket called the active site, which fits the substrate like a glove. When the substrate binds, the enzyme holds it in just the right position to help break or form bonds efficiently. Once the reaction is complete, the new products drift away, and the enzyme is ready for the next substrate. It's like a molecular assembly line where the workers never tire and everything runs with perfect precision. A classic example is the enzyme catalase found in nearly all living cells. Its job is to break down hydrogen peroxide, a harmful byproduct of metabolism, into harmless water and oxygen. A single molecule of catalase can convert millions of hydrogen peroxide molecules every second. It's chemistry on fast forward. Another star enzyme is amylase, found in your saliva, which starts breaking down starches into simpler sugars the moment you start chewing.
Enzymes are sensitive to their environment. Changes in temperature or pH can alter their shape and cause them to stop working. This is why a high fever can be dangerous and why your body works so hard to maintain a stable internal state known as homeostasis. The chemistry of life is balanced on a knife's edge, and enzymes are at the very center of it all. Outside of biology, catalysts are critical in manufacturing. The Haber-Bosch process for making fertilizer relies on an iron catalyst. Without it, we would not be able to produce enough food to feed the world's population. In fact, it's been said that half of the nitrogen atoms in your own body were fixed from the air by this process, made possible by a humble metal catalyst. In the field of green chemistry, catalysts are essential for making processes more sustainable. By lowering energy requirements and reducing waste, they help make chemistry more efficient and less harmful to the environment. They are the quiet force behind a more responsible way of doing science. Once you start noticing them, you realize that catalysts are everywhere. They enable change without changing themselves. They make the impossible seem routine. They accelerate progress without ever stealing the spotlight. It's hard not to admire that kind of quiet confidence. In a world where most reactions require heat, pressure, or brute force, catalysts are the smooth operators, slipping in, nudging atoms into place, and gliding away before anyone even notices. They're chemistry's backstage crew, making sure the stars shine as brightly as possible. And they remind us that transformation can come from gentle nudges, subtle shifts, and quiet, behind-the-scenes brilliance.
Water is, without a doubt, one of the strangest and most wonderful substances on Earth. It is also one of the most essential. It covers most of our planet, it fills the air as vapor, it flows through our veins, and it makes up the bulk of every cell in our bodies. And yet, for something so completely familiar, water is quietly full of mysteries. It bends the rules of chemistry, defies expectations, and holds our world together with an elegance that is all too easy to overlook. At a glance, water seems simple. H2O, two hydrogen atoms bonded to one oxygen atom. But this tiny V-shaped molecule is anything but ordinary. Its peculiarities are the result of its shape, its polarity, and the special bonds it forms with its neighbors. Let's start with polarity. A water molecule is polar, meaning it has a slightly positive end and a slightly negative end. The oxygen atom is more electronegative, so it pulls the shared electrons a little closer, giving it a partial negative charge and leaving the hydrogen atoms with partial positive charges. This makes the water molecule behave like a tiny magnet. This polarity is the heart of water's personality. It allows water molecules to attract one another through hydrogen bonds. These aren't true chemical bonds, but rather strong attractions between molecules. Yet, they are powerful enough to give water a collection of remarkable and life-sustaining properties. Hydrogen bonding gives water its unusually high boiling point and its strong surface tension, the property that allows water to bead up and lets insects walk on its surface as if on an invisible film. It also gives water cohesion, the ability to stick to itself, which helps pull water up from the roots to the leaves of the tallest trees. Water also has a very high heat capacity. It can absorb a vast amount of heat with only a small rise in its own temperature. This is why coastal climates are often milder than inland ones. The ocean acts as a giant thermal buffer, absorbing heat in the summer and slowly releasing it in the winter. It is nature's temperature manager, keeping our planet's climate within a tolerable range. Here is another of water's strange tricks. It expands when it freezes. Most substances become denser and shrink when they solidify, but water does the opposite. As it freezes, its hydrogen bonds lock the molecules into an open, hexagonal crystalline structure that takes up more space than the jumbled arrangement of liquid water. This is why ice is less dense than liquid water and why ice floats. The consequences of floating ice are enormous. If ice sank, lakes and oceans would freeze from the bottom up, making most aquatic life impossible. Instead, ice forms an insulating layer on the surface, protecting the liquid water below and allowing ecosystems to survive harsh winters. It is a quirk of molecular geometry that ends up preserving life itself. Water's role as the universal solvent is another of its superpowers. Its polar nature makes it incredibly good at dissolving other polar and ionic substances. When you stir salt into water, the individual sodium and chloride ions are surrounded and gently pulled apart by the water molecules. This is why nutrients can travel through your bloodstream, why plants can draw minerals from the soil, and why cleaning with water is so effective. However, water is not good at dissolving nonpolar substances, like oils and fats. This is why oil and vinegar separate in salad dressing. It's also why soap is so useful. A soap molecule has a polar end that binds to water and a nonpolar end that binds to grease, allowing the oil to be carried away by the water. Inside your cells, water is the medium in which thousands of chemical reactions take place. Enzymes, DNA, and proteins all fold and function within a watery environment. Water helps to stabilize their structures, shuttle ions across membranes, and even participates directly in some reactions. Water also plays a starring role in photosynthesis, where plants use sunlight to split water molecules. The oxygen released during this process, the very oxygen you are breathing right now, comes directly from the water that plants absorb. Every breath you take is a quiet echo of water's generosity. On a planetary scale, water helps to sculpt landscapes through erosion, move heat across the globe through ocean currents, and shape our weather through the continuous water cycle. Chemically, water is stable but not inert. It can act as both an acid and a base, making it a crucial participant in maintaining pH balance in living systems. In the search for life beyond Earth, the search for liquid water is central. Water may not guarantee biology, but it seems to be a necessary ingredient. It is a solvent, a temperature regulator, a transport medium, and a reactant. It doesn't just support life, it enables it. On a personal level, you are more water than anything else. Your blood, your brain, even your bones contain water. It cushions your joints, regulates your temperature, and delivers nutrients to your cells. And yet, for all its importance, water is often overlooked. But once you begin to pay attention, it becomes clear just how strange, clever, and vital this little molecule really is. Water is a rule bender, a shapeshifter, and a quiet alchemist that holds the secrets of chemistry in a single silent drop. Matter, at first glance, seems like such a simple thing. It is the solid stuff of the chair you're sitting on, the invisible air you're breathing, and the wan liquid in the cup beside you. But beneath these everyday appearances, matter is in a constant state of motion, shifting between forms, vibrating with energy, and occasionally undergoing beautiful transformations. Understanding the states of matter is like peeking behind the curtain of physical reality, where we find a graceful dance of particles responding to the gentle cues of temperature and pressure. Traditionally, we learn of three basic states: solid, liquid, and gas. Adding plasma gives us the full classical quartet. Let's wander gently through these familiar states to see what makes them tick. We'll start with solids, the quietest of the bunch. In a solid, particles are arranged in a fixed, orderly structure, like people sitting in assigned seats in a theater. They don't have the freedom to roam, but they are not completely still. Each atom or molecule vibrates gently in its place. Solids hold their shape because the particles are tightly bound together by strong forces, resisting change until enough energy is added to loosen their grip. If you introduce heat, the particles begin to vibrate more vigorously. At a certain point, called the melting point, those vibrations become strong enough to break free from the rigid structure. The particles don't fly apart, but they begin to slip and slide past one another. The solid has become a liquid. Liquids are the social middle ground of matter. The particles are still close together, but they can now move and flow. A liquid will take the shape of its container, but maintains a fixed volume. The molecules are in constant motion, bumping into one another and rearranging themselves, but still held together by gentle intermolecular attractions. If you add more heat, the particles move faster still. Eventually, they reach the boiling point, the temperature at which they have enough energy to break free entirely and escape into the air. The liquid becomes a gas. Gases are the wild spirits of the particle world. Their particles are fast, far apart, and largely independent of one another. A gas will expand to fill any container it is in. The air in a room is made of gas particles constantly bouncing off the walls, each other, and you. Because the particles are so far apart, gases are highly compressible. You can squeeze them into much smaller spaces. But what if you keep adding energy, far beyond boiling? The gas particles can gain so much energy that the electrons are stripped away from their atoms. What you're left with is a superheated soup of charged particles, free electrons and positive ions. This is plasma, the fourth state of matter. Plasma might sound exotic, but it is the most common state of matter in the visible universe. Our sun and all the stars are giant balls of plasma. Lightning bolts and the beautiful auroras are also plasma in action. Now, let's go the other way. As you remove energy, particles slow down. A gas will cool and condense into a liquid, like dew forming on the morning grass. A liquid will slow down further and freeze into a solid, as water turns to ice. Sometimes matter can skip a step. Sublimation is when a solid turns directly into a gas without becoming a liquid first. Dry ice, frozen carbon dioxide, does this, creating a dramatic rolling fog as it vaporizes. The reverse process, deposition, is when a gas turns directly into a solid, which is how frost forms on a cold window pane. All of these transitions are phase changes. They don't alter the identity of the substance, just its form. Ice, liquid water, and steam are all still H2O. The only difference is the amount of energy their molecules have and how free they are to move. Energy is the key player here. Temperature is a measure of the average kinetic energy of particles, how fast they are moving. Pressure influences how close they are forced to be. Together, these two factors determine the state of a substance.
Ultimately, understanding these states is about recognizing that matter is always in flux. At the particle level, everything is in motion. Matter is never completely still. It is alive with energy, just moving at different speeds. There is something profoundly comforting in that. The tea cooling beside you is losing energy, its molecules slowing down, relaxing into stillness. The air in your lungs is a gas, flowing in and out with every gentle breath. All around you, matter is shifting quietly, following the timeless rules of thermodynamics, a soft rhythm unfolding endlessly in every corner of the universe. Not every combination in chemistry ends in sparks, explosions, or dramatic transformations. Sometimes things just mix. They swirl together, settle into layers, dissolve, or float, and that's that. No new molecules are formed, no bonds are broken or created. This quiet kind of chemistry, the realm of mixtures, solutions, and suspensions, is every bit as fascinating. It is the everyday blending of substances that keeps your morning tea flavorful, your salad dressing separated, and the ocean salty. A mixture is not a chemical reaction. In a reaction, atoms rearrange to form entirely new substances with new properties. But in a mixture, the components retain their original identities. They are simply sharing the same space for a while. A key hallmark of a mixture is that its components can be separated by physical means, like filtering or evaporation. Mixtures generally fall into two categories: homogeneous and heterogeneous. A homogeneous mixture is uniform throughout. You cannot see the different components. Salt water is a great example. When salt dissolves in water, the sodium and chloride ions disperse so evenly that the mixture looks just like pure water. In contrast, a heterogeneous mixture is one where the parts remain separate and visibly distinct. Think of a bowl of soup with vegetables, or a vinaigrette dressing where oil floats on top of vinegar. The components are easily identified and do not blend uniformly. A solution is a specific type of homogeneous mixture where one substance, the solute, is completely dissolved in another, the solvent. In salt water, salt is the solute and water is the solvent. Solutions can exist in any state of matter. The air we breathe is a gaseous solution of nitrogen, oxygen, and other gases. An alloy, like brass, is a solid solution of metals. But not everything dissolves. Oil and water famously resist blending because oil is nonpolar while water is polar. Water molecules would rather stick to each other, so the oil is excluded, forming a distinct layer. This brings us to another type of mixture, a suspension. In a suspension, small particles are mixed into a fluid but are not fully dissolved. These particles are usually large enough to make the mixture cloudy and will eventually settle out if left undisturbed. Muddy water or orange juice with pulp are both suspensions. They need to be shaken or stirred to remain mixed. Somewhere between solutions and suspensions lie colloids. In a colloid, tiny particles are evenly distributed but not truly dissolved. The particles are small enough that they don't settle out, but they are large enough to scatter light. Milk, mayonnaise, and fog are all colloids. They often appear homogeneous to the naked eye, but behave differently from true solutions. Your favorite salad dressing is a classic example of an emulsion, a type of colloid where oil droplets are dispersed in vinegar. On their own, they separate. But if you add an emulsifier, like mustard or egg yolk, it helps to stabilize the oil droplets, keeping the mixture creamy and unified. In the kitchen, physical changes like mixing, grinding, or melting are part of the daily chemistry of food. They change the arrangement of molecules, but not the molecules themselves. Compare that to a chemical change, like baking a cake. Here, heat causes new compounds to form as sugars caramelize and proteins denature. The result is something entirely new, and the process is irreversible. Because the substances in a mixture retain their properties, you can often separate them using simple physical methods like filtration or evaporation. Even crude oil is separated into gasoline, diesel, and other products through fractional distillation, a process that sorts substances based on their different boiling points. In nature, mixtures play essential roles. Blood is a complex suspension of cells in plasma. Soil is a heterogeneous mixture of minerals, organic matter, and water. Seawater is a solution filled with salts and gases.
And this brings us back to one of the most calming realizations in chemistry. Not everything needs to react. Sometimes things just coexist. Molecules can float alongside each other, mingle, and remain themselves. Mixtures are about balance, between blending and staying distinct, between change and stability. They remind us that chemistry isn't always about big transformations. Sometimes it's the quiet, gentle beauty of things simply coming together. Some chemical reactions happen so fast you barely notice them, a match flaring to life in an instant. Others unfold with the patience of a mountain, like ire slowly rusting over many years. Whether it's a rapid blaze or a slow decay, every chemical reaction proceeds at a certain pace. This pace is known as the reaction rate. It tells us how quickly reactants are converted into products and reveals how willing molecules are to make a change under certain conditions. One of the biggest influences on reaction speed is temperature. In most cases, increasing the temperature speeds up a reaction. Heat is energy, and when you raise the temperature, you give molecules more of it. They move faster, collide more often, and hit each other with greater force. More frequent and more energetic collisions mean more opportunities for bonds to break and new ones to form. This is why food spoils faster on a hot day and why cooking relies on heat to transform ingredients. But it's not just about bumping into each other. For a reaction to occur, molecules have to collide with enough energy to overcome the activation energy barrier. By heating a system, you increase the proportion of molecules that possess this necessary energy.
Concentration is another key factor. The more reactant particles you have crowded into a given space, the more frequently they will collide. A concentrated acid will react more quickly than a diluted one, simply because there are more reactive particles available to interact. It's like increasing your chances of finding something by looking in more places at once. Surface area also plays a powerful, if sneaky, role. For reactions involving a solid, only the particles on the surface can react. If you increase that surface area, you speed up the reaction. A single sugar cube dissolves slowly in tea, but if you crush it into a fine powder, it disappears almost instantly. The powder has a much greater surface area exposed to the water. This is why powdered substances can be so much more reactive than their solid counterparts. But sometimes, even with high temperatures and concentrations, a reaction is still naturally slow. This is where catalysts step in. As we've learned, catalysts provide an alternative pathway for the reaction with a lower activation energy. They're like taking an escalator instead of climbing the stairs. You reach the same destination with far less effort. Enzymes in our bodies are master catalysts, allowing the reactions of life to occur at an incredible speed. Light can also influence reaction rates. In some cases, photons of light provide the energy needed to initiate a reaction. This is the first step in photosynthesis, where sunlight strikes chlorophyll and triggers the cascade of reactions that create sugar. In modern chemistry, understanding and controlling reaction rates is crucial. Chemists carefully tweak conditions, adjusting temperature, pressure, and concentration, and choosing the right catalysts to find the sweet spot where a reaction is fast enough to be useful, but controlled enough to be safe. Even in cooking, you are constantly manipulating reaction rates. Browning meat involves the Maillard reaction, which happens quickly at high temperatures to create delicious flavors. Let the pan get too hot and you burn the food. Keep it too cool and it remains pale. Refrigeration, on the other hand, is all about slowing down reaction rates. The cold temperature slows down the chemical and biological processes that cause food to spoil, preserving it for longer. Some reactions are so slow on a human timescale that they seem not to be happening at all, like the geological processes that turn ancient organic matter into oil and gas over millions of years. Others are incredibly fast, like the combustion inside an engine, happening in a fraction of a second. Understanding reaction rates is about understanding time in the language of chemistry. It's recognizing that every molecule is in motion, constantly colliding and deciding whether to stay the same or become something new. The rate at which these choices unfold is influenced by the world around them. Every bubbling pot, every rusting hinge, every ripening peach is a slow ballet of molecules interacting at their own unique pace, a pace that matches the gentle rhythm of the world around them. Biochemistry is the soft-spoken cousin of big, flashy chemistry. It doesn't erupt into fireballs or fizz over in dramatic swirls. Instead, it hums gently in the background, quietly managing the countless reactions that keep you alive every second of every day. It is chemistry in a cardigan, practical, efficient, endlessly detailed, and essential in the most fundamental way. Without biochemistry, there is no heartbeat, no memory, no breath, no thought. Every blink, every yawn, every dream is powered by the tidy, tireless work of molecules behaving just right. At the heart of biochemistry are a few key players: proteins, DNA, and ATP. These molecules are the stars of the show that plays out inside every living cell. Their power comes not from showmanship, but from consistency. Life doesn't need wild reactions, it needs reliable ones. Let's start with proteins. These are the workhorses of life itself. Proteins are long chains of amino acids folded into fantastically complex three-dimensional shapes. The shape of a protein is everything. It determines its function. A protein might become an enzyme, a biological catalyst, a structural support, a transporter, or a signal messenger. Enzymes, as we've learned, are crucial for speeding up the reactions of life, allowing digestion, cell repair, and energy production to happen on a timescale that can sustain us. And what about DNA? Deoxyribonucleic acid is the grand architect of life, the molecule that stores all the instructions for building and operating an organism. It's a beautiful double helix, a twisted ladder made of just 4 kinds of chemical rungs, or bases. The sequence of these bases forms the genetic code, the blueprint for building all the proteins your body needs. But having a blueprint isn't enough. The cell needs energy to carry out the instructions, and that's where ATP comes in. Adenosine triphosphate is the molecular currency of energy. It's a small, rechargeable molecule that powers nearly every biological process. When a cell needs to do work, contract a muscle, send a nerve impulse, or build a new molecule, it spends an ATP molecule by breaking one of its high-energy phosphate bonds, releasing a burst of energy. All of these reactions and thousands more make up what we call metabolism. Metabolism is a vast, interconnected web of chemical pathways, all happening simultaneously, all finely tuned to maintain balance or homeostasis. There are catabolic pathways, which break down complex molecules to release energy, and anabolic pathways, which use that energy to build new molecules. It is a constant, balanced cycle of breaking down and building up. You can think of metabolism like a bustling city. Molecules are zooming around, being processed in factories, by enzymes, and powered by fuel stations, ATP. And somehow, through all the motion, nothing crashes. The system is exquisitely regulated by feedback loops and signaling molecules that keep everything flowing smoothly. Take glycolysis, the process that begins the breakdown of glucose to extract energy. Instead of breaking glucose down all at once in a burst of energy, the cell breaks it down in a series of 10 small, controlled steps. Each step is catalyzed by a specific enzyme, and the energy is released in manageable packets, much of which is captured in the form of ATP. This slow, steady process is far more efficient and safer for the cell. Sometimes things do go wrong. A genetic mutation might lead to a malfunctioning enzyme, causing a metabolic disorder. A misfolded protein can lead to disease. These conditions offer a glimpse into just how carefully balanced life's chemistry really is. And yet, life is also remarkably resilient and adaptable. One of the most astonishing things about biochemistry is how universal it is. The same basic processes, the use of DNA, proteins, and ATP, occur in nearly every living thing on Earth, from the simplest bacterium to the largest blue whale. Life doesn't reinvent the wheel, it refines it. Biochemistry is the chemistry of stability. While other branches of chemistry might aim for speed or transformation, biochemistry is all about sustainability. It's how life takes a humble pile of atoms into movement, thought, feeling, and memory. And it does so without exploding, which, when you think about it, is truly incredible. You are made of atoms that follow the same rules as those in rocks and stars, but in you, they assemble and react in ways that produce not just order, but consciousness. You don't feel it, you don't hear it, but it's there, a molecular symphony playing just beneath your awareness. a whispering choreography of proteins, enzymes, and tiny sparks of ATP, all working together in the quiet dark to keep the lights on and the gears turning. At the heart of biochemistry are a few key players: proteins, DNA, and ATP. These molecules are the stars of the show that plays out inside every living cell. Their power comes not from showmanship, but from consistency. Life doesn't need wild reactions, it needs reliable ones. Let's start with proteins. These are the workhorses of life itself. Proteins are long chains of amino acids, folded into fantastically complex three-dimensional shapes. The shape of a protein is everything. It determines its function. A protein might become an enzyme, a biological catalyst, a structural support, a transporter, or a signal messenger. Enzymes, as we've learned, are crucial for speeding up the reactions of life, allowing digestion, cell repair, and energy production to happen on a timescale that can sustain us. And what about DNA? Deoxyribonucleic acid is the grand architect of life, the molecule that stores all the instructions for building and operating an organism. It's a beautiful double helix, a twisted ladder made of just 4 kinds of chemical rungs, or bases. The sequence of these bases forms the genetic code, the blueprint for building all the proteins your body needs. But having a blueprint isn't enough. The cell needs energy to carry out the instructions, and that's where ATP comes in. Adenosine triphosphate is the molecular currency of energy. It's a small, rechargeable molecule that powers nearly every biological process. When a cell needs to do work, contract a muscle, send a nerve impulse, or build a new molecule, it spends an ATP molecule by breaking one of its high-energy phosphate bonds, releasing a burst of energy. All of these reactions and thousands more make up what we call metabolism. Metabolism is a vast, interconnected web of chemical pathways, all happening simultaneously, all finely tuned to maintain balance or homeostasis. There are catabolic pathways, which break down complex molecules to release energy, and anabolic pathways, which use that energy to build new molecules. It is a constant, balanced cycle of breaking down and building up. You can think of metabolism like a bustling city. Molecules are zooming around, being processed in factories, by enzymes, and powered by fuel stations, ATP. And somehow, through all the motion, nothing crashes. The system is exquisitely regulated by feedback loops and signaling molecules that keep everything flowing smoothly. Take glycolysis, the process that begins the breakdown of glucose, sugar, to extract energy. Instead of breaking glucose down all at once in a burst of energy, the cell breaks it down in a series of 10 small, controlled steps. Each step is catalyzed by a specific enzyme, and the energy is released in manageable packets, much of which is captured in the form of ATP. This slow, steady process is far more efficient and safer for the cell. Sometimes things do go wrong. A genetic mutation might lead to a malfunctioning enzyme, causing a metabolic disorder. A misfolded protein can lead to disease. These conditions offer a glimpse into just how carefully balanced life's chemistry really is. And yet, life is also remarkably resilient and adaptable. One of the most astonishing things about biochemistry is how universal it is. The same basic processes, the use of DNA, proteins, and ATP, occur in nearly every living thing on Earth, from the simplest bacterium to the largest blue whale. Life doesn't reinvent the wheel, it refines it. Biochemistry is the chemistry of stability. While other branches of chemistry might aim for speed or transformation, biochemistry is all about sustainability. It's how life takes a humble pile of atoms and turns it into movement, thought, feeling, and memory. And it does so without exploding, which, when you think about it, is truly incredible. You are made of atoms that follow the same rules as those in rocks and stars, but in you, they assemble and react in ways that produce not just order, but consciousness. You don't feel it, you don't hear it, but it's there, a molecular symphony playing just beneath your awareness, a whispering choreography of proteins, enzymes, and tiny sparks of ATP, all working together in the quiet dark to keep the lights on and the gears turning. The Earth may seem like a solid, steady place, a big rock floating through space,
But beneath its surface and above its clouds, our planet is a restless, dynamic chemical system. It breathes, cycles, and changes constantly. The mountains erode, the oceans shift, and deep below, molten rock simmers in silence. From its churning core to its icy poles, the Earth is always reacting. Geochemistry is the study of this planetary scale chemistry, the story of rocks, water, and gases over vast stretches of time. Let's start deep underground. The Earth's interior is a hotbed of elemental drama. A core of iron and nickel is surrounded by the mantle, a thick layer of semi-molten rock that churns in slow-motion convection currents. These currents drive plate tectonics, causing the continents on the thin crust above to drift, collide, and slide past one another. Volcanoes are one of the most striking examples of geochemistry in action. Magma from deep within the Earth contains dissolved gases like water vapor and carbon dioxide. As the magma rises and the pressure drops, these gases bubble out of solution, like opening a shaken can of soda. These expanding gases can drive explosive eruptions, hurling ash, rock, and lava into the air. But these eruptions also play a vital role in cycling elements. The gases contribute to the atmosphere, and the minerals in the lava slowly break down, enriching the soil. Once those volcanic rocks are on the surface, they begin a new chapter: weathering. Weathering is the gradual breakdown of rocks. Chemical weathering occurs when water, oxygen, and acids interact with the minerals in the rock. For instance, rainwater is naturally slightly acidic because it absorbs carbon dioxide from the atmosphere, forming weak carbonic acid. Over thousands of years, this gentle acid can dissolve entire limestone formations, carving out vast caves and intricate underground rivers. It is chemistry with immense patience. One drop at a time, it transforms mountains into sediment. The dissolved ions released by weathering make their way into rivers and eventually the oceans. This is why the oceans are salty. These ions also provide essential nutrients for marine life. Calcium and carbonate ions, for example, are used by corals and shellfish to build their calcium carbonate shells. When these organisms die, their shells sink to the ocean floor, eventually becoming compacted into limestone rock. This is a key part of the carbon cycle. The carbon cycle is one of the most important chemical cycles on our planet. Carbon moves between the atmosphere, oceans, land, and living things in a complex, interconnected loop. Photosynthesis pulls CO2 from the air. Respiration and decomposition release it back. The burning of fossil fuels releases carbon that was buried for millions of years. The ocean absorbs huge amounts of CO2 from the atmosphere. It's a grand planetary cycle with a very real influence on our climate. The atmosphere itself is a reactive soup of gases. The ozone layer in the upper atmosphere protects us from harmful UV radiation. Greenhouse gases like carbon dioxide, methane, and water vapor trap heat, keeping our planet warm enough for life to exist. The balance of these gases is delicate and is what determines our global climate. Through all of this, the Earth behaves less like a static ball of rock and more like a single integrated system with feedback loops and self-regulating processes. The composition of the atmosphere affects the temperature, which affects the rate of weathering, which affects carbon levels in the ocean, which then loops back to influence the atmosphere again. It's chemistry with memory, cause, and consequence. We are not separate from this planetary chemistry, we are a part of it. The atoms in our bodies are borrowed from these great geological cycles. The calcium in your bones was once part of a rock. The nitrogen in your DNA may have been fixed by lightning in a prehistoric sky. And the carbon you exhale will one day be food for a tree. So when you step outside and feel the breeze or watch the clouds drift by, know that you are witnessing chemistry in its slow, magnificent stride. The Earth is not just a place we live, it is a vast, breathing laboratory of elements in perpetual, silent motion. Chemistry isn't just something that happens on Earth. It also unfolds in the great, open silence of space, between the stars, inside of them, and in the long, cold stretches where barely anything seems to move.
Out there, where gravity reigns and light takes millions of years to travel, chemistry is hard at work, shaping galaxies, planets, and even the very atoms in your body. It is a slower, more cosmic kind of chemistry, but it follows the same fundamental rules. Let's start in the most dazzling laboratories of all, stars. These enormous balls of plasma are powered by nuclear fusion, a process where lighter elements, like hydrogen, are crushed together by immense gravity and heat to form heavier elements, like helium. This process releases the vast energy that makes stars shine. But fusion is also a form of elemental alchemy. In the cores of massive stars, the process continues. Helium fuses into carbon, carbon into oxygen, and so on, building up heavier and heavier elements in layers, like a cosmic onion. This continues until iron is formed. Fusing iron consumes energy rather than releasing it. At this point, the star can no longer support its own weight. Gravity wins, and the star collapses in on itself, triggering a spectacular supernova explosion. In the heart of that explosion, for a brief, brilliant moment, all the elements heavier than iron are forged: gold, platinum, uranium, and more. All of this material is then hurled out into space, seeding the cosmos with the raw ingredients for new stars, new planets, and eventually, life. It is not just poetic to say that we are made of stardust, it is a chemical fact. The carbon in your muscles and the calcium in your bones were born in the hearts of stars that lived and died long before our solar system ever formed. Between the stars lies the interstellar medium, filled with vast, cold clouds of gas and dust called nebulae. These are the stellar nurseries where new stars are born. Within them, atoms and molecules drift, collide, and sometimes stick together on the surfaces of tiny dust grains. Gravity slowly pulls denser regions of these clouds together, forming new stars. Even in these frigid, near-vacuum conditions, complex chemistry occurs. Astronomers have detected over 200 different molecules in space, including water, ammonia, and even simple organic molecules like alcohols and sugars. These are the prebiotic building blocks of life, suggesting that the raw ingredients for biology might be widespread throughout the galaxy. As stars age, they recycle their matter back into space, enriching the interstellar medium with the heavier elements they created. This cosmic recycling is how the universe has grown more chemically diverse over time. Closer to home, the atmospheres of the planets in our solar system showcase their own unique chemistry. Venus has a thick atmosphere of carbon dioxide with clouds of sulfuric acid. The gas giants, Jupiter and Saturn, have swirling clouds of ammonia and methane, and Saturn's moon Titan has lakes of liquid hydrocarbons on its surface. Even comets, icy wanderers from the outer solar system, are frozen time capsules of the solar system's early chemistry, containing water, carbon dioxide, and organic compounds. In the growing field of exoplanet research, astronomers are now able to analyze the light passing through the atmospheres of distant planets to detect their chemical fingerprints, searching for signs of water, oxygen, and other potential biosignatures. All of this reminds us that chemistry is the universal language. Atoms come together, break apart, and reassemble across billions of years and billions of miles. You are not separate from that story. You are a chapter in it. The iron in your blood and the oxygen in your breath were all forged in stars, passed through the cold of interstellar space, and woven into the living being that is you. The chemistry that built you also built the galaxies. So when you look up at the night sky, you are seeing a reflection of yourself scattered across the stars. Even in the quietest moments, chemistry is never truly still. A cold cup of tea, a breath drawn in the dark, the gentle creak of wood in a settling room. Beneath it all, atoms are in motion. Molecules shift, electrons dance, and forces balance. It is a rhythm far too small for us to see and far too constant for us to hear, but it is there, all the same.
every moment, every object, every part of you is held together and changed by the slow, steady, and sometimes spectacular poetry of chemistry. Over the course of this journey, we have wandered through the vast and varied world of matter, from the tiniest atom to the fires of distant stars, from the slow rust on a garden gate to the lightning-fast reactions inside your cells. We have seen chemistry move with speed and sound, but we have also explored the calm chemistry, the kind that unfolds with immense patience, weathering stone, dissolving sugar, or folding a protein with exquisite precision. We began with the atom, the smallest building block, full of character. We followed the elusive electrons and saw how their drive for stability leads to the formation of bonds, giving rise to the endless diversity of the world. We explored how energy drives reactions, how catalysts can offer a gentle shortcut, and how acids and bases change the mood of a solution. We watched matter shift through its states: solid, liquid, gas, and plasma, each revealing a different kind of motion and freedom. We saw that not everything needs to react. Sometimes things just mix. We explored the quiet, tireless chemistry of life inside our own bodies, where proteins, DNA, and ATP perform a silent symphony. And finally, we stepped beyond ourselves, into the chemistry of the Earth and the cosmos, finding our own origins in the hearts of dying stars. What all of this reminds us is that matter is never dull. It may appear motionless, but at the microscopic level, it is always humming with invisible action. Stillness, it turns out, is full of life. There is something profoundly comforting in that thought. We live in a world that often values speed and spectacle, but chemistry tells us that slow, quiet change is just as powerful and often more lasting. Behind every one of these reactions is a story, a tiny narrative about atoms wanting to be stable and systems seeking equilibrium. It is a chemistry not just of things, but of tendencies and probabilities. The periodic table is not just a list, it is a cast of characters, each with its own quirks and preferences. The chemistry of water is the chemistry of your blood. The chemistry of carbon is the chemistry of your thoughts. The chemistry of light is the chemistry of sight. It is not separate from us. It is us. So as we come to the end of this journey through the chemistry of nearly everything, I hope you have felt the wonder that lies just beneath the surface of the everyday. I hope this has been interesting, but not so interesting that it has kept you from your rest. If you are still peacefully listening with your eyes closed, I would love to know where in the world you are tuning in from. What time is it where you are? Are you curled up in bed or on the couch with a pet? Let me know in the comments. I love hearing where this chemistry journey has taken you. And if you enjoyed this exploration, if you found it relaxing or gently thought-provoking, please consider giving this video a like or subscribing to the channel. It helps me bring more of this content to you and lets me know that these gentle dives into science are bringing a little more wonder into the world. Thank you so much for being here and for joining me in this quiet celebration of how the universe works, one invisible reaction at a time. And remember, even when nothing seems to be happening, chemistry is always happening. The atoms are still dancing, the molecules are still mingling, and the world, even in perfect stillness, is still beautifully, endlessly alive. Good night. Hello there, and a very warm, very quiet welcome to the Midnight Scientists. I am so glad that our paths have crossed here, in this peaceful sanctuary, in this soft moment, suspended perfectly between the day that was and the night that is now beginning to unfold. Wherever you are in the world, whatever kind of day you have carried on your shoulders, I invite you now to gently, lovingly set it all down. There is no need to carry it any further tonight. Perhaps your day was long and filled with challenges, and your mind is now seeking a soft, quiet place to land. Or perhaps you are simply the kind of soul who finds a deep and abiding comfort not in the quiet spectacle of counting sheep,
but in the silent, grand spectacle of counting stars, of pondering the deep, unspoken mysteries of the cosmos as you drift towards the beautiful mystery of dreams. Either way, you have found your way to the right place. This journey is for you. There is nothing left to do now, nothing to solve, nothing to plan, nothing to hold on to. The only task before you is to allow yourself to rest. Let your mind begin to relax, feeling the tight edges of the day begin to soften and blur. Begin to feel your breathing slow, finding its own natural, easy, and gentle rhythm. Notice the quiet rise of your chest on the in-breath and the soft, complete release on the out-breath. A quiet tide coming in and going out. Feel your body grow a little heavier now, a little warmer, as you sink ever deeper into the surface that supports you. Imagine just for a moment that gravity itself has softened its hold on you, allowing you to feel both grounded and wonderfully light all at the same time. Because tonight, we are not just stargazing from a distance, looking up at a faraway sky. Tonight, we are going to drift. We will travel together gently and without effort through the very heart of our magnificent cosmic home, our own galaxy, the Milky Way. Try to imagine it in your mind's eye, a vast, breathtaking spiral of over 100 billion stars, each one a sun, each one a potential center of a forgotten solar system, all of them turning together, slowly, silently, in the deep velvet darkness of space. This structure is so ancient, it has been turning for over 13 billion years, a cosmic dance that began not long after the dawn of time itself. But beneath its serene and shimmering beauty, it holds the deepest of secrets. Tonight, we will hear of rogue stars, flung from the galactic heart like golden embers from a great cosmic fire. We will learn of the vast, invisible forces that hold everything together, and of the ancient, ghostly remains of other galaxies long since devoured that still haunt our own. We will travel gently from the swirling, star-dusted arms, where new suns are being born right now, to the secretive and mysterious hidden core where a sleeping giant resides. We will witness colossal collisions that unfold not in an instant, but over billions of years, a slow-motion ballet of creation. And we will meet stars that are so ancient, they're older than the galaxy itself. This is the strange, unfinished, and profoundly beautiful story of a galaxy that is still growing, still changing, still becoming. Some of what you hear tonight may surprise you. It may spark a gentle sense of wonder, a quiet curiosity that you can hold on to as you drift ever deeper into a peaceful and restorative sleep. And just before we begin our journey in earnest, a gentle invitation. If you find that these calm, curious explorations help you to unwind or offer you a quiet way to end your day, please do consider giving this video a soft little like and subscribing to the channel. It is a small, silent gesture that helps other sleepy explorers just like you find their way to this quiet corner of the cosmos, one sleepy soul at a time. And if you feel so inclined, I would love to know where in the world you are listening from tonight and what time it is for you in this very moment. It is always such a joy to imagine this shared stillness stretching out across all the world's time zones, connecting us all in this moment of collective peace. Now, let the day and all its concerns fall away completely. Let the noise of the world fade into a soft, distant hum. Let us begin. Our galaxy, the Milky Way, may feel like a vast, stable, and eternal home, When we look up, we see a quiet island of stars in an endless ocean of space. It feels permanent. It feels like ours. But in truth, our galaxy is a survivor. It is a composite. It is a grand and beautiful structure built from the luminous wreckage of others. Over the immense, slow-motion timescale of cosmic history, the Milky Way has achieved its grand size by consuming its neighbors. For billions of years, it has been drawing smaller, dwarf galaxies into its gravitational embrace. And once they are caught, they begin a long, slow process of unraveling, like a spool of shimmering silver thread being gently unwound. The stars of these captured galaxies are pulled from their original orbits and scattered, joining the great swirling dance of our own. But they do not just vanish into the crowd. For a long time, they traveled together in what are known as tidal streams. Imagine long, ghostly, and almost invisible ribbons of stars wrapping around and through our galaxy's bright disk. These streams are the last, faint signature of a galaxy that once was, tracing the path of its final, looping orbits like a beautiful memory written in starlight across the sky. Our galaxy is haunted by these graceful, silent ghosts. This process is not just a relic of the distant past. It is happening right now. A small galaxy, known as the Sagittarius dwarf spheroidal galaxy, is currently in the slow, final stages of being pulled apart by the Milky Way's gravity. We can see its stars being stripped away one by one, woven into the very fabric of our own galactic home. It is a silent, graceful collision, a cosmic ballet that has been unfolding for millions upon millions of years. When we learn to see our galaxy in this way, we are looking at a living history of these quiet conquests. The Milky Way is not a pristine, solitary spiral. It is a grand mosaic, a breathtaking tapestry stitched together from the shining, luminous remains of 1,000 smaller, forgotten worlds.
This long and quiet history of cosmic consumption helps to explain one of the galaxy's most beautiful and profound paradoxes. Some of the stars that currently reside within the Milky Way are actually older than the Milky Way itself. Think about that for a moment. Not every star that shines in our sky was born here. Drifting high above and far below the main, flat, bustling disk of the galaxy, in that vast, spherical, and mostly empty region we call the halo, there are ancient, wandering stars. They move on their own terms, following long, slow, and highly tilted orbits that are completely different from the organized, circular paths of younger stars like our Sun. These are the galaxy's elders. When astronomers are able to capture the faint, ancient light from these lonely halo stars and study their composition, they find that their chemical fingerprints are incredibly, beautifully pure. They are made almost entirely of the original elements forged in the fire of the Big Bang: hydrogen and a little bit of helium. They contain almost no heavy elements, what astronomers refer to as metals. This is a crucial clue. It tells us that these stars were born in a universe that had not yet had time to create the heavier elements that make up planets and moons, and even the very substance of our own bodies. They were born before the great cosmic forges inside of stars had seeded the universe with the building blocks of complexity. These stars are therefore ancient relics, true fossils of light, formed shortly after the dawn of time itself, even before the Milky Way had fully gathered its gas and dust and settled into its now familiar, graceful spiral shape. Astronomers believe, with a high degree of certainty, that these stars could not have formed within our galaxy. They must have originated in much smaller, primordial galaxies, the very first tiny star systems to coalesce out of the primordial darkness.
These small, fragile galaxies were then the first to be swallowed whole by our own, much larger galaxy as it began to grow and assert its gravitational dominance. And so they continue their journey. They move slowly, these ancient suns, high above the busy galactic plane, like quiet elder spirits from a time before order, a time before spirals. In their faint, ancient, and beautifully preserved light, we are seeing a direct glimpse of a universe that was younger, wilder, and still learning how to become the cosmos we know and inhabit today. There is a profound and peaceful illusion that comes whenever we look up at the night sky. The stars feel fixed, eternal, like tiny perfect silver pins holding up the great velvet fabric of the night. But this apparent stillness is only a trick of the immense, unimaginable distance that separates us from them. In truth, everything is in constant, graceful, silent motion. Our solar system, our beautiful Earth, and you, resting here right now, are all participants in this grand cosmic current, this great, silent river of stars. Right now, you are hurtling through the galaxy at a speed that is almost impossible for the human mind to truly comprehend. We are traveling at over 828,000 kilometers per hour. That is more than 230 kilometers for every single second that passes. Imagine a speed that could carry you from one side of a vast continent to the other in the time it takes you to draw a single, slow, and peaceful breath. And yet, you feel nothing of this incredible velocity. You feel only the stillness of your room, the quiet weight of your blanket, the gentle rise and fall of your own breathing. The galaxy is so vast, so utterly immense, that even at this breathtaking speed, it takes our solar system about 225 million years to complete just one single loop around the galactic center. This immense, slow journey is called a galactic year. Pause for a moment and consider that. In the entire 4.5 billion year history of our planet, from its molten birth to this very quiet moment, we have only made this grand circle around the galaxy about 20 times. When the very first dinosaurs began to walk the Earth, our solar system was on the complete opposite side of the Milky Way, drifting through an entirely different neighborhood of stars, a sky that would have looked completely alien to us. The familiar constellations that we see today were not the same constellations they saw. The stars that feel like our celestial neighbors now were once distant strangers to our world, and in the deep future, they will be again. Nothing is permanent. Everything is drifting. There is a deep and abiding comfort in this knowledge. Even as you lie here perfectly still, preparing for sleep, you are on the most magnificent journey imaginable. The Earth gently turns, the moon faithfully circles, and the entire solar system sweeps forward in a great, silent, and beautiful arc through a galaxy that is itself in constant, wonderful motion. You are a traveler through the cosmos, even in your deepest rest.
And this ancient galaxy we travel through, it is not a finished work. It is not a static, crystallized relic from the distant past. Although the Milky Way is ancient, its story is far from over. Even now, in this very moment, as you rest and breathe, it continues to grow. It continues to gather new material from the space around it, like a great slow river patiently widening its banks over millennia. It breathes. In a slow, cosmic inhalation that takes millions of years, it gently pulls in vast, cool, and pristine clouds of hydrogen gas from what is known as the intergalactic medium. These are the tenuous, almost invisible threads of the cosmic web that stretch between all the galaxies, the raw original material left over from the dawn of time. This gas flows into our galaxy in long, slow streams, replenishing the material needed for future generations of stars. it also continues to feast upon its smaller neighbors. It captures stray stars from the dwarf galaxies it is currently consuming, adding their light to its own, and it draws in long, completely invisible streams of dark matter, which feed and expand its enormous unseen halo, strengthening the very gravitational foundation upon which the entire galaxy is built. The Milky Way grows not like a living thing with a conscious plan, but like a grand gravitational structure, deepening and settling and expanding over the eons, guided by the patient, persistent laws of physics. Sometimes this growth is quiet and almost imperceptible, a gentle infilling of cosmic clouds that drifts in almost unnoticed. Other times, it comes with a beautiful and slow disruption as satellite galaxies are finally torn apart, their stars scattered across the sky like luminous seeds sown by the hand of gravity. The galaxy you live in today is not the same one that the dinosaurs looked up at from a forgotten ancient world, and the one that your distant, unimaginable descendants may one day know could be larger and even more luminous still. A new structure, stitched together from the shining ruins of 1,000 other smaller worlds. This constant, slow state of change and evolution might help to explain why we struggle with a question that seems, on the surface, like it should be simple. How many spiral arms does the Milky Way actually have? It feels like something we should know with certainty about our own home. But from our position, nestled deep inside one of its smaller arms, it is incredibly difficult to see the whole structure clearly. Imagine trying to draw a map of a vast and ancient forest while standing in the very middle of it. The nearest trees, the trunks and branches right in front of you, would block your view of the wider landscape. A thick fog might drift between the trees, obscuring the more distant groves. You could guess at the overall shape, but you could never be entirely sure. For us, the nearby stars are those trees, blocking our line of sight, and the fog is the great, dark clouds of intrastellar dust that drift between the stars. These clouds, made of minuscule grains of carbon, silicates, and ice, are incredibly effective at absorbing and scattering starlight, creating a cosmic veil that hides the heart of our galaxy and its most distant arms from our view. For decades, astronomers pieced together the clues and believed our galaxy had 4 major grand spiral arms. But more recent and detailed observations have painted a much more complex and perhaps more interesting picture. Using infrared and radio telescopes, which can peer through the cosmic dust like a special kind of sight, we have learned that the structure is not so simple. Perhaps the current thinking goes, there are only 2 dominant primary arms that emerge from the great central bar of the galaxy. The other arms we thought we saw may be smaller, splintered fragments or secondary branches that are less dense and luminous. Perhaps the arms we see twist and split in ways we never expected. Some seem to fade away into faint, fragmented wisps, while others wrap around the core in unexpected ways. The Milky Way may not be a neat, perfect geometric pinwheel. It may be a living, layered, beautifully messy and organic swirl of stars sculpted by the complex forces of gravity and motion over billions of years. Its true and complete shape remains one of its most alluring and gently held secrets. The greatest secret of the spiral arms is that they are not solid structures. The arms are not made of the same stars moving together like horses on a carousel. If they were, the inner parts would rotate faster than the outer parts, and the beautiful spiral pattern would wind itself up and disappear in just a few 100 million years. Instead, the spiral arms are a beautiful illusion. They are a pattern, a ripple of higher density moving slowly through the galactic disk. The best way to imagine it is to think of a traffic jam on a great circular highway. The cars on the highway are the stars and the vast clouds of gas, each moving at its own speed. The traffic jam is the spiral arm. It is an area where, for gravitational reasons, the flow of traffic slows down and becomes much more dense. The cars enter the jam, slow down and bunch up for a while, and then eventually emerge out the other side, speeding up again to their normal pace. The jam itself, the pattern of density, moves slowly around the highway, but it is not made of the same cars all the time.
This is precisely what happens in our galaxy. The spiral arms are a density wave, a slow-moving pattern of compression. Stars and, more importantly, the great clouds of interstellar gas drift into these arms. As the gas clouds enter this cosmic traffic jam, they are gently but powerfully squeezed. This compression is the gentle nudge that gravity needs to begin its work. It triggers the collapse of the gas, beginning the beautiful and complex process of creating new stars. This is why the spiral arms are so bright and so prominent. They are the galaxy's great construction zones, constantly lit up by the brilliant, hot, and intensely blue light of newborn suns that have only just ignited. A star like our sun will drift into an arm, spend many millions of years traveling through that bright, dense, and beautiful region, and then it will eventually emerge from the other side, continuing its quiet, solitary journey through the darker space between the arms until its orbit eventually brings it to the next one. The arms are not a place, they are a phenomenon, a slow, graceful, and self-sustaining ripple, forever turning and forever creating. Most stars drift calmly through the galaxy, held in these long, slow orbits by the gentle, persistent, and collective pull of gravity. They are part of a great, orderly, and predictable river of light. But a rare few, a very rare few, are thrown from this river with astonishing and irrevocable violence, flung outward into the great void at speeds so great they can escape the pull of the Milky Way entirely. These are the hypervelocity stars, cosmic exiles on a one-way journey into the great, dark, and silent ocean that lies between the galaxies. Many of them begin their lives in a common arrangement, a binary pair, two stars born together, locked in a close and stable gravitational dance, orbiting each other for millions or even billions of years. But if their long, looping orbit through the galaxy happens to take them on a fateful path, a path that brings them too near the supermassive black hole at the very center of our galaxy, their eternal dance can come to a sudden and brutal end. The black hole's immense gravity can reach out and capture one of the stars, pulling it violently from its partner and into an inescapable spiral from which it will never, ever return. As that poor star falls inward and vanishes from the known universe, all of its immense orbital energy and the energy of its lifelong partnership is transferred to the surviving star in a single catastrophic instant. The surviving star is slingshotted outward, hurled into the darkness at over 1,000,000 kilometers per hour, a speed that dwarfs the normal motion of the stars. It travels alone now, its trajectory carrying it up and out of the bright, flat plane of the galaxy, far from the light and company of its kin. It is like a single glowing ember shot from a dying fire, a silent, lonely comet with no return path. These rogue stars are a stark and beautiful reminder that even in a galaxy that feels so orderly, a galaxy bound by the predictable laws of gravity, there are moments of profound and violent release. Quiet, sudden, and final expulsions that send entire suns flying into the endless, silent, intergalactic night. And there are other wanderers too. Stars that do not follow the established rules of the Great Galactic River. While the vast, overwhelming majority of stars in the Milky Way orbit the galactic center in the same general direction, forming a gentle, collective clockwise swirl, some stars stubbornly move against the current. These are the retrograde stars,
They orbit backward, moving in the opposite direction to the galaxy's main rotation. This strange and defiant behavior is a quiet but unmistakable signature of a foreign origin. It is a kind of celestial accent, revealing that these stars were not born here. They likely arrived from somewhere else entirely, born in much smaller dwarf galaxies that were later captured and gravitationally consumed by the much larger Milky Way. Imagine their small home galaxy orbiting ours at a completely different angle. When that home galaxy was finally and completely torn apart by the Milky Way's tides, its constituent stars were thrown into new, often highly tilted and sometimes completely reversed orbits within our own. Their backward motion is a living fossil. It is a quiet memory of an ancient merger, a story preserved not in stone or in light, but in the slow, patient, and lonely turning of a star against the great cosmic stream. It is as if the galaxy in its very motion still carries the faint ghostly memories of the worlds it has consumed, and these stars are the keepers of that silent, kinetic history. And this grand story of galactic collisions, of mergers and consumption, is not over. It is not just a tale of the past, it is also a prophecy of the future. High above the horizon, on a clear, dark, moonless night, far from the lights of any city, you can just barely see a faint, fuzzy, and elongated patch of light in the constellation for which it is named. This is the Andromeda Galaxy. It is a great and magnificent spiral, in many ways a larger sibling to our own Milky Way, containing perhaps 1,000,000,000,000 stars. It lies over 2 million light-years away, an almost incomprehensible distance. And yet, for all that immense empty space that separates us, it is moving steadily, silently, and inexorably towards us. In about 4.5 billion years, a span of time longer than our Earth has even existed, the Milky Way and Andromeda will meet. They will collide. But this will not be a violent crash in the way we might imagine on a human scale. Space is so profoundly vast and the distances between individual stars are so immense that it is almost certain that no two individual stars will ever actually hit each other. Our sun and its planets will likely drift through the encounter completely unscathed. Instead, it will be a slow, majestic, and breathtakingly elegant dance of gravity, unfolding over hundreds of millions of years. As the two great galaxies first pass through one another, their immense, interlocking gravitational forces will warp and stretch them into long, curving, beautiful arcs of stars. Great tidal tails, hundreds of thousands of light-years long, will be drawn out and will curl gracefully into the surrounding space. The supermassive black holes at their centers will begin a long, slow inward spiral towards one another, a dance that will take eons to complete. After billions more years of this graceful, cosmic weaving and intertwining, the two formerly separate spiral galaxies will finally settle and merge and become a single, larger, more rounded and more golden system, a new galaxy, an elliptical galaxy, which some astronomers have already named Milkomeda. This is the future of our home, written in the slow approach of that faint fuzzy light in our night sky. A slow, quiet merger, a dance of creation born from a gentle cosmic collision. It is a soft and profound reminder that even galaxies are not eternal. They evolve, they collide, they are born again. Every single star that shines in the night sky is a messenger from the past. Its light has traveled for years or centuries or millennia to reach your eyes in this very moment. But that ancient light carries more than just an image of a distant sun. It carries a story. It carries a detailed chemical fingerprint that reveals the time, the place, and the circumstances of that star's birth. When astronomers look at the faint light from a single star through an instrument called a spectroscope,
That light is spread out into a beautiful, shimmering rainbow, a spectrum. And woven into that spectrum, like a secret code, are tiny, dark, vertical lines. These are absorption lines. Each line corresponds to a specific chemical element present in the star's hot atmosphere, an element that has absorbed its own unique and specific frequency of light, leaving a tiny missing note in the grand symphony of color. By reading these lines, we can read a star's entire history. Some stars, like our own sun, are rich in a wide variety of heavy elements like iron, oxygen, silicon, and calcium. This tells us that they are relatively young, cosmically speaking. They were formed in dense, dusty regions of the galaxy where the raw material of their birth, the great clouds of gas, had already been enriched by the explosive deaths of many, many previous generations of stars. But other stars, especially those ancient, lonely wanderers in the great outer halo, are almost pure. Their light tells a very different story. They are made of almost nothing but pristine hydrogen and helium. They are what we call metal poor, because they were born in a much younger, cleaner universe, before the great cosmic forges inside the hearts of countless stars had time to create the heavier elements that make up worlds and that make up us. The very first stars in the universe were the true giants, and they lived fast and died young, exploding and seeding the cosmos with the first generation of heavy elements. The elder stars we see in our halo today were the next generation, born from gas that was only lightly seasoned with these new ingredients. And our sun, a star of a much later generation, was born from gas that had been enriched time and time again over billions of years. These differences in chemistry allow scientists to group stars into great cosmic families, to uncover the ghostly trails of ancient galactic mergers, and to patiently reconstruct the hidden, layered story of how the Milky Way was built. In this way, the light of a star becomes a kind of quiet time machine. It allows us to read its distant past like a line of ancient poetry, written not in ink, but in pure, shimmering, and beautifully preserved light. And yet, for all that we can learn from the light of the stars, the greatest mystery of our galaxy is held in what we cannot see at all. By all the laws of physics that we understand, the Milky Way should not exist as it does. In the 1970s, astronomers began to carefully measure the speed of the stars in the outer regions of our galaxy, and they found something deeply puzzling, something that defied all expectations. The stars on the outer edges were moving far, far too fast. Imagine a great spinning merry-go-round. The horses near the center move slowly, but the ones on the very edge have to travel much faster to keep up. If you spin it too quickly, the outer horses will be flung off by centrifugal force. The same should be true for our galaxy. Based on all the visible matter we can see, all the billions of stars, all the vast clouds of gas and dust, the gravitational pull of the galaxy should not be strong enough to hold on to these speeding outer suns. They should be flung off into the darkness of intergalactic space, scattered like sparks from a spinning wheel. Our galaxy should have flown apart billions of years ago. And yet here it is. Here we are. The stars remain. The galaxy holds its beautiful, stable, spiral shape. The only way this is possible is if there is something else out there, something massive, something pervasive, and something completely invisible, providing the immense extra gravity needed to hold it all together. This mysterious and unseen substance is what we now call dark matter. It does not shine, it does not reflect, it does not absorb or block any form of light. It passes through the ordinary matter of our world, through this room, through you, as if it were a ghost. But it exerts gravity, and there is so much of it that it appears to outweigh all the visible luminous matter in the galaxy many times over. We do not yet know what dark matter is. It remains one of the greatest and most profound mysteries in all of science. But we know with near certainty that without it, our galactic home would simply cease to exist. It is the invisible scaffolding that holds the cosmos in place, the silent, unseen foundation that gives our galaxy its structure and its stability. A quiet, gravitational ghost holding our entire starry city together from the outside in. Let us drift now, in our minds, on a slow and peaceful journey toward the very center of our galaxy. We leave behind the calm and quiet suburbs of the Orion Spur, where our own sun makes its home. We move inward through the denser, more crowded lanes of stars, where the sky would begin to change dramatically. The darkness between the stars would begin to shrink, replaced by a profound golden glow. The stars here are older, more ancient, and packed together in a luminous, shimmering sea. We're approaching the great central hub of our starry city, a place of immense gravitational power and ancient light. But as we draw closer, a great veil appears before us. Thick, dark, and impenetrable curtains of interstellar dust and gas, so dense that they completely block the visible light from the very heart of the galaxy. To our eyes, the center is forever hidden, shrouded in a deep and profound mystery. But with other kinds of sight, with telescopes that can see in radio waves and infrared light, we can peer through this veil and witness the wonders that lie within.
At the very center of it all, the gravitational anchor point around which every star in the Milky Way orbits, lies an object of almost unimaginable power and density, a singular, perfect point of gravity from which nothing, not even light, can escape. This is the Milky Way's supermassive black hole, a quiet giant that astronomers have named Sagittarius A*. It contains the mass of more than 4 million suns, all of it compressed by its own immense gravity into a space smaller than the orbit of the planet Mercury. We cannot see it directly, of course. It is a perfect spherical darkness against the backdrop of the glowing gas and stars that surround it. But we know with absolute certainty that it is there. For decades, astronomers have been patiently watching the stars that orbit closest to this central point. They have tracked their frantic high-speed movements year after year. These stars, like one named S2, perform a breathtaking cosmic ballet, whipping around an invisible partner at tremendous speeds, some reaching several % of the speed of light. They trace tight, precise, invisible loops through the void, and by mapping these orbits, we can calculate the exact mass and location of the unseen object they are dancing with. Sometimes a cloud of gas or a stray, unlucky star will drift too close, and as it is pulled inward by the immense tidal forces, it will be stretched and heated, flaring with a brilliant and sudden flash of X-rays before it spirals over the edge of the event horizon and disappears from our universe forever. A final, silent whisper before it is gone. For now, Sagittarius A* is mostly quiet. It sleeps. But there is growing evidence that billions of years ago, it was a far more violent and active entity. It may have feasted on much more gas and dust, burning with the brilliant, ferocious, and unimaginable light of a quasar, a blinding beacon that would have lit up the entire galaxy from within.
and been visible across the universe. Today, it is the silent gravitational conductor of the Milky Way's heart, a sleeping giant, patiently pulling every star in the galaxy into a slow, graceful, and utterly relentless dance. And the heart of our galaxy holds other surprises too. The region around the black hole is not a simple spherical cluster of stars. When astronomers used infrared telescopes to peer through the obscuring dust and map the structure of the central bulge, they discovered something wonderfully, beautifully unexpected. The central bulge of the Milky Way is not a round ball of stars at all. Instead, it has a peculiar, three-dimensional, peanut-like shape. Seen from the side, from an angle we can never have, it would swell outward in the middle and narrow at the ends, like a great twisting hourglass made of billions of ancient golden stars. This strange and intricate geometry is believed to have been formed by the galaxy's great central bar, a dense, elongated stripe of stars tens of thousands of light years long that rotates like a slow-moving propeller at the galaxy's heart. Over billions of years, the complex gravitational forces of this rotating bar can stir up the orbits of the surrounding stars, causing them to buckle and puff upward and downward, sculpting the core into this intricate and beautiful form. It is a quiet reminder that our home is full of unexpected complexity. It is not a simple mechanical object, but a layered, sculpted, and living structure, alive with the accumulated, rhythmic, and graceful dance of a billion stellar orbits. The great, glowing spiral arms of our Milky Way are not just a collection of existing stars. They are woven from the very birthplaces of stars. They are the galaxy's great fertile nurseries. Drifting throughout these arms are enormous, dark, and beautiful clouds of cold hydrogen gas and interstellar dust. These are the great molecular clouds. Some of them are so vast that they span hundreds of light years from end to end. They are so cold, chilled to just a few degrees above absolute zero, and so dense with dust that they block the light of all the stars behind them, appearing to our eyes as great dark rifts in the starry sky, like holes in the very fabric of the night. These silent, dark, and cold places are the galaxy's great reservoirs of raw material. This is where the story of every star begins. Within these clouds, in the deep and profound stillness, gravity begins its slow, patient, and persistent work. It gently coaxes the scattered atoms of gas and the tiny grains of dust to begin drifting toward one another. Over millions of years, small pockets of the cloud grow denser and denser, pulling more and more material inward under their own increasing weight. At the heart of one of these collapsing cores, a new object begins to form. It is not yet a star. It is a protostar, a glowing embryonic core that is heating up not from nuclear fusion, but from the immense pressure and friction of all the material that is raining down upon it. This protostar continues to grow, to gather mass for hundreds of thousands of years. The pressure and temperature at its center build and build, slowly, steadily, until a magical threshold is reached. The core becomes so hot and so dense that nuclear fusion ignites. The star awakens. It takes its first breath, and for the very first time, it begins to shine with its own self-sustaining light. The intense, brilliant light and the powerful stellar winds from these newborn suns then begin a process of beautiful destruction. They push away the remaining gas and dust from their birth cocoon, carving out great glowing cavities in the molecular cloud. They are unveiling themselves to the galaxy. It is like pulling back a dusty, dark curtain to reveal a newly formed, glittering collection of stellar jewels. The intense ultraviolet radiation from these hot, young new suns energize the surrounding hydrogen gas that has not yet been blown away, causing it to glow with a breathtaking luminescence. This is what creates the beautiful, colorful nebulae we can see in pictures, like the Great Orion Nebula. The radiant shades of pink, deep red, and shimmering silver are the signs of a stellar nursery, a place where creation is happening right now. These brilliant bursts of ongoing creation are what trace out the graceful, curving shape of our galaxy's spiral arms, illuminating them with a quiet, celestial, and life-giving fire. Every single star you have ever seen in the night sky, including our own gentle, life-giving sun, was born from one of these cloudy, cosmic cradles long, and unimaginably long ago. Beyond the bright, flat, spinning spiral of the disk, our galaxy holds another, much larger, older, and far more mysterious component. Surrounding everything we see, everything we typically think of as the Milky Way, is a vast, ancient, and nearly invisible sphere of influence. This is the galactic halo. Imagine a great, diffuse, and mostly transparent cloud that completely envelops the entire starry disk, extending for hundreds of thousands of light years in all directions. It is the galaxy's quiet, outer atmosphere. It is the galaxy's great, silent attic, where the oldest and most forgotten treasures are stored. This halo is a place of profound emptiness and immense scale. Its primary component is not stars or gas, but the vast, overwhelming, and still unidentified presence of dark matter. Though it is almost entirely invisible to our eyes, this halo holds the vast majority of the Milky Way's total mass. It is the true foundation, the great gravitational anchor that holds our spinning disk together. But it is not entirely empty of light. Drifting through this immense dark sphere are the true elders of our galaxy. Those ancient, scattered, metal-poor stars, born in another time, in other long-dead galaxies. They travel through the halo on long, slow, looping arcs that can take hundreds of millions of years to complete, rarely ever touching the busy, crowded plane of the disk. The halo is also the galaxy's great museum, its quiet archaeological record. It is here that we can still see the faint, ghostly remnants of those ancient galactic mergers, the long, delicate stellar streams, those beautiful ribbons of stars torn from smaller galaxies, continue to orbit here for billions of years, a final visible testament to the worlds that the Milky Way has consumed. The halo is, in essence, the galaxy's outer memory, a quiet, dim, and profoundly peaceful space, still in motion, still shaping what the Milky Way is and what it will one day become. And drifting within this great dark halo, like magnificent celestial jewels, are some of the oldest and most beautiful objects in the entire galaxy. These are the globular clusters. They are magnificent, compact, and almost perfectly spherical cities made of hundreds of thousands or even millions of ancient stars, all tightly bound together by their mutual gravity. Imagine a great cosmic snow globe, packed with ancient golden suns. There are over 150 of them that we know of, orbiting the galactic center on their own long elliptical paths far outside the main disk. They move through the empty halo like ancient golden moths, circling a very distant and sacred flame. These clusters are incredibly stable. Some are more than 12 billion years old, containing stars that predate the formation of the Milky Way's thin disk itself. All the stars within a single cluster were born at the very same time, from the very same cloud of primordial gas, making them perfect cosmic time capsules. By studying the light from these clusters, we can open a direct window into the past, holding clues about what conditions were like in the very early universe, how the first stars formed, and how our galaxy first began to assemble itself from the darkness. These quiet, golden, and self-contained worlds drift patiently high above and far below the galactic plane, glowing softly and serenely in the eternal silent dark. After all this talk of galactic collisions that unfold over eons, of supermassive black holes with the power of millions of suns, and of vast, dark, and empty halos, it may be comforting to know that our own solar system resides in a relatively peaceful and wonderfully unremarkable part of the galaxy. We do not live within one of the Milky Way's grand, bustling major spiral arms. Those are the great, luminous galactic highways, ablaze with the light of countless newborn stars and shaken by the frequent, violent explosions of dying ones. Instead, our sun occupies a much smaller, quieter structure, a partial arm, or a kind of celestial bridge called the Orion Spur. Imagine the galaxy as a vast, spinning city of light. The dense, brilliant core is its downtown, a place of intense energy and chaos. The great spiral arms are its major multi-lane highways, crowded, bright, and loud with the traffic of creation and destruction. Our home, the Orion Spur, is like a quiet, residential side street, a calm harbor nestled peacefully between the much larger and more active Sagittarius and Perseus arms. It is not an especially dense region, nor is it bursting with the chaotic energy of massive star formation. And that gentle quietness may be precisely why we are here. Why life, in all its fragile complexity, was able to take hold on our small blue planet. In the grand spiral arms, the density of stars is much higher. Massive, short-lived stars are born and die in rapid succession. And when a massive star dies, it explodes as a supernova, a cataclysmic event that can briefly outshine the entire galaxy. Such an explosion unleashes a devastating wave of high-energy radiation, which would sterilize any nearby planets, wiping out any life that had begun to emerge. Here, in our quiet spur, these events are much rarer. Our nearest stellar neighbors are at a safe and stable distance. We are far enough from the chaotic core to be safe from its intense radiation, yet we are not so far out in the sparse halo that there weren't enough heavy elements to form rocky planets like our own in the first place. We exist in a kind of galactic habitable zone, a Goldilocks region, not too violent, not too empty, but just right. This quiet corner of the cosmos may have given life on Earth the most precious gift of all, a long, uninterrupted period of peace. Billions of years of relative stability, a safe harbor in which the slow, delicate, and miraculous process of evolution could unfold. From the grand, dramatic, and radiant stage of the galaxy, we found our home in a calm and gentle spur, a quiet, protected place, perfect for complexity and consciousness and you to unfold. Our galaxy, from a great and distant vantage point, might appear as a perfect, flat, spinning disk of stars, a pristine and geometric spiral, but up close, its true structure is far more delicate, organic, and complex. The Milky Way does not lie perfectly flat. Its great disk of stars is gently, beautifully warped. Imagine an old, enormous vinyl record left out in the warm sun just long enough to develop a gentle, sweeping wave in its surface. This is the shape of our galactic disk. The outer edges of the disk bend gracefully upward on one side and downward on the other, forming a subtle, vast, and slowly rotating wave across the stars. This beautiful warp was completely invisible to us for centuries, hidden within the sheer, overwhelming scale of the galaxy itself. But when radio astronomers learned to map the vast, cool clouds of neutral hydrogen gas, the galaxy's great, invisible atmosphere that extends far beyond the visible starlight, this gentle cosmic curve was finally revealed. What could cause such a colossal structure to bend? The most likely answer lies with our closest companions. The Milky Way is not entirely alone. It is in a long, slow gravitational dance with two smaller satellite galaxies, the large and small Magellanic Clouds. For billions of years, as these two companions have looped around us in their orbits, their own gravity has been gently but persistently tugging on the outer edge of our disk, like a child gently pulling on the hem of a great flowing skirt. Over eons, this quiet, steady pull has been enough to draw the very fabric of our galaxy slightly out of shape. And this great warped disk also wobbles, very, very slowly as it spins. The entire wave pattern processes like a vast, slow-motion ripple moving through the stars. From a great distance, the Milky Way might look as if it is dancing, a slow, rhythmic, and silent dance through space. This gentle warp is part of a larger, more profound truth about our galaxy. It is not perfectly symmetrical. Though many scientific diagrams show it as a neat, evenly balanced spiral, the real Milky Way is beautifully, wonderfully lopsided. One side of the stellar disk appears to be slightly thicker and more populated with stars than the other. Its magnificent spiral arms are uneven in their brightness, their length, and the graceful arc of their curvature. Even the great spherical halo of ancient stars that surrounds everything is itself slightly off-center, its gravitational heart not perfectly aligned with the center of the bright disk. These gentle asymmetries are not flaws. They are the character. They are the quiet, physical evidence of its long, dramatic, and dynamic history. They are the subtle scars of ancient collisions with smaller galaxies. They are the wrinkles of deep time. They are the quirks of an uneven and organic growth that give our galaxy its unique and irreplaceable identity. It is not a perfect mechanical pinwheel. It is a living, evolving structure marked by the gentle tugs and twists of its cosmic journey. Its beauty lies not in a sterile perfection, but in its graceful, storied, and perfect imbalance. Now imagine yourself on the clearest, darkest night, far away from the golden haze of any city. You lie back and you look up, and the sky is a breathtaking, overwhelming canopy of light. You might see a few thousand individual stars, a glittering silver spray scattered across the deep, velvet darkness. To our human eyes, this feels like an ocean of light. It feels infinite, but what we can see, even on the most perfect night, is barely a single shimmering droplet in the true colossal ocean of the Milky Way. Our galaxy contains over 100 billion stars, perhaps as many as 400 billion. The numbers are so vast, they become almost meaningless. For every single star that you can see with your naked eye, there are tens of millions more that you cannot. The few thousand we can see are only our very closest and brightest celestial neighbors. The rest, the overwhelming, silent majority, are completely hidden from our view. Their gentle light is blocked by the great, dark, impenetrable curtains of interstellar dust that drift between the star systems. Or they are simply too faint, like the small, cool red dwarf stars that are the most common type of star in the galaxy. Or they are just too profoundly, unimaginably far away for their ancient, tired light to ever complete its long journey to reach our eyes. That pale, milky streak that crosses the night sky on a moonless summer night, the very feature that gives our galaxy its name, is not a cloud. It is the combined, blurry, and gentle glow of billions upon billions of unresolved stars, their light merging together across infinite distances. When you look at it, you are looking along the plane of our galaxy, deep into its crowded, luminous heart. We live surrounded by a colossal, silent river of starlight, and yet almost all of it remains forever invisible to us, too vast, too distant, and too dim to ever grasp from our small, precious vantage point within. And it is not just stars that are hidden from our view. The galaxy may be filled, perhaps even teeming, with another kind of cosmic wanderer that is cold, dark, and utterly, eternally alone. These are the rogue planets. Planets are not always tethered to the warmth and light of a parent star. Some may form in the usual way, within the swirling disk of gas and dust around a newborn sun, only to be ejected later in the chaotic early days of that solar system. A close gravitational encounter with a much larger, sibling planet could fling a smaller world out of its home system, sending it on a solitary journey into the darkness. Other rogue planets may never have had a star to call their own at all. It's possible for smaller clumps of gas and dust within a great stellar nursery to collapse under their own gravity, but without enough mass to ever ignite the fires of nuclear fusion and become a true star. They become worlds, born alone in the cold and the dark. Whatever their origin, these worlds drift silently, endlessly through the galaxy. They're cold, dark, and completely untethered, warmed only by the faint residual heat of their own formation or the slow decay of radioactive elements in their core. Studies and simulations suggest there may be billions of them in the Milky Way, perhaps even more rogue planets than there are stars. They are the cosmic orphans, the planetary drifters, following long, lonely, and almost completely invisible paths through the immense, quiet darkness between the suns.
Long, long ago, in its fiery and chaotic youth, the Milky Way was a much more active and violent place. The rate of star formation was dramatically higher than it is today. The galaxy was ablaze with the brilliant, searing blue light of countless massive, short-lived supergiant stars. The interstellar medium was constantly being shaken and stirred by the shock waves of far more frequent supernova explosions. It was a brilliant, turbulent, and formative era. But in more recent epochs, over the last few billion years, the pace has begun to slow. The great reservoirs of primordial gas are being used up, and the galaxy is settling. The star formation rate has been slowly, gracefully declining ever since its peak, long ago. This does not mean the end is near. It only means that we are living in a quieter, more peaceful, and more stable chapter of our galaxy's long life. It is moved from its fiery youth into a gentle and serene maturity. We are living in the Milky Way's golden afternoon. It is a mature spiral, glowing gently and steadily, no longer in a hurry, with many billions of years of quiet life still ahead of it. And within this grand, mature galaxy, nothing is ever truly lost. Stars are not permanent. They are born, they live, they burn, and they die. And in their spectacular dying, they return their very substance back to the galaxy in a beautiful, magnificent, and endless cycle of renewal. When a truly massive star, many times larger than our sun, reaches the end of its life, it explodes as a supernova. In its final, fiery moments, and in the cataclysm of the explosion itself, it forges all the heavy elements of the universe: the oxygen, the carbon, the iron, the gold. The explosion then scatters these precious, newly minted elements out into the surrounding space like a celestial sower casting seeds. When a smaller star, like our own sun, grows old, its death is a much more gentle and graceful affair. It will swell into a great red giant, and then it will slowly and peacefully shed its outer layers, creating a beautiful, intricate, and glowing structure called a planetary nebula, while its core settles into a small, quiet, cooling ember. This enriched material, this stardust, from both the violent and the gentle deaths of stars,
mixes back into the great interstellar clouds. It enriches them, seeds them with the complex elements that the universe did not have at its beginning. And it is from these enriched, second-hand clouds that new generations of stars are born. And more importantly, it is from this stardust that rocky planets like our Earth are made. And it is from this stardust that life itself is made. Every single atom in your body, apart from the very oldest hydrogen atoms, was forged in the heart of a star that lived and died long before our Earth was ever born. The iron in your blood that carries oxygen through your veins was created in a supernova. The calcium in your bones that gives you structure, the carbon in your DNA that holds the blueprint of your life, all of it is recycled stardust. The Milky Way is not a static stage. It is a great and patient engine of renewal. It breathes in time with its stars, making, unmaking, and beginning again, forever and ever. You are not just living in it. You are a part of it. You are the universe made conscious. And now, as our long and quiet journey together draws to its gentle and peaceful close, let the last of the stars begin to dim behind your thoughts. Let the immense concepts of space and time soften and dissolve into a beautiful, green, and peaceful backdrop for your own deep and restful sleep. Together, we have drifted through 100 quiet truths of our magnificent galactic home. We have wandered through its warped and beautiful disk and gazed into the ancient, ghostly light of its halo. We have danced along its mysterious spiral arms, where new suns are born, and peered toward its glowing, secret heart, where a sleeping giant resides. We have witnessed stars flung into the void and imagined the slow, graceful ballet of galaxies merging in the deep, distant future. We have felt the quiet presence of the invisible matter that holds it all together, and we have learned that we are living in a calm, protected, and peaceful corner of it all. Through it all, remember this final, simple truth. You are a part of this galaxy. You are not just a passenger on a small blue planet, but a true and inseparable participant in its long and luminous unfolding. You are a child of the cosmos in the most literal, physical, and beautiful sense. The very substance of your being is the dust of ancient, long-dead stars. Tonight, as you let go completely and surrender to the gentle call of rest, the great, silent galaxy continues its majestic turning. New stars are being born right now in its dusty, cosmic cradles. Ancient light from its farthest edges is just now arriving after a journey of billions of years. Its quiet, invisible forces are holding everything together in a perfect, peaceful, and eternal balance. And you are floating safely within it, a small, precious, and irreplaceable warmth in the great, cool darkness, resting peacefully in a quiet spiral arm of a gentle, radiant, and ever-moving sea of stars. I truly hope this long and quiet journey together has brought you some measure of peace, and that your mind is now quiet, calm, and ready for beautiful dreams. Thank you for spending this time with me here at the Midnight Scientists. Sleep well. See you in next video.
Hello there, and welcome to the Midnight Scientists, your cozy corner of the universe where curiosity and calm meet under a blanket of stars. Whether you are winding down after a long day, tucked gently under your blankets with your screen casting a soft glow, or perhaps you are simply allowing your mind to float untethered towards the peaceful shores of sleep, I am so very glad you have found your way here. Tonight, we will turn our gaze upward toward the vast open sky. We are going to explore the quiet science of flight, from the near-invisible flutter of a hummingbird's wings to the deep, steady hum of engines powerful enough to gently lift us toward the stars. This is the story of how life, and later our own creations, learn to rise from the ground, to hang suspended in the air, and to soar through the endless blue. Now, my only hope is that this story is just interesting enough to hold your attention, but gentle enough to let it go when you are ready. The goal, after all, is for you to drift away peacefully. But if you do find your mind still awake, captivated by the wonder of lift and thrust, well, at least you will be resting in a place of quiet wisdom. Before we begin our ascent, take a moment to notice where you are. I often wonder where in the world you might be listening from tonight. Perhaps night has just fallen where you are, or maybe the sun is preparing to rise. You can, if you feel so inclined, leave a quiet comment to say hello. It is always a joy to imagine this sleepy community stretching across all the world's time zones and continents. And if you find comfort in these gentle explorations where knowledge and calm intertwine, a soft tap on the like button or a quiet subscribe helps this channel in ways you cannot imagine. It is a small, silent gesture that supports so many hours of thoughtful research and softly whispered wonder. And finally, just a gentle reminder, while our journey tonight is filled with fascinating science, it is here only to help you relax, not to serve as medical advice. If you find sleep to be a consistent challenge, it is always best to speak with a qualified professional. This space is here to be a comfort, not a cure. All right, let's settle in now. Take a soft, slow breath in and let it go. Let's begin our gentle journey into the science of flight. Birds make flight look so wonderfully effortless. A gentle leap from a branch, a few soft flaps, and suddenly they are riding the breeze as if they were born from the air itself, which, of course, in a way, they were. But the reality of a bird's flight is a masterpiece of quiet complexity. It is the result of millions of years of evolution, a story of finely tuned mechanics and the cleverest tricks from nature's engineering department. What appears to our eyes as a graceful, weightless glide is truly a masterclass in physics, biology, and design, all working in perfect harmony. To understand how a bird flies, we must begin with its very essence, its anatomy. Birds are, in the most beautiful sense, living, breathing, flying machines. Every single part of their body, from the inside out, has been shaped over countless generations to serve one primary purpose: to remain in the air. The most obvious feature, of course, is the wing. But a bird's ability to fly is not just about having wings. It is about how those wings work in perfect concert with the rest of its delicate body. A bird's wing is built around a modified forelimb, not so different from a human arm. It has a humerus, a radius, and an ulna, familiar names if you have ever studied your own form. But in birds, these bones are elongated, reshaped, and refined to support the intricate structure of feathers and muscle, allowing them to maneuver through the air with breathtaking agility. This structure is both incredibly strong and impossibly light. This is made possible by bones that are hollow, yet reinforced with delicate internal struts, like the framework of a tiny cathedral. This means a bird can have large, sturdy wings without being weighed down by them. And then there are the feathers, each one a marvel of design. Flight feathers are asymmetrical, with a strong central shaft and delicate veins that lock together with microscopic hooks, like a zipper woven from air and light. These feathers can flex and twist, allowing the bird to sculpt the air around it, controlling the flow and generating lift with remarkable precision. The overall shape of the wing, known as an airfoil, is gently curved on top and flatter underneath. This elegant design helps generate lift. As air moves across the wing, it travels a little faster over the curved top surface, creating a pocket of lower pressure that gently pulls the bird upward. It is the very same principle that helps the great wings of an airplane lift off the ground. But birds do not just flap their wings randomly. There is a deep, ancient rhythm to it. During the downstroke, powerful chest muscles contract, pushing the wings down and forward to generate thrust. On the upstroke, smaller muscles help lift the wings while they partially fold, minimizing resistance. This coordinated motion allows birds to maintain their forward momentum and stay aloft, a continuous cycling dance between power and grace. In some species, this cycle happens in the blink of an eye. The hummingbird, for example, a tiny jewel of motion, beats its wings up to 80 times per second, hovering in place with astonishing control. Of course, not all birds fly in the same way. A hawk, soaring high over a field, uses its long, broad wings to ride invisible currents, conserving its energy as it patiently searches for prey below. In contrast, a tiny sparrow flits from bush to bush using quick, choppy strokes for agility in confined spaces. And some birds have made other choices. Penguins, though technically birds, have traded flight through the air for flight through the water. Their wings have evolved into powerful flippers, perfectly suited for slicing through the dense ocean currents. Ostriches and emus gave up flight entirely, opting instead for powerful legs and the freedom of running across open plains. Evolution, it seems, is always more concerned with survival than with a single style. Even among flying birds, the shape of a wing tells a story about its lifestyle. Birds with long, narrow wings, like the albatross, are built for gliding over vast open oceans. They can travel thousands of miles with barely a flap, trusting the wind to carry them. Birds with shorter, rounded wings, like pheasants, are designed for quick, explosive takeoffs and short bursts of speed, often to escape predators in dense forests. And falcons, the sprinters of the sky, have pointed wings that allow for high-speed dives, reaching over 200 miles per hour as they descend upon their prey. The bird's tail is more than just decorative. It acts as a rudder, helping with balance, steering, and braking. When landing, many birds spread their tails wide, like a fan, to increase drag and slow down for a gentle touchdown. But even the most beautifully designed wings would be useless without the right power source. Birds have enormous breast muscles, which can make up a significant portion of their body weight. These muscles attach to a large, keeled sternum, a unique feature that provides a broad surface for muscle attachment, enhancing the strength of each downstroke. Their internal systems are also built for this high-energy lifestyle. Birds have incredibly efficient respiratory systems. Unlike mammals, they use a unidirectional airflow system, with air sacs that keep fresh oxygen moving in a continuous loop. Their hearts are proportionally larger, and their metabolic rates are sky-high, everything geared toward fueling the demanding act of flight. From their light skeletons to their aerodynamic feathers, from their powerful muscles to their efficient breathing, every detail has evolved to serve a purpose in the air. It is not magic, it is science. But sometimes, when you see a gull tracing lazy loops over the waves, or a swallow diving through the summer air like a living arrow, it feels like the closest thing to magic that nature has ever invented. Long before the first bird took to the air, another group of creatures had already mastered the skies. Insects were the first pioneers of flight on Earth. They were buzzing through prehistoric air long before the dinosaurs, experimenting with flight in all its strange and miniature glory. And their flight is wonderfully strange, so unusual in fact that when scientists first tried to model it using the principles of classical aerodynamics, the mathematics simply did not add up. According to those early equations, some of these tiny creatures shouldn't be able to fly at all. But fly they do, beautifully, erratically, and sometimes with the floating elegance of a dream. Take the humble bumblebee. For years, a myth circulated that its flight was physically impossible. This isn't quite true, of course. It just doesn't follow the same rules as airplanes or even birds. Bumblebees don't rely on a smooth, steady flow of air over their wings. Instead, they beat their wings with incredible rapidity, creating unsteady vortices, tiny swirling currents of air that generate lift in ways we are only just beginning to fully understand. It is a different kind of grace, one born of vibration and energy. One of the key differences between birds and insects lies in how their wings are controlled. Birds flap using muscles that move their entire limb. Many insects, on the other hand, flap their wings by vibrating their thorax, the middle segment of their body. Their wings are attached indirectly, and it is this method of muscle control that allows some species to flap at astonishing speeds. A common housefly can beat its wings around 200 times every single second, all while maintaining stable flight and dodging obstacles with near instantaneous reflexes. Many insects also have multiple pairs of wings. The dragonfly, a living jewel of the air, has 2 pairs that can operate independently. This grants them a stunning degree of control. They can hover, glide, drift sideways, and even fly backward, as if rewinding time. Their wings are not synchronized like a bird's. They are more like 2 sets of silent oars paddling through the currents of the air with absolute precision. Watching a dragonfly maneuver is like watching a helicopter with a doctorate in dance. Butterflies offer a different case entirely. Their flight appears almost clumsy, a gentle, fluttering dance. But that fluttering has a purpose. The irregular wing beats make their path through the air unpredictable, making it harder for predators to track them. Butterflies also use their large, broad wings to absorb sunlight, warming their bodies to the perfect temperature before taking flight. For them, flight is not just travel, it is a vital part of their thermoregulation. Then there are the moths, the night shift of the insect aviation world. Some moths, like the hawk moth, are surprisingly powerful flyers. The hummingbird hawk moth is so agile and precise that it is often mistaken for an actual hummingbird, as it hovers before a flower, sipping nectar with its long, coiled tongue, all while maintaining rock-steady mid-air control. One of the reasons insects can perform such aerial acrobatics is their size. At such a small scale, air behaves differently. It feels thicker, stickier, more like moving through syrup than the thin, breezy air we're used to. This means insects rely on what is known as unsteady aerodynamics, where the rapid motion of the wing creates complex patterns of air that generate immense lift. Insects also exploit something called delayed stall. When a bird or a plane tilts its wing too far, airflow separates and lift is lost. But insects flap their wings so quickly that the airflow doesn't have time to separate in the usual way. Instead, a vortex forms along the leading edge of the wing, clinging to it and pulling the insect upward. It is like surfing on your own personal whirlpool. Despite their mechanical genius, insect wings are astonishingly delicate, made of a thin membrane supported by a network of veins, more like stained glass than aircraft components. Yet these wings can endure thousands upon thousands of flaps. The variety in insect wings is dazzling. Some are short and stubby, others long and ribbon-like. Some shimmer with iridescence, while others are nearly invisible in motion. They dazzle, confuse, and occasionally, they simply fill us with wonder. And then there are the mayflies, whose adult life is so fleeting they barely have a chance to use their wings at all. Some species live for less than a day in their winged form. Yet they still take to the skies, driven by instinct. Their brief flights are a quiet reminder that even the most temporary moments in nature can be filled with purpose and grace. While the physics may seem chaotic, it is rooted in biological innovation. A fruit fly can change direction in less than 1/100th of a second, faster than we can blink. In their fluttering, zipping, hovering dance, there is a kind of miniature marvel that makes the night air feel just a little more alive. When we imagine creatures of flight, our minds often drift to birds and insects. But the world of mammals, ever resourceful, has found its own quiet ways into the sky. While they may not have feathers or iridescent wings, they have evolved some truly remarkable tools for becoming airborne. Among them, bats are the true masters of powered flight. And others, like the gentle flying squirrel and the sugar glider, have chosen a different path, learning to glide from tree to tree, using skin stretched like a living parachute. The night sky, it seems, is not exclusive to the feathered or the six-legged. Some mammals have claimed a slice of it for themselves. Let's begin with the bats, for they are not just gliders pretending to fly, they are the real deal. Bats are the only mammals capable of true, sustained flight. That is not a bit of poetry, it is a biological fact. They flap their wings, generate lift, and propel themselves through the air just as a bird does, but with a structure that is entirely their own. Where a bird's wing is a modified arm adorned with feathers, a bat's wing is more like an incredibly long and graceful hand, veiled in a soft, dark membrane. This wing membrane, called the patagium, stretches from the elongated fingers of their forelimbs all the way down to their hind legs, and sometimes even to their tail. If you could watch a bat's wing move in slow motion, it would seem less like a bird's rigid flap and more like a silken scarf dancing in the wind. This flexible design gives bats a level of flight control that is astonishingly advanced. They can bank sharply, hover in place, and even drift backward. The skin of the patagium is filled with tiny sensory receptors that respond to the flow and tension of the air, giving the bat immediate, constant feedback about its position and speed. It is like flying with touch-sensitive gloves that are also a part of your own skeleton. Bat species vary widely in their size and style of flight. The tiny bumblebee bat, which weighs less than a coin, flits through the air with quick, delicate wing beats. At the other end of the spectrum are the flying foxes or fruit bats with wingspans that can stretch over 5 feet. These larger bats tend to glide more than flap, using long, slow wing beats to cruise through the forest in search of sweet fruit or nectar. Bats are also the champions of navigating the night. Since most species fly in complete darkness, they rely on a remarkable ability called echolocation to perceive their surroundings. By emitting high-frequency calls far beyond our range of hearing and listening to the echoes that bounce off nearby objects, bats can build a detailed mental map of their environment in real time. It is a way of seeing with sound. It is not just for avoiding trees or catching insects, it is also essential for landing softly on ceilings, for locating their roosts, and for finding one another in the vast darkness. Some species have perfected this ability to a degree that is almost unbelievable, able to detect objects as fine as a single human hair in the pitch black. These gentle creatures are essential pollinators, pest controllers, and seed spreaders in many ecosystems. Without bats, tropical forests would lose some of their most dedicated gardeners, and warm summer evenings would be noticeably less peaceful. While bats took the path of powered flight, other mammals decided that gliding was a quieter, more elegant solution. Gliders do not flap. They simply launch themselves into the air, spread their limbs, and let gravity and the currents of the wind do the work. And if you have ever been lucky enough to see a flying squirrel drift from one tree to another under the moonlight, you will know that it is a moment of pure, silent magic. Gliding mammals look more like professional parachutists than reluctant leapers. Flying squirrels have a skin membrane, also called a patagium, that stretches between their wrists and ankles. When they leap into the air, they spread their limbs wide, creating a soft, square sail to catch the wind. They steer with tiny, subtle shifts of their legs or their large, fluffy tail. It is not flight in the powered sense, but it allows them to travel surprisingly long distances, sometimes over 100 feet, with a minimal loss of altitude. Their tail acts as a rudder in midair, helping to stabilize their glide and control their landing. It is not as fast or as flexible as a bat's flight, but for crossing gaps in the forest canopy, it is incredibly effective. Sugar gliders, which come from Australia and nearby regions, follow a similar pattern. These small, wide-eyed marsupials get their name from their love of sweet things and their gliding prowess. They can launch from high branches, spread their limbs, and silently coast across open spaces to reach another tree, using their long tail as a rudder to fine-tune their glide path with surprising precision. Together, bats and gliding mammals represent two fascinating solutions to the same challenge: how to move through the air. One uses power and propulsion, the other uses grace and gravity. But both demonstrate that flight, in its many forms, is a possibility that nature keeps rediscovering, tweaking, and perfecting in different shapes and sizes. When night falls and the forests darken, these creatures take to the skies, silent, swift, and often unseen. Their movements are a testament to the beautiful diversity of flight. Whether flapping through the darkness or gliding like a whisper on the wind, they remind us that the sky is open to more than one kind of traveler. Flying may look like magic, but it is truly a clever and beautiful balancing act, a quiet negotiation between four invisible forces. These forces are always present, always in a gentle conversation with one another. Their names are lift, thrust, drag, and gravity. Together, they create the delicate harmony that allows a bird to soar, a great plane to cruise through the upper atmosphere, and a tiny bee to buzz through a garden without simply tumbling from the sky. Understanding how these forces work does not require a mind for complex physics. It only asks for a little bit of quiet curiosity, a willingness to imagine the air around you not as emptiness, but as something alive, something with shape and pressure and gentle movement. Let us begin with gravity. It is the most familiar of the four forces. It is the constant, gentle pull of the earth, the force that keeps your feet on the ground and holds the oceans in their beds. Gravity is always there, a quiet, persistent anchor. For anything to fly, it must find a way to answer this downward pull. And that is where lift comes in. Lift is the upward force, the gentle whisper that counteracts gravity and keeps a flying object suspended in the air. It is generated by the movement of air over a wing. The shape of a wing, gently curved on top and flatter underneath, is known as an airfoil. As the air moves across this shape, it travels a little faster over the curved top surface and a little slower underneath. This small difference in speed creates a difference in pressure. The air pressure on top becomes lower and the pressure underneath becomes higher. And this difference results in a gentle upward push. That is lift. It's a bit like the feeling of holding your hand out the window of a slowly moving car. If you tilt your hand just so, you can feel the air gently pushing it upward. Your hand, for a moment, becomes a small wing, having a quiet conversation with the air. Birds, insects, and airplanes all rely on this very same simple principle. Next in our quiet dance is thrust. This is the forward force that propels a flying object through the air, allowing the wings to meet the wind in the first place. Birds create thrust by the gentle push of their flapping wings. Airplanes use the deep hum of engines or the spin of propellers. Even the tiniest insect, in its buzzing flight, is generating thrust with each delicate wing beat. Thrust keeps things moving, and that forward motion is what allows the wings to create lift. But nothing moves through the air without feeling its presence. And this brings us to our fourth force, drag. Drag is the gentle resistance of the air, the force that pushes back against motion. It is caused by the air itself as it touches and flows over the surface of a moving object. Think of drag as the whisper of the wind against your face as you walk. In flight, drag pulls backward while thrust pushes forward. It is a constant, soft tug of war. And so, we have our four dancers. Lift, pushing up. Gravity, pulling down. Thrust, pushing forward. And drag, pulling back. For a flight to be smooth and steady, these four forces must be in perfect balance. When lift is equal to gravity and thrust is equal to drag, you have a serene, level flight. If lift becomes a little greater than gravity, the aircraft or bird will gently climb. If gravity wins the conversation, it will softly descend. If thrust overtakes drag, it accelerates. And if drag gets the upper hand, it slows down. Flying, in its purest form, is simply the art of managing this continuous, peaceful relationship between these four invisible players. A bird adjusts the angle of its wings. A pilot adjusts the power of the engines. Every movement is about shifting this delicate balance to suit the moment. It is a triumph of physics and engineering, yes, but also of evolution. It is a continuous negotiation made possible by the quiet, invisible push and pull of the air. The world may seem still from a bird's eye view, but the air is alive with these forces, all working in harmony to keep things aloft. Understanding them doesn't take away the wonder of flight. If anything, it adds to it. Because once you know what is truly happening up there, how every flap, every tilt, and every curve is shaping the air, you can't help but feel a little awed by it all. Flying is not about defying gravity, it is about dancing with it, listening to the air, and trusting it to hold you up. Now let us drift for a moment into one of nature's most elegant solutions to flight, gliding. It is not quite flying in the powered sense. There are no engines humming, no wings flapping furiously. It is flight's quieter, more thoughtful cousin. It is the art of slipping through the air with minimal fuss, relying on gravity, the wind, and the well-shaped body to move forward. At its very core, gliding is a form of controlled falling. Gravity is always there, pulling things down, but a glider has learned to use that pull to its advantage. Rather than tumbling straight to the ground, a glider tilts itself into the air, trading a little bit of vertical descent for a great deal of horizontal travel. It is like coasting down a long, gentle, invisible hill. The shallower the angle, the farther it can go. And with the right conditions, a glider can stay airborne for hours, for hundreds of miles, without burning a single drop of fuel. Birds, of course, are some of the most skilled gliders in the animal kingdom. Think of the albatross, with wingspans that can stretch over 11 feet. These magnificent seabirds are the undisputed champions of long-distance gliding. They spend most of their lives soaring over the open ocean, harnessing the subtle differences in wind speed near the water surface to gain energy, covering thousands of miles without seeming to try at all. Other birds, like vultures and hawks, are masters of thermal gliding. Thermals are invisible columns of rising warm air that form when sunlight gently heats the ground. These birds can feel these invisible updrafts, and they will circle gracefully within them, gaining altitude without a single flap of their wings. Once they are high enough, they can glide for miles, scanning the world below, suspended between the earth and the sky on a soft pillar of warm air. And it is not just the specialists who glide. Many birds use it to conserve energy. A well-timed glide can provide a moment of rest during a long journey, or a silent, stealthy approach to a branch. It is not always about going far. Sometimes it is simply about moving efficiently and peacefully. And as we know, gliding is not limited to birds. The flying squirrel launches from a high branch, stretches its limbs, and drifts through the forest canopy like a soft brown leaf. Clever adjustments of its body and tail allow it to steer, slow its descent, and land with remarkable accuracy. It does not just fall, it steers, pivots, and fine-tunes its path, a tiny, living parachute. Even some reptiles and amphibians have learned this quiet art. Certain lizards can spread their ribs to create makeshift wings, gliding from tree to tree. And some tropical frogs have evolved webbing between their toes that allow them to catch the air as they leap, turning a simple jump into a long, floating descent. Humans, too, have long been fascinated by the silent dream of gliding. Modern gliders, or sailplanes, are sleek, high-performance machines. They have long, slender wings designed to maximize lift and minimize drag. A pilot is towed into the air and then released to begin a silent search for rising air currents. With no engine to drown out the experience, flying a sailplane is often described as the closest a person can come to soaring like a bird. It is silent, it is smooth, and it requires a constant, quiet awareness of the invisible structures in the sky. A glider pilot reads the landscape below the way a sailor reads the water. They look for sunlit fields that might generate thermals, for hills that deflect the wind upward, or for soft, puffy clouds that mark the tops of rising air columns. It is a mix of science and intuition, of calculation and feeling. Hang gliders and paragliders offer another form of this freedom. Launching from a mountaintop or a cliff, the pilot catches the wind and is suddenly floating, not falling, carried along by the invisible rivers of air that swirl and flow all around us. While gliding may lack the drama of powerful engines, it is a marvel of quiet efficiency. It turns gravity from a foe into a friend, using descent to travel, not just to drop. What is most fascinating is how this strategy has evolved again and again across so many different forms of life. It is efficient, versatile, and often surprisingly precise. Whether it's a sailplane tracing lazy spirals against a blue sky, or a flying squirrel leaping into the moonlit night, gliding reminds us that flight does not always need power. Sometimes all it takes is a clever design, a little bit of altitude, and the patience to let the air do most of the work. For most of human history, the sky was a place that belonged to others. It was a realm reserved for birds, for the clouds, and for the distant silent stars. The idea that we as humans might one day take to the sky was a thought as far-fetched as living on the moon. And yet, the desire to fly has been with us for millennia. It is a dream etched into our oldest myths and legends, a quiet yearning scribbled into the notebooks of thinkers, and a hope tested through brave, imaginative attempts. Behind every imaginative design and every learning experience was something truly inspiring, a quiet belief that flight was not just possible, but that it was a part of our destiny. One of the first great minds to give this dream a scientific shape was Leonardo da Vinci. In the late 15th century, long before the principles of aerodynamics were understood, da Vinci sketched out elaborate flying machines in his private notebooks. There were ornithopters, machines with flapping wings inspired by the birds he so carefully studied, complete with intricate gears and pulleys. He was not trying to build a working aircraft so much as he was thinking aloud on paper, laying the intellectual and imaginative groundwork for the centuries to come. His drawings were a conversation between art, science, and a deep longing for the sky. As the centuries passed, the dream persisted. Throughout the 17th and 18th centuries, brave inventors across Europe tested various winged contraptions and gliders. One of the earliest recorded attempts came from Abbas ibn Firnas in 9th century Spain, who reportedly covered himself in feathers and glided from a tower. He managed a short flight, a brief and beautiful moment suspended in the air before returning to the earth with a hard landing. It was a courageous experiment, born of pure enthusiasm. By the late 18th century, things started to become a little more floaty. In 1783, in France, the Montgolfier brothers launched the very first hot air balloon. It was not powered flight, but it was a profound milestone. For the first time, humans were truly in the air, drifting silently above the earth in a basket suspended beneath a billowing silk balloon. The very first passengers on this ascent were a sheep, a duck, and a rooster, chosen for their calm dispositions. The balloon rose to over 1,000 feet and returned them all safely to the ground. It must have felt like pure magic. Later that same year, two men, Jean-François Pilatre de Rosier and François Laurent Darlans, became the first people to fly. They floated over Paris in a hot air balloon for nearly half an hour. No engines, no flapping wings, just fire, air, and an immense sense of wonder, looking down upon the world as only birds had before. The 19th century brought new ideas and a more scientific approach to gliding. This was thanks in large part to the German aviation pioneer Otto Lilienthal. He was the first person to systematically study how wings worked, conducting over 2,000 flights with his carefully constructed gliders. Lilienthal's approach was patient and methodical. He gathered data, he experimented with wing shapes, and he helped confirm the importance of the curved airfoil shape for generating lift. His flights were a form of listening to the air, learning its secrets through quiet, personal experience. Tragically, he died in 1896 after a glider accident. But his work, his passion, and his meticulous research directly inspired the very people who would finally succeed where so many had only dreamed. From feathered suits to fiery balloons, from patient gliders to imaginative sketches, humanity's path to the sky was anything but a straight line. But it is precisely that long and winding road that makes the reality of modern flight so remarkable. Every smooth takeoff today carries the quiet echoes of centuries of dreams and of the countless people who looked up at the sky and thought, with a hopeful whisper, why not? At the turn of the 20th century, if you had asked who was going to solve the great mystery of flight, the answers would have likely involved famous inventors or wealthy scientific teams. No one would have expected that two unassuming bicycle mechanics from Dayton, Ohio, working quietly out of their modest workshop, would be the ones to finally crack one of the most stubborn puzzles in human history. But that is exactly what Orville and Wilbur Wright did. The Wright brothers were not born into privilege, and they did not have formal engineering degrees. What they did have was a deep, shared curiosity, a quiet persistence, and a natural gift for understanding how things worked. Their mechanical experience came from building printing presses and repairing bicycles, machines that require a keen understanding of balance, friction, and control. In hindsight, it was the perfect training for building an airplane. What set the Wright brothers apart was their methodical, patient, and data-driven approach. While others were still focused on building powerful engines, the Wrights believed the true challenge was not just getting off the ground, but learning how to control a machine once it was in the air. They wanted to understand how to stay up there safely and how to steer with grace and precision. To do this, they began with gliders. Between 1900 and 1902, they traveled to Kitty Hawk, North Carolina, a place they chose for its steady winds, its soft sands for gentle landings, and its wide open, peaceful spaces. There, under the vast coastal sky, their early gliders taught them invaluable lessons. They learned how wings behaved in the real air, and they discovered that much of the existing aerodynamics data was simply wrong. So they returned home and built their own wind tunnel. It was a simple, handmade wooden box, but inside it, they could test dozens of miniature wind shapes, carefully recording the forces of lift and drag. For the first time, they had real, accurate numbers to base their designs on, not just guesses or theories. Their next great innovation was control. They developed a system that allowed a pilot to steer the aircraft in all three dimensions. And to control the roll of the aircraft, they invented something called wing warping, a way of gently twisting the wings in opposite directions to maintain balance and turn smoothly. It was a clever solution inspired by watching how birds twisted their wingtips to steer. Once they had a glider that could be controlled, the final piece of the puzzle was power. They needed an engine that was light and powerful, something that did not exist at the time. So, naturally, they built their own. With the help of their mechanic, Charlie Taylor, they constructed a small, lightweight engine. Their first powered aircraft, the Wright Flyer, was a delicate machine of wood, wire, and fabric. And then, on the quiet, windswept morning of December 17, 1903, with Orville at the controls, the Flyer lifted off the sand. The flight lasted for just 12 seconds and covered only 120 feet. There were only 5 witnesses. There were no cheering crowds. But in that brief, quiet moment, history was changed forever. Heavier than air, controlled, powered flight had become a reality. By the end of the day, they had made 4 flights, the longest lasting nearly a minute. The Wright brothers' story is not just about an invention. It is about how ordinary people can achieve extraordinary things through curiosity, patience, and a refusal to give up. They didn't just build an airplane. They quietly opened a door to the sky. And in their story, we find a gentle lesson. Sometimes the greatest breakthroughs come not from a loud bang, but from a quiet, persistent whisper of an idea, patiently nurtured until it is ready to take flight. At first glance, an airplane might seem like a simple shape against the sky, a smooth metal tube with wings. But every curve, every angle, and every surface is there for a reason. An airplane is a carefully crafted machine built to slice through the sky with stability, speed, and a quiet grace. Let's begin with the main body, or the fuselage. This is the long central structure that holds everything together. It is where passengers rest, where cargo is stored, and where, at the very front, the pilots guide the journey. It is designed to be strong enough to handle the changes in pressure high above the Earth, yet light enough not to weigh the aircraft down. Its smooth, streamlined shape allows the air to flow over it like water over a stone. Connected to the fuselage, of course, are the wings, the true stars of the show. These are what make flight possible. As we know, the air moves over and under their gentle, curved shape, the airfoil, to generate the soft, upward push of lift. But the wings are not just simple, solid structures. They are filled with fuel tanks, structural supports, and a series of moving parts called control surfaces, which help to guide the plane through the air. Near the wingtips are the ailerons. These are small, hinged sections that move in opposite directions. When one goes up, the other goes down. This creates a gentle rolling motion, allowing the plane to lean into a turn, much like a bicycle leans into a curve. Closer to the body of the plane are the flaps. These are larger panels that extend downward and backward from the edge of the wing. They are used during takeoff and landing to increase lift at slower speeds. By changing the shape of the wing, flaps allow the aircraft to lift off the ground sooner and to land more slowly and softly. Now let's drift to the back of the plane, to the tail section. This part includes the horizontal and vertical stabilizers, which do exactly what their name suggests. They keep the plane stable and steady in the air, preventing it from pitching up and down or swinging from side to side. They act much like the feathers on an arrow, ensuring a smooth and true path. Attached to the horizontal stabilizer is the elevator. This is a movable surface that guides the nose of the plane gently up or down. Attached to the vertical stabilizer is the rudder, which helps to steer the nose left or right. All of these surfaces, the ailerons, the flaps, the elevator, and the rudder, work together in harmony. They are guided by the pilot from the quiet, focused cockpit, making small, constant adjustments to keep the flight smooth and on course. And finally, there are the engines. Whether they are jet engines that hum with a deep power or propeller engines that spin like graceful windmills, their purpose is to provide the forward thrust needed for the wings to meet the air and generate lift. An airplane is not just a collection of parts. It is a complete system, a flying ecosystem, where every piece plays a role in keeping it stable, responsive, and safe. As it gathers speed down a runway, the air begins to rush over its wings. And then, almost magically, but really thanks to physics, it lifts off the ground, a bird of aluminum and circuitry slicing through the sky with poise and with purpose. Jet engines are a wonder of controlled power. Their entire purpose is to gently draw in the air, energize it, and then release it in a way that creates a smooth, continuous forward push. They are the quiet heart of modern air travel, humming with a deep and steady rhythm. It all begins at the front of the engine with the intake. As the aircraft moves, air flows into the engine where it is met by large, spinning fan blades. These fans guide the air inward, compressing it, making it denser and warmer. This warm, compressed air then flows into the combustion chamber. Here, a fine mist of fuel is introduced, and the mixture ignites, not in an explosion, but as a continuous, glowing stream of hot, energized gas. This stream of energy wants to expand, and it is guided out through the back of the engine. As it is released, it creates a powerful, steady push forward. It is a beautiful and simple principle. For every action, there is an equal and opposite reaction. The engine pushes a river of air backward, and in return, the airplane is gently pushed forward. All of this happens thousands of times per minute inside a casing of precision materials designed to withstand incredible temperatures. And yet, from a passenger seat, the experience is one of quiet serenity. The immense power becomes a distant hum, the background music to your journey through the clouds. Now, if you push an aircraft fast enough, you eventually reach the speed of sound. This is a special threshold, a point where the air begins to behave in new and interesting ways. To travel beyond this speed to achieve supersonic flight requires a special kind of design and power. As a plane approaches this threshold, the air in front of it can no longer move out of the way as easily. Pressure waves begin to build up. When the plane crosses that threshold, these waves are released, creating a ripple of pressure that travels through the air behind it. For those inside the aircraft, the moment is often unnoticeable. The journey simply becomes smoother, quieter, as the plane outraces its own sound. Supersonic flight is less about raw, noisy speed and more about a serene glide at the very edge of the atmosphere. The most famous supersonic passenger aircraft was the Concorde. It was a beautiful machine with long, sweeping delta wings shaped like a graceful paper dart. It could cruise at over twice the speed of sound, flying so high that you could see the gentle curve of the Earth and the deep, dark blue of the upper atmosphere. A journey on the Concorde cut transatlantic flight times in half, turning a long day of travel into just a few peaceful hours. Though it no longer flies, the dream of quiet, high-speed travel continues, with new designs exploring ways to make supersonic flight even more efficient and serene. But whether an aircraft is traveling at the speed of sound or cruising gently below it, the engines that carry it are marvels of reliability. They are some of the most thoroughly tested machines on the planet, built to perform their quiet, powerful work for thousands of hours, carrying us smoothly across oceans and continents through the calm, thin air high above the world. And now, let us consider a different kind of flight, one that does not need a long runway or forward speed to begin. Let us think about the helicopter, the mechanical equivalent of a hummingbird, able to rise straight into the air, to pause, and to dance in place. Where an airplane slices through the sky, a helicopter seems to negotiate with it, hovering, pivoting, and moving in any direction it chooses. It is a form of flight that feels like it belongs in a dream, but it is all based on wonderfully clever engineering. At the heart of every helicopter is the main rotor. This is not just a spinning fan, but a set of long, graceful blades, each one shaped like a slender wing. As they sweep through the air in a wide circle, they generate lift, allowing the helicopter to ascend vertically as if being drawn upward by an invisible thread. But the true magic of a helicopter is its ability to hover, to hang suspended in one single spot in the air. This requires a constant, delicate balancing act. The pilot must make continuous, tiny adjustments to the angle of the rotor blades to counter every gentle puff of wind, every shift in air temperature. Hovering is like trying to balance on the head of a pin. It is a state of perfect, active stillness. This remarkable control is made possible by a system that allows the angle, or pitch, of each rotor blade to be changed as it spins. To move forward, the pilot can subtly increase the pitch of the blades as they sweep towards the back of the helicopter and decrease it as they move forward. This tilts the entire rotor disc, and the helicopter gently leans in the direction it wants to go. To rise straight up, the pilot increases the pitch of all the blades at once, causing them to take a deeper bite of the air. To descend, the pitch is lessened and the helicopter settles back towards the ground, as softly as a falling seed. But as the main rotor spins in one direction, the body of the helicopter naturally wants to spin in the other. This is a simple law of physics called torque. To counteract this, most helicopters have a smaller tail rotor. This quiet, sideways-facing rotor acts like a gentle rudder, providing a soft push that keeps the main body perfectly steady. It is the quiet counterbalance that allows for smooth, controlled turns. This agility is what makes helicopters so uniquely useful. They can reach places no other vehicle can. They can land on a hospital rooftop, a mountain ledge, or in a remote forest clearing no bigger than a backyard. They are used for search and rescue, for medical evacuations, and for delivering aid to places cut off from the world. They are an airborne multi-tool, a gentle machine of access and assistance. To watch a helicopter hovering in place, its blades a shimmering, transparent disc, its body perfectly still against the sky, is to forget all the complex forces at play. Beneath that poised, floating posture is a beautiful ballet of physics and human control. It is perhaps the closest thing we have built to a mechanical dragonfly, able to lift off on a whim and land with the precision of a whisper. Rockets are not subtle machines, but there is a deep and profound beauty in their purpose. Where an airplane hums through the atmosphere, a rocket is designed for a much grander journey, to leave the embrace of the Earth entirely. To reach the silent, weightless realm of space, a rocket must perform an act of incredible power. It must rise against the full pull of gravity, push through the dense layers of the atmosphere, and accelerate until the planet finally lets it go. What makes a rocket so different from a jet is that it brings everything it needs with it. A jet engine breathes in the air around it, but a rocket must carry its own breath in the form of an oxidizer. This is because where it is going, there is no air at all. A rocket engine works on that simple, elegant principle. For every action, there is an equal and opposite reaction. Inside the engine, a fuel and an oxidizer are combined, creating a continuous, powerful stream of hot, energized gas. This stream is guided through a nozzle at the bottom, and as it pushes downward, the rocket is gently but irresistibly pushed upward in response. The moment of launch is a sight of pure majesty. It begins with a deep, rumbling vibration that you can feel more than hear. Then, a pillar of bright, warm light appears at the base, and the rocket begins its slow, steady ascent. It rises with a deliberate and unwavering purpose, a shining needle pointing toward the heavens, leaving behind a soft cloud of billowing white vapor. To break free from the Earth's gentle but persistent pull, a rocket must reach a speed known as escape velocity. It does not do this all at once. Instead, it follows a long, graceful arc, climbing upward while also moving sideways, faster and faster until it is essentially falling around the Earth rather than back down to it. To make this journey more efficient, most rockets are built in stages. The first stage, the largest and most powerful, does the heavy lifting of getting the rocket off the ground and through the thickest part of the atmosphere. Once its fuel is spent, it gently separates and falls away, having completed its part of the journey. This allows the rest of the rocket, now much lighter, to continue its climb. It is like a traveler shedding a heavy coat as they ascend a mountain. With each stage that falls away, the rocket becomes lighter, faster, and more graceful as it moves toward the quiet of space. In recent years, we have even taught these rocket stages how to return home. Instead of being discarded, some are now designed to guide themselves back through the atmosphere and land softly on their own, standing upright, ready to begin another journey. It is a beautiful dance of engineering and precision. There is something deeply poetic about a rocket's flight. These immense machines carry our greatest curiosities into the void. They carry telescopes that look back to the dawn of time, robotic explorers destined for other worlds, and sometimes they carry people. They turn the sky from a ceiling into a gateway. And when you watch a rocket rising through the clouds, a steady point of light against the deep blue, it is hard not to feel a sense of wonder. It is a machine built on a simple idea. If you push hard enough in one direction, you can go anywhere. And its journey, which begins with such deep and powerful sound, is ultimately a journey toward the most profound and perfect silence. Once a rocket has completed its powerful ascent, it delivers its precious cargo into the silent, peaceful realm of orbit. Orbit is a state of perfect, weightless balance. It is not flying in the way we think of it. It is more like a continuous, effortless fall. Imagine you could throw a stone so fast that as it began to fall, the Earth's surface would curve away beneath it at the very same rate. The stone would keep falling and falling, but it would never actually reach the ground. It would simply circle the planet forever. That is what it means to be in orbit. You are in a perpetual, silent dance with gravity. Up there, in the vacuum of space, there is no air to slow you down. Once a spacecraft reaches orbital velocity, it can turn off its engines and simply coast, drifting along its curved path around the world. The International Space Station does this, circling the entire planet once every 90 minutes, its inhabitants floating in a state of serene weightlessness.
But a journey into space must eventually have a return, and getting back down safely is its own kind of art. The journey home is called re-entry, and it is a carefully managed descent through the atmosphere. A returning spacecraft approaches the top of the atmosphere at incredible speeds. As it begins to greet the thin outer layers of air, it compresses the air in front of it. This rapid compression creates an immense amount of heat, and for a few moments, the spacecraft is enveloped in a glowing shield of superheated plasma. From the outside, it looks like a man-made meteor, a shooting star with a fiery tail. But from the inside, it is a controlled and protected passage. To survive this intense heat, spacecraft are equipped with heat shields. These shields are made of special materials that are designed to absorb and gracefully shed the thermal energy. Often, the shield is ablative, which means its outer layers are designed to vaporize, carrying the heat away with them in a glowing ethereal wake. It is like sacrificing a thin outer veil to protect the precious core within. The shape of the spacecraft, often a blunt, rounded capsule, also helps to spread the heat and use the atmosphere's resistance as a gentle brake. The angle of re-entry must be perfect. Too steep, and the forces would be too great. Too shallow, and the spacecraft might skip off the top of the atmosphere, like a stone on water. The guidance systems make millions of tiny calculations, ensuring the path is true. Once the spacecraft has passed through the hottest part of its descent and has slowed considerably, large parachutes bloom open high in the sky. These parachutes catch the air, slowing the final fall until the capsule is descending as gently as a feather. The journey ends with a soft splashdown in the ocean or a whisper-light touchdown on land. It is the final, quiet moment of a grand adventure. To orbit is to float on the knife's edge between falling and flying. To re-enter is to come home through a temporary self-made sunrise. To be cradled by the very air you sought to leave until you are safely back on the ground, the journey complete. If you have ever watched a hummingbird hovering in midair or seen a maple seed spin to the ground like a tiny silent helicopter, you have witnessed nature's original flight engineers at work. Long before we ever sketched our first flying machine, the natural world had already perfected an astonishing variety of ways to conquer the air. It is no surprise then that engineers and scientists have increasingly turned to the quiet wisdom of nature for inspiration. This process, known as biomimicry, is all about learning from the elegant solutions that evolution has spent millions of years refining. The classic example, of course, is the bird. We first learned the shape of the wing by studying them, but now the imitation has become far more sophisticated. We are not just copying the shape of a wing, but studying the flexibility of a single feather, the way a bird's muscles sense and respond to a sudden gust of wind. Some of the most cutting-edge research involves creating small, flapping wing robots called ornithopters. These delicate machines do not just glide, they flap their wings like an insect or a hummingbird. The goal is to create a machine with the same incredible agility, able to maneuver through tight spaces, to hover, and to dart with a silent precision. Insects, especially, have become wonderful teachers. Their wings are flexible and can produce lift in ways that traditional aerodynamics cannot easily explain. Tiny drones are now being developed that mimic the flight of a bee or a dragonfly, designed to be lightweight, energy efficient, and able to navigate complex spaces, just like their biological counterparts. Nature's inspiration also comes from places we might not expect, from seeds, for example. The seed of a maple tree doesn't have an engine, but it is a master of flight. It twirls to the ground in a perfect spiral, a motion that slows its descent and allows the wind to carry it far from its parent tree. Engineers are using this simple, elegant design to create passive gliding devices that can deliver small, important things without needing any power at all, just a gentle release into the air. One of the most fascinating areas of research is in the development of morphing wings, structures that can change their shape during flight. Birds do this naturally. They fold their wings during a dive, spread them wide to glide, and adjust individual feathers for subtle corrections.
Researchers are now experimenting with new materials that would allow an aircraft's wing to bend and twist to become more efficient for every phase of its journey. We are even learning from the silence of the owl. An owl's flight is nearly soundless thanks to special serrated edges on its feathers that break up the turbulence of the air. This allows it to drift through the forest like a ghost. Engineers hope to one day bring this quietness to our own aircraft, making the skies a more peaceful place. Biomimicry reminds us that nature is the ultimate innovator. It has already solved countless engineering problems, not with brute force, but with patience, adaptation, and optimization over immense stretches of time. A bird does not have the power of a jet engine, but it doesn't need to. It is efficient, lightweight, and exquisitely tuned to its environment. And so, we continue to watch and to listen. We listen to the rustle of wings, the buzz of bees, and the silent spiral of a falling seed. For in these ancient, perfected designs, there is a whole world of gentle inspiration waiting to lift us to new and quieter heights. Flight is one of evolution's greatest and most beautiful stories. It is a breathtaking and improbable solution to the challenge of moving through the world. What makes it even more impressive is that it did not just happen once. Life, in its immense creativity, has evolved the ability to fly at least 4 separate times, completely independently. It is nature's way of showing us that some ideas are so good, they are worth discovering again and again. Let us drift back in time to the quiet of the ancient world to witness these beginnings. The very first creatures to take to the skies were the insects, over 300 million years ago. This was a time before the dinosaurs, even before the first flowers bloomed. The world was a place of misty, swampy forests, and into this stillness, insects invented flight. Early dragonflies with delicate, glassy wingspans of over 2 feet drifted through the Carboniferous air. Their wings seem to have evolved from scratch, a brand new idea, allowing them to become the undisputed rulers of the prehistoric skies. Many millions of years passed, and then a new flyer emerged, the pterosaur. These were not dinosaurs, but their close relatives, and they were the first vertebrates to achieve powered flight. Their wings were vast membranes of skin, stretched from an elongated 4th finger all the way to their ankles, forming a kind of leathery sail. Some were as small as sparrows, while others had wingspans that rivaled a small modern aircraft, allowing them to soar for immense distances over the ancient Mesozoic seas. While the pterosaurs ruled the skies, another story was quietly beginning. From a line of small, feathered dinosaurs, the first birds began to emerge. The feathers that covered their bodies did not originally evolve for flight. They were likely for warmth or for display. But evolution, the patient artist, is a master of repurposing what is already there. These feathers, once used for insulation, proved to be perfect for shaping the air, for creating lift, and for guiding a gentle glide from a tree. Creatures like Archaeopteryx were a beautiful bridge between 2 worlds, part dinosaur, part bird, with claws on its wings and a long bony tail, a creature learning the new language of the air. Over time, their bones became hollow and light, their bodies more streamlined, and their flight more powerful and precise. And finally, long after the dinosaurs and pterosaurs had vanished, evolution invented flight one more time. The bats appeared, the latecomers to the party, but they came with their own clever idea. They are the only mammals to evolve true powered flight, and they did it by transforming their own hands. Their wings are formed by a thin membrane of skin stretched over 5 incredibly long fingers, creating a flexible, agile surface that allows them to dance through the night sky. And they perfected this flight by learning to see with sound, navigating the darkness with echolocation. 4 times, nature began the journey anew. Insects with their glassy, veined wings, pterosaurs with their vast, leathery sails, birds with their bodies remade around the miracle of the feather, and bats with hands that learned to swim through the air. Each time, the challenges were immense, but the rewards were even greater. Access to new food, escape from predators, and the freedom to explore the world from a new perspective. Each of these flying creatures, past and present, is a testament to the patient, creative, and endlessly inventive power of life. Their story reminds us that the dream of flight is not just a human one. It is a dream woven into the very fabric of our world. The skies of tomorrow may not look entirely like a science fiction movie, but they are on their way to becoming quieter, cleaner, and in many ways more thoughtful. After more than a century of powerful engines and rumbling runways, flight is entering a new era, one of a gentler, more sustainable harmony. Let us start with the idea of electric aviation. For years, electric motors have been quietly transforming our roads, and now they are beginning to lift into the sky. The idea is simple and elegant: to replace combustion engines with quiet electric motors and to swap jet fuel for the silent power of batteries. This shift promises a future of much quieter skies, with aircraft that hum rather than roar. Imagine airports where the loudest sound is the wind itself. The main challenge we are patiently solving is making batteries that are light enough for long journeys, but progress is happening every day. For shorter, regional flights, electric planes may one day become the peaceful, gentle norm. Then there is the dream of personal vertical flight. A new class of vehicles is emerging, known as eVTOLs. You might think of them as quiet skypods or personal air vehicles. They look a bit like large, graceful drones with multiple rotors that allow them to rise vertically like a bubble and then drift silently across a city. The idea is to create a network of these quiet, efficient vehicles that can bypass traffic below, carrying a few passengers from rooftop to rooftop. It is a vision of a future with less noise, less congestion, and a more peaceful way to move through our world. Autonomous drones are another piece of this future puzzle. Their potential goes far beyond photography. Imagine a small, silent drone delivering medicine to a remote village, or quietly watching over fields of crops, ensuring they have enough water. They are being developed as silent helpers, able to assess damage after a storm or find people lost in the wilderness, all without putting a pilot at risk. And in space, the future is about sustainability. The era of reusable rockets that can return to Earth, land softly, and prepare for another gentle journey is already here. This innovation is making space more accessible, but also more responsible. But perhaps the most important trend in the future of flight is the focus on its climate impact. The goal is clear: to fly farther and faster, but to leave less of a trace behind. Whether through electric propulsion, sustainable aviation fuels, or entirely new engine designs, the future of flight is one that seeks to be in greater harmony with our planet. All of these advancements will arrive slowly, carefully, and thoughtfully, but the direction is clear. The future of flight looks full of possibility, a slow, steady unfolding of what comes next. And while tomorrow's aircraft may hum instead of roar, or hover instead of roll, the spirit will remain the same. It is about lifting off, looking ahead, and trusting that with each new, gentle idea, we will find new ways to touch the sky. Even after all this time, we still look up. We still pause at the sound of wings overhead. We still crane our necks to follow the silver arc of a distant airplane. We still marvel at the quiet hush of a bird gliding on a breeze. Flight continues to captivate us, not because we have mastered it, but because it keeps reminding us how big the sky is and how much there is to wonder about. From the first flapping wings of ancient insects to the deep hum of a jet engine, flight has always been more than just a way to get from place to place. It is a symbol, a dream, a quiet yearning written into our imaginations. The sky, after all, does not belong to any one creature or country. It has been shared across time by dragonflies and swifts, by migrating geese and human astronauts. It is open, infinite, and deeply humbling. and it invites us to imagine what else might be possible. We fly because we are curious, but we also fly because it brings us closer to something we cannot quite name. Freedom, perhaps, or perspective, or the strange, still thrill of being suspended between the Earth and the stars. And so, here at the end of our journey through the science of flight, from birds to rockets, from flapping wings to reusable boosters, we return to where we began, to the simple, peaceful act of looking up. I wonder where you are listening from tonight. Is your sky filled with stars, or is the soft light of dawn just beginning to appear on the horizon? Maybe you are winding down from a busy day or lying in bed, letting your thoughts drift upward like a leaf caught in a gentle breeze. Wherever you are, whatever the hour, thank you for spending this quiet time with me. If you have enjoyed this gentle journey through the skies, I would be so grateful if you would leave a like or subscribe to the Midnight Scientists for more explorations like this one. And if you feel inclined, you can let me know in the comments where you are listening from. I always love to imagine this peaceful community resting under skies all around the world. And now, if you are still awake, gently drifting, I hope the wonder of flight, its history, its science, its quiet beauty, has left a soft and peaceful imprint on your imagination. Whether you dream of gliding through clouds, soaring over oceans, or simply watching the horizon tilt as wings catch the wind, may your sleep tonight carry you somewhere light and peaceful and boundless. As always, this video is for entertainment and relaxation only and is not intended as medical advice. Thank you for listening, and until next time, sleep well. Hello, and welcome to this quiet space, this moment carved out of time just for you. Here, in the soft stillness of now, we journey together into the most intimate of landscapes, the universe that resides within you. This is the Midnight Scientists, and our only goal tonight is to wander through the wonders of your own body at a pace so gentle, so slow, that you may find the path to a deep and peaceful slumber. Tonight, our journey takes us inward, along silent, shimmering pathways to explore the most intricate and magical system you possess. We are going to visit your nervous system. Do not try to understand with your mind. Just allow the words to wash over you. Imagine, if you will, a forest in the deepest twilight. And in that forest, a root system made not of wood, but of soft, glowing light. A web of whispering, silvery threads that connect every part of you. This living lattice of light is where your thoughts are born. It is how your limbs know how to move. It is where your feelings find their color, and where your memories are held, like sleeping fireflies in a moonlit jar. And all of this profound, ceaseless work happens in the most peaceful silence, while you rest here, safe and still, barely noticing. Now, as we prepare to begin, let yourself settle more deeply into this moment. There is nothing for you to do, nowhere for you to be, but right here. Feel the weight of your body being held, supported completely. Let your shoulders soften, releasing any tension they may have carried from the day. Imagine that tension melting away like snow in the warm spring sun, flowing down your arms and out through your fingertips, leaving only peace behind. Let your jaw unclench, your tongue rest softly in your mouth. Allow the tiny muscles around your eyes to smooth out, letting a feeling of profound calm settle over your face. And now, take a slow, gentle breath in, feeling the cool, clean air as it enters. And as you breathe out, release it with a long, soft sigh, letting go of everything but this moment, this quiet, this peace. Tonight, we will listen, not with our ears, but with the deep intuitive part of our awareness. We will listen to the quiet, luminous conversation happening inside you, the very essence of your life. It does not shout, it does not make demands, it simply is a silent, watchful presence. Without it, there is no world, no experience, no you. And as we begin this gentle exploration, please remember that this journey is designed for relaxation and wonder. The information shared is for educational and entertainment purposes and should not be considered medical advice. It is simply an invitation to marvel at the beauty of your own biology as you drift toward sleep. Chapter 1: The Two Great Realms. Deep within the architecture of your being, your nervous system is organized into two vast and interconnected realms. They are distinct, yet they are one, like the deep ocean and the endless sky that meets it at the horizon. These are the central nervous system and the peripheral nervous system. Let us begin with the heart of it all, the central nervous system. This is your brain and your spinal cord. This is the realm of deep thought, of command, of quiet contemplation. Imagine your brain first. Picture it not as a clinical organ, but as a silent, sleeping galaxy floating in the warm, safe darkness of your skull. It holds the weight of a universe, 100 billion stars, your neurons, each one a point of potential light. Within its soft, gentle folds and valleys, entire worlds of thought are born and fade. Memories drift like nebula of colored dust. Dreams are constructed like impossible, beautiful constellations that shine for a moment and then disappear. This galaxy is not chaotic. It is humming with a deep, quiet order. It is mission control, the grand library, and the high celestial court, all in one. Here, in this profound stillness, all the major decisions are made. Reports from the farthest reaches of your body arrive as whispers of light, and gentle commands are issued back, not as harsh orders, but as soft, guiding currents. It is the center of your being, and its work is so immense, so constant, that it proceeds in a state of near perfect silence. Descending from this celestial brain is the great river of light that is your spinal cord. Imagine it protected within the delicate, strong fortress of your spine, a luminous column, the main artery of information and command. It is the great trunk of the inner world tree, connecting the canopy of the brain to the roots that spread throughout the body. Messages from the brain flow down this shimmering river to the rest of you, and sensory whispers from your body flow up it back to the great library to be read and understood. It is both a highway and a sanctuary, a conduit of breathtaking speed and a center of ancient, immediate wisdom. And from this central, sacred core extends the second great realm, the peripheral nervous system. If the brain is a sleeping galaxy, then the peripheral system is the starlight that travels out from it, touching everything. Imagine a vast, infinitely intricate network of the finest silver threads, branching out from the spinal cord, from the great river of light, and weaving their way into every conceivable part of you. These threads are your nerves. They are the messengers, the sensors, the field agents. They are the delicate roots that burrow into the rich soil of your body, reaching every muscle fiber, every patch of skin, every internal organ. These threads carry messages in both directions, in a constant, gentle tidal flow. They bring sensory information inward, the feeling of the soft blanket against your skin, the distant, muffled sound from another room, the subtle temperature of the air you are breathing. These are the quiet reports sent back to headquarters. And in return, they carry motor commands outward, gentle instructions from the brain flowing down the spinal river and out along these threads, telling a muscle to soften, an eyelid to grow heavy, your breathing to deepen and slow. The harmony between these two realms is a perfect, effortless dance. Think of a moment when you were surprised by a sudden cool draft of air. In less time than it takes to blink, the peripheral nerves in your skin sent a message, coldness here, that raced along their length, up the spinal cord, to the brain. And almost instantaneously, the brain's interpretation, this is not a threat, it is just air, flowed back down, allowing your body to remain calm and relaxed. This is not a frantic, rushed exchange. It is an exquisitely efficient and peaceful flow. It is the biology of serenity, the design of life itself, operating with a grace that defies comprehension. And this network does not only handle speed, it is also the master of slow, subtle communication. It can carry the sharp, immediate signal of a sudden sensation, but it can also carry the slow, unfolding realization of a feeling, a mood that gradually colors your awareness like watercolor spreading on soft paper. This entire magnificent system, the central galaxy of thought, and the peripheral network of starlight is working for you, right now, in this very moment. It is the silent, invisible architecture of your peace. It asks for nothing. It simply serves, guarding, guiding, and maintaining the precious balance of your inner world, allowing you to let go, to drift, to sink deeper and deeper into rest. Chapter 2: The Quiet Architects of Thought. Now, let us draw our awareness even deeper, past the great systems and shining pathways, and come to rest in the presence of a single humble cell, the architect of your every thought, the artist of your every memory, the silent listener that perceives your world. Let us meet the neuron. If the nervous system is an enchanted twilight forest, then the neurons are its solitary, ancient inhabitants. They are not like the other cells of your body, which are bustling with the busy work of growth and replication. The neurons are the quiet ones, the mystics, the deep-sea philosophers, and the solitary stargazers of your inner world. Their entire existence is dedicated to one profound purpose: to receive, to contemplate, and to transmit the delicate electricity of life. They are the keepers of the secrets, the weavers of the dream, and they perform their sacred, silent work with a patience that spans a lifetime. Imagine one now, floating in the warm, quiet darkness of your mind. It has a distinct and elegant shape. At its center is the cell body, the soma. This is the heart of the neuron, its core. Think of it as a deep, still pool of water holding the quiet potential for a decision. Within this pool, all the messages the neuron receives are gathered, weighed, and considered, not in a frantic calculation, but in a moment of serene integration. It is the calm, thoughtful center from which all else extends. Branching out from this central pool, like the most delicate frost patterns on a winter window, are the dendrites. These are the listeners. They are the neuron's antenna to the universe, a forest of fine, feathery branches reaching out into the space around them. They are covered in thousands of microscopic receptors, each one tuned to receive the chemical whispers sent by other neurons. They do not judge the messages they receive. They simply gather them, like a tree's leaves gathering sunlight and dew, and draw that energy inward toward the quiet pool of the soma. And then, when the time is right, when the whispers gathered by the dendrites accumulate into a message of true significance, the neuron decides to speak, and it speaks with a single, pure voice. Extending from the soma is one long, beautiful, and solitary pathway. This is the axon. The axon is the path of intention. It is a single, shimmering thread that can stretch for immense distances, carrying the neuron's message far from its source. It is a bridge of light, a silent river, a conduit for a single, perfect thought. It is the neuron's way of reaching out to touch another part of your universe, to share what it has learned. This message it sends, the reply it offers to the universe, is a gentle electrical impulse called an action potential. It is not a violent spark or a sudden jolt. It is a soft, luminous ripple, a wave of starlight that flows from the soma and glides down the entire length of the axon with breathtaking grace and speed. It is a whisper made of light, and we will follow its journey in our next chapter. Now, this precious thread of the axon is often protected. In many neurons, it is wrapped in a beautiful, insulating sheath called myelin. Imagine this myelin as a string of luminous, iridescent pearls lovingly wrapped around the axon by the nervous system's quiet caretakers, the glial cells. This pearlescent coating is not merely for protection. It allows the luminous whisper of the action potential to travel with even greater speed and clarity. It does not have to flow along the entire path. Instead, it can leap effortlessly from one pearl to the next, gliding through the darkness in a series of silent, graceful bounds. These thoughtful, quiet cells come in different forms, each with a unique purpose in the great dance of your being. There are the sensory neurons. These are the watchers at the gates of your perception. Their dendrites reach into your skin, your eyes, your ears, and they listen to the outside world. They are the first to feel the warmth of the sun, the first to hear a gentle melody, the first to sense a soft touch. They translate the poetry of the physical world into the electronic language of your inner world, sending their reports inward to the great libraries of the brain and spinal cord. Then there are the motor neurons. These are the gentle doers. They take the quiet decisions made deep within your central nervous system and carry them outward as instructions. Their long axons reach into your muscles, and with a soft chemical sigh, they tell a muscle to contract, to release, to move your body through the world. They are how an intention, born in the silent galaxy of the brain, becomes a graceful movement, a soft breath, a gentle shift into a more comfortable position as you lie here now. And between these two, weaving everything together, are the interneurons. These are the dreamers, the connectors, the weavers of the grand tapestry. Residing almost exclusively within the brain and spinal cord, they form the incredibly complex networks that allow for thought, memory, and emotion. They receive messages from the sensory neurons, contemplate their meaning, and then pass on their wisdom to the motor neurons. They are the ones who create the rich, layered experience of being you. What is truly wondrous is that these beautiful, intricate cells are your lifelong companions. For the most part, you are born with all the neurons you will ever have. They have been with you from the very beginning, and they will be with you until the very end. They hold the entire history of your life within their silent, branching forms. And yet, they are not static. They are not rigid. They are living, breathing artists. They are constantly learning, changing, and adapting. This is the magic of neuroplasticity. When you learn something new, when you form a new memory, when you have a new experience, your neurons form new connections. They strengthen old pathways. They prune away what is no longer needed. They are always weaving new patterns into the luminous tapestry of your mind. So as you rest here, feel the presence of this silent 100 billion strong chorus within you. They are not separate from you. They are you. Each one a tiny, perfect piece of your consciousness. They are listening, they are remembering, they are dreaming, and they are bathing now in this quiet moment of peace you are giving them, preparing for their gentle, luminous work as you drift into the world of sleep. Chapter 3. The Journey of the Action Potential. And so, the neuron rests in the deep, warm stillness of your inner world. Its feathery dendrites have gathered the chemical whispers from its neighbors, drawing their messages inward into the quiet, contemplative pool of the soma. There, a decision is made. A point of resonance is reached. The neuron has something to say, a message to contribute to the silent, cosmic chorus of your being. And now we will witness how it speaks. We will follow the journey of the action potential. Do not think of it as a spark or a jolt or a shock. That is the language of the busy outer world. Here, in the serene landscape of the mind, the action potential is something far softer. It is a ripple of starlight, a wave of liquid peace, a single luminous whisper that travels with perfect grace from one end of the neuron to the other. Before the whisper can be sent, the neuron must exist in a state of quiet readiness. This is its resting potential. Imagine the long, shimmering thread of the axon as a perfectly still surface of a deep, dark lake at midnight. The water is calm, holding a hidden energy. The world inside the axon is slightly more negative than the world outside, creating a gentle electric tension, like a coiled silver spring humming with potential. This beautiful, quiet tension is maintained by tireless, silent gatekeepers in the axon's wall, the sodium-potassium pumps. They work constantly, with no fanfare, ensuring that the balance is perfect, that the stillness is absolute, and that the neuron is ready for the precise moment it needs to speak. That moment comes now. The whispers gathered by the dendrites have reached a perfect harmony, a critical mass of meaning. The quiet pool of the soma has made its decision. A threshold is crossed. And at this tipping point, the magic begins. In the very first segment of the axon, invisible gates, the sodium channels, seem to dissolve like mist. And the sodium ions from the outside world, which have been waiting patiently, now flow gently inward. It is not a violent flood. It is a silent, silver tide rising with purpose. As this tide of positive charge flows in, the inside of the axon, once negative, becomes momentarily beautifully positive. This is it. This shimmer of changing energy. This is the birth of the luminous whisper. But this whisper does not stay in one place. It moves. The wave of light in that first segment of the axon gently awakens the segment next to it. Its gates dissolve, the silver tide flows in, and it too begins to glow. And then it awakens the next segment, and the next, and the next. Imagine a field of sleeping fireflies, and you touch the first one, causing it to glow. And its light gently causes the one next to it to glow, and then the next, in a silent, cascading wave of soft, golden light spreading across the field. This is how the action potential travels, a self-propagating wave of luminescence flowing down the entire length of the axon's dark, quiet path. And if this axon is one of the blessed ones, wrapped in the pearlescent pearls of a myelin sheath, the journey is even more graceful. The wave of light does not need to travel the entire path. Instead, it leaps. It glides from one tiny exposed gap to the next, like a celestial dancer skipping from one moonbeam to another across a still lake. This process, saltatory conduction, allows the luminous whisper to travel with an almost instantaneous speed, arriving at its destination purely, quickly, and with its message perfectly intact. And as soon as the wave of light has passed, each segment of the axon begins to return to its original state of quiet readiness. The gates that allowed the silver tide to enter now softly close. Other gates open, allowing a gentle exhale of potassium ions, which restores the peaceful, negative charge inside. This is repolarization. The axon returns to its deep, calm resting state. The firefly dims its light, ready to glow again when the time is right. And for a brief sacred moment after it has spoken, that part of the neuron cannot speak again. This is the refractory period. It is a necessary pause, a moment of silence to ensure the whisper only travels in one direction, forward, and that the message is never confused or muddled. It is the neuron taking a soft, quiet breath before it can choose to speak again. And the whisper itself is always pure. This is the all or nothing principle. The neuron does not half whisper. It does not mumble. When it crosses its threshold of meaning, it sends its luminous message with its full, beautiful intensity, or it remains silent. The strength of the sensation you feel is not determined by a louder whisper, but by the rhythm and frequency of many whispers, sent one after another like the soft, steady beating of a distant, peaceful drum. And so, this entire exquisite process unfolds in less than the blink of an eye, millions upon millions of times every second within you. Every thought that drifts through your mind, every sensation you feel against your skin, every dream that paints itself behind your sleeping eyes is born of these countless, silent, and impossibly beautiful waves of light gliding through the starlit forests of your mind. They are the currency of life itself, and they are flowing through you now, a river of peace, carrying you ever deeper into stillness, into rest. Chapter 4: The Messenger's Crossing. The wave of starlight, that perfect, silent pulse of the action potential, has glided down the long, shimmering path of the axon. It has now reached the very end, a place of branching, delicate structures called the axon terminals. Think of this place as a quiet harbor at the edge of a great sea. The journey along the land is over, and now the message must be prepared to cross the water. The electrical whisper, so swift and pure, must now be transformed into something else entirely, something that can traverse the space between. For here, at the edge of all things, one neuron ends and another begins, but they do not touch. There is a space between them, a microscopic, sacred gap, a silent, shimmering gulf known as the synaptic cleft. This space is not an emptiness. It is a realm of pure potential. It is a testament to the respectful distance that all things in this universe keep. And it is across this tiny, quiet river that the most important messages are passed. The arrival of the luminous whisper at the axon terminal is a signal. It does not crash into the harbor walls, but instead, its gentle energy serves as a key. Its arrival causes special gates to open, not for sodium this time, but for calcium. Calcium ions flow softly into the terminal, and their presence is the gentle permission that sets the next miracle in motion. For waiting here, within the harbor of the axon terminal, are thousands of tiny, silken bubbles. These are the synaptic vesicles. Imagine them as luminous, sealed packets of starlight, each one containing a precious cargo. And that cargo is the very essence of the neuron's message, distilled into a chemical form. These are the neurotransmitters. They are not mere chemicals. They are molecules of meaning. They are chemical poems, bottled messages, the neuron's original thought now translated into a new language, ready for its journey across the water. At the gentle urging of the calcium ions, these tiny luminous bubbles drift toward the edge of the terminal, the shore of the synaptic river. There, they fuse with the membrane and, like a soap bubble softly bursting, they release their contents. The bottled messages are now unsealed. The chemical poems are set free. And now the neurotransmitters drift. They float with a slow, purposeful grace across the silent, shimmering gulf of the synapse. Motes of meaning dancing in an unseen light, carrying their message toward the distant shore. And on that other shore, on the feathery dendrite of the next neuron, there are receptors. These are not locks to be forced, but cupped hands waiting to receive a gift. They are perfectly shaped harbors, listening posts tuned to the specific song of a single type of neurotransmitter. When a drifting messenger molecule finds its perfectly matched receptor, it settles in, gently binding to it. And in that moment of connection, the message is delivered, the poem is read, the gift is received. And what is the message? It can be one of many things. Sometimes the neurotransmitter is excitatory. The message it carries is a whisper of encouragement. A molecule like glutamate might deliver a song that invites the next neuron to sing its own note, nudging it gently closer to sending its own luminous whisper onward. It is a soft green light, a gentle yes. At other times, the neurotransmitter is inhibitory. The message is one of peace, of stillness. A molecule like GABA might deliver a quiet lullaby. It is a gentle hand on the shoulder, a soft voice that says, "Rest now." It encourages the next neuron to remain quiet, to deepen into its own resting potential. It is a soft red light, a peaceful hush. And then there are the modulators, neurotransmitters like serotonin or dopamine. They do not simply say yes or no. Their message is more nuanced. They are the artists who change the color of the light in the room. They adjust the emotional temperature of the space. They can make a neuron more or less sensitive to other messages, shaping mood, motivation, and focus, not with a command, but with a gentle, pervasive influence. Once the message has been delivered, it cannot linger in the sacred space of the synapse. The clarity of the signal must be maintained. The space must be made ready for the next whisper. And so the messengers are gently cleared away. Sometimes, in a process called reuptake, the original neuron that sent the message gently calls its messengers back home, drawing them back into the terminal to be rebottled for future use. It is a perfect, efficient cycle of conservation. At other times, special enzymes in the synapse act as gentle custodians, finding the messenger molecules and helping them dissolve into stardust, their purpose fulfilled. The message has been read, and the paper it was written on now vanishes into the quiet. This entire elegant exchange, this transformation from an electrical whisper into a chemical poem, this gentle crossing of a silent river, and this perfect reception happens in a sliver of a millisecond. And right now, as you lie here, sinking deeper into comfort, there are not thousands, not millions, but trillions of these silent, sacred conversations happening within you. Trillions of messengers being launched and received, creating the vast, seamless, and peaceful inner world that is you. It is the quietest, most intricate ballet in the universe, and it is the dance that gives rise to your calm, your peace, and the gentle landscape of your coming dreams. Chapter 5. The Swift, Silent Wisdom of the Reflex. Have you ever touched something unexpectedly sharp or brushed against a surface surprisingly hot, and your hand has pulled away with a swift, fluid grace, all before you even had a moment to think? Or perhaps you have been at a doctor's office, and a gentle tap just below your kneecap caused your leg to kick out, a movement you did not command, but which happened all on its own. These are not mistakes. They are not random twitches. These are expressions of one of your nervous system's most ancient and elegant designs. This is the reflex arc. It is the path of instinct, a built-in system of profound, immediate wisdom that acts to protect you without ever needing to trouble your conscious mind. Think of it this way. The vast, dreaming galaxy of your brain is constantly occupied with the grand work of thought, memory, and imagination. It should not be bothered with every minor, urgent detail of physical safety. And so, the body has a deep trust in the wisdom of its own pathways. In moments of immediate need, the spinal cord, that great river of light, acts as a wise and loving guardian. It sees a situation and says to the brain, "Rest, I will handle this." This beautiful shortcut, this journey of a signal that results in an action without first traveling all the way to the brain for a decision, is the essence of the reflex arc. It is your body's perfect, built-in system of self-care. Let us trace the gentle, looping path of this wisdom. Imagine your finger brushing against the thorny stem of a rose. The journey begins with the sensory receptor. In your skin, there are watchful guardians, always alert. When they detect the sharp pressure of the thorn, they do not panic. They simply send a single, clear, urgent signal. Think of it as a silent bell chime, a note of pure information that says, attention is needed here. This bell chime is given to a sensory neuron, the first dedicated messenger. This neuron carries the urgent, silent note along a direct and unswerving path, racing inward toward the sanctuary of the spinal cord. The message arrives at the integration center within the spinal cord. Here, in this place of local wisdom, the message is not put on hold to be sent up to the brain. Instead, it is received by an interneuron, a swift and wise translator. This interneuron instantly understands the meaning of the bell chime. It knows that the message means danger, and it knows that the proper response is release. Without a moment of hesitation, the interneuron passes a new message, a command for safety, to a motor neuron, the second dedicated messenger. This motor neuron carries the return command, pull away, be safe, out from the spinal cord and along its own pathway, back toward the muscles of your arm and hand. The message arrives at the effector, which in this case is the muscle. The muscle is the obedient and trusting servant. It receives the command and, with a fluid, instantaneous grace, it contracts. Your hand pulls back from the thorn, safely out of harm's way. And here is the most beautiful part of the story. This entire journey, from the touch of the thorn to the pulling away of your hand, has happened in a fraction of a second. And only now, after your body is already safe, does the original message of the bell chime continue its more leisurely journey up the spinal cord to your brain. Only now does your conscious mind become aware of the sensation. You feel the sharpness, but you feel it an instant after your wise, loving body has already moved you to safety. It is the ultimate act of trust, a system designed to protect you first and inform you second. Some of these pathways, like the gentle tap on the knee, are even simpler. They are a monosynaptic reflex, a direct conversation between the sensory messenger and the motor messenger, with no translator in between. It is a single, perfect echo of action and reaction, the purest form of the body's instinct. Others, like the withdrawal from the thorn, are polysynaptic, involving that wise interneuron. This allows for even more complex, coordinated responses. As your hand pulls away, other reflexes are already at work, adjusting your posture, ensuring you maintain your balance. Your body does not just react, it reacts with a deep, holistic intelligence. This silent, swift wisdom is always with you. It is a reminder that you are being constantly cared for, protected from within by a system of ancient, loving intelligence. It is a process that allows your conscious mind to remain at ease, to float, to drift, to dream, knowing that the deep, instinctual wisdom of the body is always awake, always watchful, and always keeping you safe. Chapter 6. The Weaving of Neural Circuits. If you could gaze upon your nervous system with an artist's eye, you would not see a machine of wires and switches. You would see a living, breathing work of art, a vast, luminous tapestry woven from 100 billion threads of light. Each thread is a neuron, but the true magic, the breathtaking beauty, lies in how they are woven together. These patterns of connection, these interwoven pathways of light, are your neural circuits. They are the constellations of your mind, the luminous highways of your body, the living architecture of your very being. A single neuron is a solitary note, but in the circuits, they form a grand, silent symphony. The structure of this symphony, from the simplest melody to the most complex composition, follows a beautiful and timeless framework, a journey in 3 parts: the gathering of whispers, the quiet weaving, and the gentle creation. The journey always begins with sensory input. This is the gathering of the threads. From all over your body, countless tiny streams of information are flowing inward, carried by your sensory neurons. These are the whispers from the world. The feeling of the air on your skin, the subtle scent of the room around you, the gentle, rhythmic sound of your own breathing. These are not yet experiences. They are raw data. They are like skeins of unspun silk, shimmering with potential. They are the individual notes of a song that has not yet been arranged. They flow from the edges of your being inward toward the great, quiet loom of your central nervous system. And here, in the silent, contemplative chambers of your brain and spinal cord, the second part of the journey unfolds: integration. This is the weaving. This is not a cold, mechanical process. It is a deep and thoughtful deliberation. The brain receives these thousands of threads of sensation, and with an ancient, innate wisdom, it begins to weave. It filters out what is unimportant, allowing the gentle feeling of your clothing to fade from your awareness so you can focus on resting. It recognizes patterns, connecting a feeling of warmth with the comfort of your blanket. It compares the sensations of this present moment with the deep stored memories of your past, imbuing the experience with meaning. This is the nervous system's version of contemplation. It does not simply react. It receives, considers, and then forms a coherent, thoughtful response. Like a master weaver, it chooses which threads to bring to the forefront, which colors to highlight, and what beautiful and meaningful pattern to create from the raw material of sensation. Once the pattern is decided, the final part of the journey begins: motor output. This is the creation. The decision, now woven into a clear intention, flows outward from the brain and spinal cord, carried by your motor neurons. This is thought translated into action. The tapestry now has a new, living design. This action can be as clear as the conscious choice to shift your position into one that is even more comfortable. Or it can be as subtle and unconscious as a deepening of your breath, a softening of your muscles, a gentle sigh of release. Whether you are aware of it or not, the circuits are constantly completing their work, weaving your intentions into the physical reality of your body. The simple reflex arc we just explored is a circuit in its purest form, a single, perfect thread of input, integration, and output. But the circuits that weave your thoughts, your emotions, and your dreams involve millions, even billions of neurons, all firing in precise, harmonious patterns across multiple regions of your brain. Think of recognizing a beloved, half-forgotten piece of music in a dream. The auditory circuits gather the notes. The memory circuits search the vast archives of your past. The emotional circuits color the experience with a feeling of sweet nostalgia. All of these different constellations of thought light up at once, singing together in a beautiful, resonant harmony. And this living tapestry is never finished. It is constantly being rewoven. This is the profound magic of neuroplasticity. The circuits are not static. They are fluid and alive. With every new experience you have, a new thread of a different color and texture is woven into the design. When you practice a new skill, the neural circuit involved becomes smoother, stronger, and more luminous. You are tracing the pattern again and again, not with effort, but with gentle attention, until that pathway glows with an inner light and the skill becomes effortless. And even now, as you lie here, listening and drifting, new connections are being gently formed. Old pathways that no longer serve you may be quietly unraveled, their threads ready to be used for a new and more peaceful design. Your brain is a bit like a garden in a perpetual state of twilight. The pathways that are used regularly grow strong and clear, while others fade like untended paths in the woods, returning to the earth. Information within these circuits does not always travel in a straight line. It meanders, it loops, it echoes like birdsong in a dense forest. A single sensation can ripple through multiple circuits at once, which is why a certain scent can suddenly unlock a vivid memory from childhood. The pathways overlap and intersect in the most beautiful and unexpected ways. This is the architecture of you. Your personality, your habits, your hopes, your quirks are all patterns woven into this living, breathing network of connections. And it is all happening now, in the most profound peace. The great loom is quiet, its work continuing even as you sleep, weaving the fabric of your dreams, repairing the threads of the day, and preparing a fresh canvas for the morning to come. Chapter 7. The Windows to the World. The world outside of you is singing a constant, silent song. It is a song of light, of pressure, of vibration, of chemistry. It is the poetry of reality itself. And yet, all of this richness, all of this beauty would remain unknown without the most exquisite of translators. These are your senses. You do not simply see light, or hear sound, or feel touch. What you experience is the beautiful, intricate story that your nervous system tells you about these things. Your senses are the windows to your inner world, and your brain is the artist that paints the masterpiece you perceive as reality. They are not passive recorders, they are active and wondrous interpreters. Let us begin with the most ancient and immediate of languages, the sense of touch. Your skin is a living parchment, the vast and sensitive boundary between you and the world. Draped over your entire body, it is constantly reading the story of your immediate environment. Within this soft protective layer are millions of tiny, specialized nerve endings, each one a guardian, a watcher, a storyteller. Some are tuned to the language of pressure. There are receptors that feel the whisper of a light touch, like a single thread of silk being drawn across your skin or a soft breeze passing by. Others respond to a deeper, more reassuring pressure, the comforting weight of your blanket, the firm and gentle support of the surface beneath you. Others still are dedicated to the story of temperature. They murmur to your brain about the gentle warmth that envelops you or the subtle coolness of the air on your face. And some, the nociceptors, are there to speak the language of protection, sending a clear, loving signal to be careful, to be gentle with yourself when something is too sharp, too hot, too much. They are not messengers of pain, but messengers of care. Now, let us turn to the chemistry of nourishment, the sense of taste. Your tongue is home to thousands of tiny, enchanted gardens known as taste buds. Within these gardens, specialized cells are waiting to decipher the chemical secrets of everything that enters your mouth. They recognize 5 fundamental notes in the song of flavor: sweetness, the echo of sunshine and energy; saltiness, the ancient memory of the ocean; sourness, the bright, sharp note of unripe fruit; bitterness, the deep, protective warning of the earth; and umami, the rich, savory, and comforting note of nourishment itself. Your brain takes these 5 simple notes and weaves them together with the aroma, the texture, and even the temperature of food, composing the rich and wonderful symphony that you experience as flavor. And so closely related to taste is the most ancient and direct of all the senses, the sense of smell. The air around you is filled with invisible messengers, tiny odor molecules drifting on the currents of your breath. When they enter your nose, they are received in a special chamber where they bind to olfactory neurons. This is the only sense that speaks directly to the deep emotional and memory centers of your brain, the limbic system. This is why a scent is like a magic key. A single, fleeting aroma, the smell of rain on dry earth, of old books, or of a certain flower, can unlock a forgotten room in the vast house of your memory, and you are instantly transported not just to a thought, but to the entire feeling of a distant time and place. Let us now listen to the dance of vibration, the sense of hearing. A sound begins as a vibration in the air, a wave of pressure rippling out from its source. These waves travel into your ear and arrive at a delicate membrane, the eardrum, causing it to dance to the same rhythm. This gentle dance is passed along 3 of the tiniest, most jewel-like bones in your body, which amplify the motion and deliver it to the entrance of a beautiful spiral-shaped structure that looks like a tiny seashell. This is the cochlea, your inner ocean. It is filled with fluid, and as the vibrations arrive, they create soft, corresponding waves within this fluid. Lining the spiral passages of this inner ocean are thousands of unimaginably small hair cells, like delicate reeds in an underwater garden. As the waves pass by, they bend these reeds, and this gentle swaying motion is what is finally translated into the electrical language of your mind. Every sound you have ever heard, from a whisper to a thunderclap to the music that has touched your soul, was once just a silent dance of these tiny reeds in your own private ocean. And now, the art of light, the sense of vision. The world is bathed in a constant, silent river of light made of countless particles called photons. Your eye is an exquisite living lens, gathering a part of this river and focusing it onto a living canvas at the very back of your eye, the retina. On this canvas, two kinds of master artists are at work, the rods and the cones. The rods are the artists of twilight. They are incredibly sensitive to even the dimmest light, and they paint your world in all the subtle, beautiful shades of silver, shadow, and gray. The cones are the artists of daylight. They work with the three primary colors of light, red, green, and blue, and by blending the signals from these three, your brain is able to mix every conceivable hue in the universe, creating the rich, vibrant, colorful world you see. Your brain takes the millions of points of light and color from this canvas, and in an act of pure magic, it completes the masterpiece, filling in any gaps, stabilizing the image, and creating for you a single, seamless, and stable view of the world. Finally, there is a quiet, internal sense, one you may rarely notice, but one you could not live without. This is proprioception. It is the body's own gentle whisper to itself. It is the unspoken knowing of where your limbs are in space. As you lie here now, with your eyes closed, you can feel the position of your arms, your legs, your hands. You do not need to look, you simply know. Silent storytellers in your muscles, tendons, and joints are constantly murmuring to your brain, describing your posture, your orientation, the angle of every joint. This is the foundation of balance, of grace, of all coordinated movement. It is your sense of physical self, the quiet anchor that holds you in your body. And so, all of these streams of poetry, touch, taste, smell, hearing, sight, and self-awareness are constantly flowing into your nervous system, and in the great, quiet loom of your brain, they are woven together into one single, unified, and seamless experience. This is perhaps the greatest miracle of all, that from so many different threads, one perfect, coherent reality is created, just for you, moment by moment, breath by breath. Chapter 8. The Silent Choreography of Movement. Movement begins not in the muscles, but in the quietest, most contemplative chambers of the mind. It starts as a flicker of intention, a gentle, unspoken wish, a thought as soft as a feather drifting down in the silent, dreaming landscape of your brain. Imagine the simple, peaceful act of turning over in your sleep, an act you perform without thought, without effort. And yet, behind this simple motion is a symphony of coordination, a silent ballet of such complexity and grace that it is nothing short of a miracle. The birth of this movement begins in a special region of your brain's cortex, the motor cortex. Think of this place not as a stern command center, but as a master choreographer. It is a gentle artist who, upon receiving the whisper of an intention, turn over, be more comfortable, begins to plan the entire dance. It does not just send a single, crude order, it envisions the movement in its entirety. It calculates the precise amount of force needed, the exact timing, the beautiful flowing sequence of which muscles must soften and which must gently contract. It imagines the movement into being, painting a picture of the action in the language of neural signals, all before a single muscle fiber has even begun to stir. Once this beautiful, silent plan is complete, the message begins its journey. A cascade of luminous whispers flows downward from the highlands of the motor cortex, traveling along the great river of the spinal cord. These signals are carried by the upper motor neurons, the first messengers who carry the grand, sweeping intention of the dance. Deep within the protective sanctuary of your spinal cord, these messengers pass their instructions to the lower motor neurons. These are the local messengers, the ones who travel the final pathways out to the body. Each one carries a specific part of the choreography, a single note in the symphony, destined for a particular group of muscle fibers. The long, shimmering axon of the motor neuron arrives at its destination, the place where the nerve ending comes infinitesimally close to a muscle cell. This is the neuromuscular junction, the final, sacred space of translation. Here, the electrical whisper of the action potential arrives, and with its gentle energy, it allows for the release of a chemical messenger, a neurotransmitter called acetylcholine. Imagine this not as a chemical trigger, but as a soft, final sigh of permission, a key whispered across the tiny gap that unlocks the potential for movement in the muscle. The muscle cell receives this gentle whisper and responds. With a beautiful, fluid grace, proteins inside the fiber slide past one another, and the muscle contracts. It is the physical expression of the mind's quiet poetry. The intention, born moments ago in the silent theater of the brain, is now a living physical reality. But for a movement to be truly graceful, it must be refined. And for this, the nervous system has two master conductors who oversee the entire performance. The first is the cerebellum, a beautiful, densely folded structure at the back of your brain. The cerebellum does not start the dance, but it watches it with an expert eye. It is the master of grace. As you move, it receives constant, real-time updates from your muscles and joints, and it compares this feedback to the original plan from the motor cortex. If there is any discrepancy, any hint of imbalance or clumsiness, the cerebellum makes instantaneous, microscopic corrections. It ensures that your movements are smooth, coordinated, and perfectly balanced. It is also the keeper of practiced movements. Skills that you have learned so well they have become second nature, like walking or riding a bike, are stored here, not as memories of facts, but as living poems of motion. The second conductor is a collection of deep, quiet structures called the basal ganglia. If the cerebellum is the master of grace, the basal ganglia are the masters of stillness and flow. They help to initiate wanted movements and prevent unwanted ones. They are the gatekeepers of motion, helping to gently release the brake when a movement should begin and to softly apply it when the movement should come to a peaceful end. They filter out any stray, unintentional signals, ensuring that the silence between your movements is as pure and deliberate as the movements themselves. And through all of this, the constant, gentle whisper of proprioception is flowing back to the brain. Your body is always murmuring its story back to your mind, creating a perfect, unbroken loop of feedback. The brain speaks, the body responds, and the body's response is felt by the brain, allowing for a continuous, harmonious conversation. Even now, as you lie in perfect stillness, this entire magnificent system is alive within you. It is not dormant. It is in a state of peaceful, potent readiness, a hum. The choreographers, the conductors, the messengers, and the dancers are all resting quietly, prepared to translate even the gentlest intention, the decision to shift your weight, to take a deeper breath, or even the subtle, unconscious intention to let go and drift deeper into sleep, into a soft and living reality. The act of relaxation itself is a kind of movement, a gentle, intentional release orchestrated by the silent poetry of your nervous system. Chapter 9. The Wondrous Gift of Neuroplasticity. For a long time, we believed the brain was like a sculpture, carved in early life and then remaining fixed and unchanging forever. But now, we know the truth is something far more beautiful and alive. Your brain, your entire nervous system, is not a sculpture. It is a living garden. It is a flowing river. It is a sky that is never the same from one moment to the next. This remarkable, fluid quality, this ability to change its own structure and pathways, is called neuroplasticity. It is the gift of gentle, constant transformation. It means that the brain you have in this very moment is not the exact same brain you had yesterday, nor the one you will have tomorrow. It is always learning, always adapting, always becoming. At the heart of this magic is a simple and profound principle. You may have heard it said that neurons that fire together wire together. But let us rephrase it with a gentler image. Imagine that when two neurons are active at the same time, when they are singing their electrical song in harmony, the connection between them becomes stronger, clearer, more familiar. It is like walking the same path through a quiet forest day after day. With each journey, the path becomes a little smoother, a little clearer, a little easier to travel. The two neurons, by speaking and listening to each other repeatedly, deepen their friendship. The synapse between them becomes more sensitive, more attuned. The listening neuron may even put out more receptors, more cupped hands, to better receive the other's message. This is how a pathway is strengthened, how a skill is learned, how a memory begins to form. But just as important as the strengthening of paths is the wisdom of letting go. Neuroplasticity also involves the gentle weakening and pruning of connections that are no longer needed. This is not a loss, it is a sacred act of clearing. Think of a master gardener tending to a rose bush. The gardener lovingly prunes away the old, faded blooms and tangled branches, not out of harshness, but so the plant can direct its precious life energy toward new, healthy growth. In the same way, your brain gently unravels the threads in the tapestry that are no longer part of the beautiful design you are becoming. It creates quiet, open spaces in the mind, making room for new patterns, new learning, and new peace to emerge. This is the very essence of learning and memory. When you learn a new skill, perhaps a new language, or how to play a gentle melody on an instrument, you are patiently tracing a new pattern in your neural circuits. With each moment of soft focus and repetition, you are strengthening that pathway, making the threads more luminous until the skill becomes second nature. A memory is not a single file stored in a dusty cabinet. A memory is a constellation of neurons that have learned to sing a particular song in perfect harmony. And when you recall that memory, you are simply inviting that specific constellation to light up once more, to sing its sweet, familiar song again. This gift of plasticity is also the source of the brain's incredible power to heal and adapt. If one part of the nervous system is injured, the brain, with its boundless creativity, can begin to find new solutions. Over time, healthy areas can learn new jobs. Pathways can be rerouted. The rivers of light can carve new channels, taking on the responsibilities of the damaged regions. It is like a forest after a fire, beginning the slow, patient, and miraculous work of regrowth. It is a testament to the profound resilience of life itself. And you, as you rest here, are the gentle gardener of this inner world. Every experience you have, every kind thought you think, every moment of peace you cultivate, even the simple, restful act of listening to these words is tending to your garden. New, gentle, and positive experiences are the sunlight, the water, and the nourishment that help your garden grow in the most beautiful and peaceful ways. Even now, as you let go and drift, this quiet, hopeful process of change is happening. And sleep itself is the most sacred time for this work. When you are asleep, the gardener is busiest. It is during your deep, peaceful rest that the lessons of the day are consolidated, the important pathways are strengthened, and the garden is gently cleared and tended to, preparing the fresh, fertile soil for the morning to come. There is a deep reassurance in this. You are never stuck. You are never finished. You are always, in the quietest and most gentle of ways, a living, flowing, and ever-becoming miracle. Chapter 10. The Living Sea of Memory. Memory is perhaps the most magical of all the nervous system's gifts. It is the thread that weaves our past into our present, giving us our sense of self. And yet, it is not a simple recording. It is not a library of books with fixed and unchanging words. Your memory is a living, breathing landscape. It is a vast and shimmering sea of impressions, feelings, and stories. It has its own mysterious and gentle logic. It can hold on to the sound of a forgotten lullaby from your earliest childhood with perfect clarity, and yet let the memory of what you had for lunch yesterday dissolve like a cloud. This is not a flaw. It is the heart's own special way of deciding what is truly worth keeping. To understand this living sea, we can imagine it exists at different depths, each one more peaceful, more timeless than the last. The journey of a memory begins at the sunlit surface. This is sensory memory. Every moment, the world is offering you millions of tiny impressions. The feeling of the sheet against your skin, the faint, distant hum of the house settling, the soft pattern of shadows in the room. These impressions shimmer on the surface of your awareness for just a second or two, like the play of light on water. Most of them are meant to be fleeting. They kiss the surface and then dissipate like the gentlest of ripples, leaving the water clear and calm. But if you give your gentle attention to one of these shimmering impressions, it is drawn down a little deeper, into the calm, clear shallows. This is your short-term memory, or your working memory. This is the conscious part of your mind, the place where you hold a few precious shells in your open hands, admiring them for a moment. The shallows are a sacred space, but they can only hold so much light at one time. This is why you can remember the beginning of this sentence as you listen to the end. But it is also why, if you walk into a room with a purpose, a new and unexpected sensation, a sudden cool draft, a forgotten object on the floor, can be like a soft, gentle wave that washes the shells from your hands, and you are left wondering what you came for. It is a gentle reminder to do one thing at a time. And then there is the great deep. This is long-term memory. When an experience is meaningful enough, when it is touched with emotion or visited with gentle repetition, it is not left in the shallows. It begins a slow, graceful descent into the vast, mysterious, and silent depths of your inner ocean. Here, in this luminous archive, memories are kept safe. Here, they become part of the very water of your being. The process of this descent is called consolidation, and one of the master guides of this journey is a beautiful seahorse-shaped structure deep in your brain called the hippocampus. Think of the hippocampus as a master pearl maker. It takes the different threads of a single experience, the sight, the sound, the feeling, the scent, and with a gentle, loving magic, it weaves them all together into a single luminous pearl. And then, when you sleep, the quiet, dark, healing tide of your slumber carries this new pearl down into the great deep of your long-term memory to find its perfect resting place. This is why sleep is so essential for memory. It is the sacred, nightly ritual of carrying the treasures of the day down into the timeless safety of the archive. And when you wish to recall a memory, you are not pulling a dusty file from a shelf. You are calling to the deep. You are inviting that specific pearl to release its light once more. You are inviting the constellation of neurons that holds the memory to sing its song again. But because this is a living sea, the song is never quite the same. Each time you remember something, the memory is gently reshaped, colored by your present mood, by new wisdom, by the simple passing of time. Your memories are not static photographs. They are living stories, and you are always gently retelling them to yourself. And what of the memories that fade? What of forgetting? This is not a failure. It is one of the most compassionate functions of the mind. Forgetting is the ocean's way of letting the sand settle, of letting the water become clear again. It is a necessary and gentle release. It is the gift of letting go, which clears the space for new treasures to be found, for new peace to be discovered. It is a form of quiet, constant healing. So, as you rest here now, feel the presence of this vast, peaceful ocean of memory within you. It is calm tonight. The waters are still. It holds the sum of all the love you have ever known, all the beauty you have ever seen, all the wisdom you have ever gained. It is the thread that connects you to yourself. And it is here, in this quiet stillness, that the gentle work continues as you drift and float on the calm, deep waters of your own being. Chapter 11. The Weather of the Soul. Emotions are the weather of our inner world. They are the subtle currents and the deep, silent tides that move through the ocean of our being. They are not chaotic or random. They are a form of deep, non-verbal wisdom, a language that the heart and body use to speak to us. They arrive like clouds on the horizon. They stay for a while, and then, if we allow them, they drift on, leaving the sky clear and peaceful once more. The source of this inner weather can be found deep within the brain, in a collection of interconnected structures known as the limbic system. This is not a cold, mechanical center. This is the emotional core of your mind, a warm, ancient, and sensitive place where feelings are born. At the heart of this system is the amygdala. Do not think of it as an alarm bell of fear, but rather as the ancient, watchful guardian of your heart. Its job is to pay attention, to notice what is truly important in your experience. When something significant happens, something beautiful, something surprising, something that touches you deeply, the amygdala highlights it with a kind of luminous ink, whispering to the rest of the brain, "This matters, remember this." It is the keeper of your safety and the curator of your emotional significance. Working in perfect harmony with this guardian is the hippocampus, the master storyteller we have already met. When the amygdala highlights a moment with feeling, the hippocampus gently weaves the story around it. It records the details, the place, the time, the gentle sound of a voice, giving context and meaning to the emotional tide. This is why our most powerful memories are so often intertwined with our deepest feelings. And from this core, there is a bridge that connects the world of feeling to the world of your physical body. This is the hypothalamus. It translates the silent, internal language of an emotion into a physical sensation. It sends the gentlest of signals that can influence your heart's rhythm, the depth of your breath, and the warmth of your skin. This is why you do not just think an emotion, you feel it throughout your entire being. The feeling of deep peace can be felt as a slowing of your heart, a deepening of your breath. The feeling of joy can feel like a lightness in your chest, a warmth spreading through you. These are not just metaphors, they are the physical expression of your inner weather, orchestrated in perfect, quiet harmony. This physical expression is guided by the two great branches of your autonomic nervous system. The sympathetic nervous system is the rising tide. It is the energy of activation. It is the quickening pulse you feel not just in fear, but also in excitement and delight. And its gentle counterpart, the parasympathetic nervous system, is the receding tide. It is the soft, deep exhale that brings you back to a state of calm, glassy stillness. It is the feeling of your muscles softening, your heart rate slowing, your entire body returning to a state of profound peace. As you rest here now, you are inviting this gentle, receding tide to wash over your entire being. The quality of this weather is also colored by the delicate chemistry of your brain. Special neurotransmitters act as the artists of your emotional palette. Dopamine is the gentle glow of satisfaction, the soft inner warmth of pleasure or a task completed. Serotonin is the feeling of quiet contentment, the deep, unspoken sense that all is well in your world. And oxytocin is the profound warmth of connection, the feeling of being safe, held, and cared for. And watching over all of this with a calm and compassionate gaze is the higher region of your brain, the prefrontal cortex. This is the wise observer. It is the part of you that can look upon the rising tide of a feeling without being swept away by it. It has the gentle power to name a feeling, and in the simple, loving act of naming it, this is sadness, this is joy, it can soothe it. It brings a loving understanding to the weather of the heart, allowing the clouds to drift by without resistance. So as you lie here, floating on the calm, deep waters of your own being, simply allow any feelings that are present to be here. There is no need to push them away or hold on to them. They are simply currents passing through. Let them be like clouds in the vast, open sky of your awareness. And know that beneath any weather, there is always a deep and abiding stillness. Sleep is the time when the emotional seas become calm, when the water becomes clear, and when your entire being can rest in the perfect, peaceful silence of the deep. Chapter 12. The gentle, nightly miracle of sleep. And so you lie here, at the edge of the waking world. The day, with all its thoughts, feelings, and sensations, is now a distant shoreline, growing softer and dimmer with every gentle breath. Ahead of you lies a vast, peaceful, and welcoming darkness. This is the world of sleep. Do not think of it as falling or as a loss of control. Think of it as a gentle surrender, a homecoming. It is the nightly pilgrimage your body and mind take to a place of profound healing, restoration, and quiet magic. It is a loving act of letting go. It is a common misunderstanding that when you sleep, your brain simply turns off, but that could not be further from the truth. Your brain does not shut down. It simply begins a different, more ancient, and perhaps even more important kind of work. Imagine your mind is a grand and beautiful house. Sleep is the time when the busy daytime residents have all gone to bed, and now in the deep quiet of the night, a silent, diligent, and loving crew emerges. This is the night crew of your brain, and they have come to clean, to repair, to sort, and to dream. Your journey into sleep is not a sudden drop, but a slow, graceful descent, as if you are walking down a soft spiral staircase, deeper and deeper into a place of perfect peace. The first few steps on this staircase are stage 1 sleep. This is the threshold, the beautiful, hazy space between worlds. Here, you are simply drifting. You are floating on the calm surface of the water. The sounds of the world outside become distant and unimportant, like echoes from a life you have momentarily left behind. Your thoughts lose their sharp edges, becoming fluid, dreamlike, and gentle. As you take a few more steps downward, you enter stage 2. You are sinking a little deeper now. Your heart rate begins to slow, becoming a soft, steady, peaceful drumbeat. Your body temperature gently drops, as if you are wrapping yourself in a cool, quiet blanket of peace. Here, the night crew is just beginning its work, sending brief, shimmering bursts of electrical activity through the quiet hallways of your mind, checking the circuits and preparing the house for the deep work to come. And now you descend further still into the deepest, most silent, and most healing chamber of the house, This is stage 3, or deep sleep. You have reached the bottom of the staircase and have entered a silent cathedral. The electrical rhythms of your brain become slow, powerful, and rolling like a deep, silent ocean swell. Down here, in this profound quiet, the most sacred physical healing takes place. The night crew is now focused on restoring your body. Growth hormone is gently released, tissues are mended, your immune system is strengthened and replenished. Your physical body is being lovingly repaired in the perfect, undisturbed stillness of the deep. After spending some time in this deep healing silence, you begin to ascend the staircase again, but not to wakefulness. You ascend into the most magical room in the house. This is REM sleep, the theater of dreams. Here, your brain becomes beautifully active again, its electrical rhythms looking almost as if you were awake, and yet your body remains in a state of perfect, safe stillness. This is a loving gift from your nervous system. It sends a gentle message of paralysis to your voluntary muscles, a protective, loving embrace that keeps you safe and sound, so that your mind is free to have the most incredible adventures. And in this safe stillness, your brain begins to dream. It takes the feelings, the images, the memories, and the hopes of your day, and it weaves them into stories. It paints impossible, beautiful landscapes. It composes strange and wonderful music. It is processing your emotional world, sorting through the archives of your heart, and speaking to you in a language of symbol and metaphor. Throughout the night, you will cycle through these stages, descending into the deep, silent cathedral for physical healing and ascending to the magical theater for emotional and mental sorting again and again. The librarian of your mind is at work, strengthening the important memories of the day and gently sweeping away what is no longer needed. The emotional seas are being calmed, washing away the residue of stress and worry. And a gentle, cleansing tide is flowing through the very pathways of your brain, washing away the metabolic dust of your waking hours, leaving your mind clean, clear, and refreshed for the morning. And so, as you lie here now, you can feel yourself on this journey. You are on that gentle spiral staircase, and you can give yourself permission to descend. There is nothing else to do. There is nowhere else to be. The loving, diligent night crew is here, ready to take care of everything. All that is required of you is to trust, to let go, and to allow yourself to drift into the sacred, healing darkness. Chapter 13. The Body's Gentle, Automatic Pilot. Even now, as you float in this deep state of peace, your life's most essential functions continue with a perfect, effortless grace. Your heart beats a soft, steady rhythm. Your lungs draw in and release the air in a gentle, tidal flow. Your body maintains its perfect temperature. You do not have to think about any of this. You do not have to command your heart to beat or remind your lungs to breathe. It is all being done for you by a deep and ancient wisdom within. This is the work of your autonomic nervous system. The word autonomic means self-governing, and that is precisely what this system is. It is the wise and gentle pilot of your inner world, the silent orchestra conductor who ensures that all the background music of your life is played in perfect harmony. Your conscious mind, the part of you that thinks and dreams, has lovingly delegated these vital tasks to this deeper intelligence, freeing you up to experience the world and now to rest completely. This silent guardian has two main branches. They are not opposites, but partners in a beautiful, constant dance. They are like the in-breath and the out-breath, two parts of a single, perfect rhythm that maintains the balance of your life. The first partner in this dance is the sympathetic nervous system. Think of this as the energy of the sun. It is the spark of activation, the rising tide that readies you for engagement with the world. It is the system that quickens your heart not only in moments of stress, but also in moments of joy and excitement. It is the feeling of aliveness, of readiness. In our busy modern world, this sun energy sometimes shines a little too brightly for a little too long, and we can feel tired from its constant light. But the second partner is the parasympathetic nervous system, and this is the energy of the moon. This is the energy you are embracing now, in this moment of deep rest. It is the gentle, cooling rain that soothes the sun-drenched earth. It is the deep, restorative sigh of release. Its purpose is to help you rest and restore. As you sink deeper into relaxation, this lunar energy becomes dominant. It sends a soft, calming whisper to your heart, inviting it to slow down. It speaks to your lungs, encouraging your breath to become deeper, slower, and more peaceful. It gently nudges your digestive system, reminding it that now, in this time of safety and peace, it can do its slow, nourishing work. It is a gentle, downward spiral into the most profound state of calm. One of the most beautiful pathways of this calming system is the vagus nerve. Imagine it as a great, wandering river of peace that flows from the base of your brain down into your body, touching your throat, your heart, your lungs, and your belly with its serene current. And you are connected to this river through your breath. Every slow, deep, gentle exhale is a message you are sending along this river of calm. With each outbreath, you are sending a signal to your entire being, a whisper that says, "I am safe. All is well. I can let go even more." The ideal state of your being is a fluid, graceful dance between these two energies, the sun and the moon. And sleep is the sacred time when the moon energy is allowed to take the lead. It is a time for the sun energy to rest and recharge. It is a nightly rebalancing, a return to the quiet, gentle center of your being. So as you rest here now, know that your silent guardian is on watch. You can release all effort. You can let go of all control. Your heart is being beaten for you. Your lungs are being breathed for you. Every quiet, essential rhythm of your life is being tended to with a perfect, loving, and effortless wisdom. You are completely cared for. And in this perfect safety, you are free to surrender completely to the deep, healing peace of sleep. Chapter 14. The Quiet Miracle of Myelin. Imagine again the long, shimmering thread of a single axon, stretching out to carry its luminous whisper from one part of your inner world to another. For this message to arrive with perfect clarity and grace, especially across the vast distances of the body, it needs to be protected. It needs to be insulated. It needs to be nurtured on its journey. The nervous system, in its infinite wisdom, has created the most beautiful solution. It is not a crude coating or a simple layer of insulation. It is a living, luminous sheath, a soft blanket of pearlescent light that is lovingly wrapped around the axon. This is myelin. This beautiful sheath is woven by the silent artisans of your nervous system, the glial cells. In the great central galaxy of your brain and spinal cord, these weavers are the oligodendrocytes. In the peripheral pathways that stretch out into your body, they are the Schwann cells. Think of them as loving caretakers. They see a long, bare axon, and with an innate, artistic wisdom, they begin to wrap it, layer upon luminous, fatty layer, creating a thick, soft, and protective covering. It is an act of devotion, repeated millions of times throughout your body, ensuring that every important message is kept safe and pure on its journey. But this luminous sheath is not wrapped like a single continuous blanket. The artisans leave tiny, sacred gaps. Imagine the axon as a dark thread, and the myelin as a series of long, iridescent pearls strung along it. The dark, quiet spaces between the pearls are just as important as the pearls themselves. These are the nodes of Ranvier. And here is where the true magic happens. We have spoken of the action potential as a wave of light, a luminous whisper. In an unmyelinated axon, this wave must flow along the entire length of the thread, a continuous and steady ripple. But in an axon blessed with the gift of myelin, the whisper does not need to flow. It can leap. The wave of starlight is born at one node, in one of those dark, quiet spaces between the pearls. And then, instead of traveling through the insulated segment, it vanishes, and in the same instant, reappears at the very next node. It is a flicker of light, disappearing and reappearing, leaping from one sacred gap to the next. Imagine a dancer moving across a still, dark river at night by leaping from one smooth, polished moonlit stone to the next. The dancer does not touch the water in between. She simply appears on one stone, and then the next, and then the next, crossing the wide river in a few breathtakingly graceful bounds. This is how your neural messages travel. This is saltatory conduction. It is a silent, beautiful, and impossibly fast dance of light. This is the biological secret to effortlessness. This silent, leaping speed is why a simple thought can become an action in an instant. It is why your protective reflexes are so swift. It is why your movements can feel so fluid and coordinated. It is the quiet work of myelin that allows for the grace and precision of your entire being. And this beautiful process is one that develops patiently over time. When a baby is born, many of its neural pathways are not yet fully wrapped in their luminous sheaths. This is why a baby's movements can seem uncoordinated at first. But slowly, patiently, over the course of childhood and adolescence, the silent artisans do their work. They spin and weave their myelin, and as they do, movements become smoother, thoughts become clearer, and the entire nervous system becomes a more efficient and harmonious orchestra. And even now, this luminous sheath is being tended to within you. It is the insulation for your inner peace, ensuring that the gentle, restorative signals of your nervous system travel purely and without interference, especially now, in this deep state of rest. It allows the quiet lullabies of your parasympathetic system to reach every part of you, inviting you to let go, to soften, and to drift even deeper into the silent dark. Chapter 15: The Silent, Loving Support of the Glia. In the great, starlit theater of your mind, the neurons are the famous actors. They are the singers of the electrical songs, the ones who generate the thoughts, the memories, and the dreams. And because they are so brilliant, we often give them all of our attention. But for every singer on the stage, there must be a vast and silent crew working in the shadows, ensuring the lights are perfect, the stage is clean, and the performer is safe and cared for. In your nervous system, this silent, loving support crew is the glia cells. The name glia comes from a word meaning glue, and for a long time it was thought that was their only job, to simply hold the brilliant neurons in place. But they are so much more than glue. They are the living, intelligent mortar that holds the sacred temple of your mind together. They are the unsung guardians, the silent, humble majority. And without their tireless, devoted work, the neurons could not sing their beautiful songs. Let us meet these quiet caretakers. First, there are the astrocytes, named for their beautiful, star-like shape. These are the master nurturers of your brain. With their many gentle, reaching arms, they tenderly connect to the tiny blood vessels that flow through your brain, drawing out the purest nourishment, the oxygen and glucose, and offering it directly to the neurons they care for, like a mother bird feeding its young. These starlit cells are also the keepers of the chemical peace. After the neurons have whispered their chemical poems across the synapse, the astrocytes gently move in and mop up any excess neurotransmitters, keeping the synaptic rivers clean and clear for the next conversation. They ensure the environment is always perfectly balanced and serene. Then there are the microglia. These are the tiniest of the guardians, but they possess the fiercest love. Think of them not as soldiers, but as the diligent, microscopic gardeners of your inner world. They wander the quiet pathways of your brain, constantly tidying up. They gently prune away old, unused synaptic connections, like a gardener trimming a vine to make it stronger. They clear away any cellular debris, sweeping up the fallen leaves of a busy day, ensuring the garden is always fresh, healthy, and has open, fertile space for new growth to occur. We have already met the master artisans, the oligodendrocytes, and the Schwann cells. They too are part of this loving family of glia. They are the weavers of light, the patient craftspeople who spin the luminous, pearlescent sheaths of myelin, allowing for the grace, speed, and clarity of your every thought and feeling. And finally, there are the ependymal cells. These are the keepers of the sacred inner river. They line the quiet, fluid-filled chambers deep within your brain, and with the gentle waving of their tiny cilia, they help to produce and circulate the cerebral spinal fluid. This is the clear, pure, life-giving water that bathes, cushions, and cleanses your entire brain and spinal cord. These guardians ensure this sacred river is always flowing, always pure. And so, you are not just a collection of brilliant singing neurons. You are also held, supported, nourished, and cleaned by this vast, silent, and loving community of guardians. They are constantly at work, asking for nothing in return, their only purpose to ensure that the singers on the stage can perform their miracles in an environment of perfect peace, safety, and support. As you lie here now, feel this deep internal support. Feel the presence of these trillions of unsung guardians, all working in perfect, silent harmony for you. You are being profoundly cared for from within, and in this perfect, supportive stillness, you can let go. You can release all effort. You can allow yourself to be held, to be tended to, as you drift ever more deeply into the healing dark. Chapter 16. The Unbroken Striving for Balance. Your nervous system is like a vast and perfectly tuned musical instrument, capable of playing the most beautiful and intricate symphonies of life. For most of our lives, this instrument plays its music in flawless harmony. But sometimes, in the journey of life, a string may fall out of tune, or a section of the orchestra might lose its rhythm for a time. This is not a story of brokenness. This is a story of resilience. It is the story of the music itself and its profound, innate desire to find its harmony once more. This final part of our journey is about hope and about the quiet, unbreakable strength of the life force that flows through you. Sometimes the challenge comes as a change in the delicate chemical weather of the mind. A river of a particular chemical messenger may begin to flow less abundantly. When the gentle current of a neurotransmitter like dopamine begins to soften, the body's ability to perform its effortless dance can be challenged. But even here, there is a deep striving for balance. The brain, with its incredible plasticity, begins to learn new ways to dance with a quieter rhythm. And modern medicine can often offer a gentle hand, helping to replenish the flow of that missing chemical river, restoring grace to the body's poetry of motion. Sometimes the challenge comes as a disruption in the quiet electrical harmony. For a moment, a sudden, brief thunderstorm of electricity can roll through the neurosky. And for that moment, the quiet, steady rhythm is lost. But like any storm, it passes, and the deep, innate drive of the system is to return to the calm, clear sky that follows. And here, too, gentle care can help to soothe the weather of the mind, creating a climate where the thunderstorms are less likely to form. And sometimes a pathway of light can be blocked, or a bridge can be broken. In these moments, the brain's response is one of the most beautiful expressions of life's creativity. The great, wise river of neural information does not simply stop. It begins the slow, patient, and miraculous work of carving a new channel. Through the gentle gift of neuroplasticity, neighboring areas of the brain, like loving communities, can begin to learn new songs, taking on the responsibilities of the regions that have been challenged. The process of rehabilitation is simply the loving and patient act of teaching the brain these new melodies, of helping it to discover its own profound capacity to find another way. In every challenge, the story is the same. The nervous system is always, in every moment, striving for balance. It is always seeking a return to wholeness. This is the deep biological imperative for healing that is woven into the very fabric of your being. So as you rest here, feel this deep, resilient wisdom within you. Know that your own nervous system, right now, in this very moment, is a perfect expression of this healing intelligence. As you sleep, you are participating in this profound restorative process. You are offering your entire being the sacred gift of time and peace to rebalance, to restore, and heal. Trust in this innate wisdom. It is the quiet, unbreakable strength that holds you. It is the deep, resilient peace that is your truest nature. A final reflection, the universe within. And so, our long and peaceful journey through your inner world comes to a gentle close. We have wandered through the starlit forests of your mind, met the silent, thoughtful neurons, and witnessed the luminous whispers that carry the messages of your life. We have floated on the living sea of memory and felt the gentle tides of the heart. We have visited the sacred, healing darkness of sleep and met the silent guardians who watch over you, always. All of this entire, magnificent, and impossibly complex universe is you. It is humming with a quiet, peaceful, and intelligent light right now as you lie here. It does not need you to manage it. It does not need you to understand it. It only asks that you trust it. It is the source of your strength, your creativity, and your profound capacity for peace. It is the quiet, unbreakable center of your being. Thank you for taking this journey with me tonight. If this exploration has helped you find a moment of peace and you feel so inclined, a simple like is a quiet way of helping other curious minds find their way to this place of rest. And you are always welcome to subscribe for more sleepy science in the future. But for now, all of that is the world of doing, and you are now in the world of being. There is nothing left to do, nothing left to figure out. There is only the gentle, rhythmic tide of your own breath carrying you out into the calm, deep, and silent ocean of sleep. Sleep well, and may the quiet, loving universe within you grant you the most peaceful and restorative of nights. See you in next video. Good night. Welcome, sleepy thinkers, curious night owls, and anyone who finds themselves drifting gently toward the shores of dreamland. You have arrived at the Midnight Scientists, a quiet harbor where the stars feel close, the questions are vast, and the pace is slow enough to honor your rest. Tonight, we will tiptoe together into one of the most mysterious questions ever whispered in the dark. Was there ever a time when nothing existed? But do not worry, we will wander through this idea with the softest voices and a calm, gentle curiosity. This is not a race through equations, but rather a slow, weightless float through a galaxy of thought, perhaps with a warm cup of chamomile tea in hand. Now, I do hope this journey isn't too interesting. That would be a terribly inconvenient thing at bedtime, but if it happens to keep your mind gently glowing for a while, then at least you will be dreaming of something fascinating as you drift away. Before our cosmic wandering truly begins, a gentle invitation. If these journeys through science help you find rest, a simple tap on the like button or subscribing helps other curious souls find their way to this quiet corner of the cosmos. I also find a quiet comfort in reading where you're listening from and what time it is in your world. A sleepy hello from across the planet is always a welcome sight. And finally, a gentle reminder. While we explore these deep and dreamy questions, think of this not as medical advice, but as a soft place for your mind to land at the very end of your day. Let us begin. Let's take a deep, slow breath. Not to fill your lungs with cosmic insight just yet, but because we are about to drift into a subject that feels simple at first, but soon becomes as elusive as a shadow in a starless room. Tonight's question: what do we truly mean by nothing? You would think that of all the things in the universe, or outside of it,
nothing would be the easiest to describe. After all, it is, well, nothing. No things, no stuff, just a perfect silent emptiness, right? But here is where the mystery deepens. The more carefully we gaze into nothing, the more it begins to look suspiciously like something. And as we will see in both science and philosophy, nothing wears many disguises. There are, in fact, several kinds of nothing, each one stranger and more beautifully counterintuitive than the last. Let's start with something familiar. Picture a simple, empty jar sitting on your kitchen counter, bathed in moonlight. You twist off the lid and peer inside. It appears empty. There's no honey, no sugar, not even a single forgotten grain of rice. Most of us would call that nothing. But of course, our senses are telling a small fib. The jar is humming with air, with nitrogen, oxygen, and perhaps the lingering, ghostly scent of cinnamon from whatever it held last week. Molecules are bouncing within its glass walls like a universe of invisible motes, all dancing in the dark. To a creature small enough to see them, the jar would be overwhelmingly full of something. So let us deepen the quiet. Imagine we draw all of the air out of the jar, creating a vacuum until not a single molecule of atmosphere is left inside. Now we have what we might call empty space. Is that nothing? We're getting closer, but even this perfect vacuum is not truly empty. First, there are still fields breathing within it. Not fields of grass, but the invisible architecture of the universe, woven into the fabric of everything. These are quantum fields, and according to our deepest understanding of physics, they can never be completely switched off. Even in their lowest possible energy state, their ground state, they still ripple with possibility. And this is where the world begins to feel like a dream. In the early 20th century, physicists discovered that the tiniest levels of nature are never truly still. Even a perfect vacuum, stripped of all matter and energy, is still humming with a deep cosmic uncertainty. Tiny particles flicker in and out of existence, constantly, like brief thoughts in the mind of the universe. They are called virtual particles, born from what physicists call quantum fluctuations. In other words, even the emptiest nothing is always quietly doing something. If we could shrink ourselves down to that quantum scale inside our sealed jar, we would witness a silent, fizzing reality, not because matter is leaking in, but because the fabric of space-time itself is restless. The vacuum is like a deep, still ocean that appears calm from above, but teems with hidden life in its depths. So let's journey even deeper. What if we could remove not just the contents of space, but space itself? Imagine it gone. No dimensions, no up or down, no here or there. Can our minds even hold such a thought? This is where our language, born of a world of places and things, begins to dissolve. It is not a black void or a white screen. It is not darkness or silence. It is the absence of place itself. There is no inside for your mind to enter. And now, for the most radical step of all, what if we took away time? No seconds ticking by, no change, no flowing river of moments, a timeless, spaceless, matterless what? Some thinkers propose that this is the only true form of nothing, the absolute absence of everything, including the very stage upon which things can exist or happen. But now we are holding a paradox in our hands. If there is no space or time, can we even say it exists? Trying to imagine this is like trying to draw a square circle. The words are familiar, but together they point to something beyond our intuition. Our brains, which evolved to navigate landscapes and anticipate seasons, are not built to visualize the absence of all things. Perhaps the most extreme form of nothing is beyond not just our senses, but beyond thought itself. The philosopher Heidegger once famously asked, Why is there something rather than nothing? It's one of those questions that seems simple at first, but it grows more profound and more unsettling the longer you let it rest in your mind. And the more we learn from science, the more it seems that true nothing might be impossible to find. Even asking what came before the Big Bang might be a gentle error in thinking. If time itself began with the universe, then before is like asking what is north of the North Pole. The question sounds logical, but it collapses into a soft paradox. So we are left with a spectrum of nothings, all of which are actually quite something. From air-filled jars to the seething quantum vacuum to a theoretical void beyond space and time, nothing is not a single, neat idea, but a ladder of increasingly abstract possibilities. And in the end, we might have to accept that pure, total nothingness may be a resident only of our imagination, not of reality. But asking the question is never pointless, for in wondering about nothing, we come to understand what something truly means. It is in the contrast that a peaceful clarity emerges. And as we will soon explore, nothing may not be the end of the story, but the very beginning of a strange and beautiful road. We are going to take a calm stroll through the history of, well, of everything. But don't you worry, you will not need a time machine or a seatbelt. All you need is a quiet mind, a comfortable pillow, and a sense of gentle cosmic wonder. Tonight, we are visiting the moment the universe began, or at least the moment our current understanding says it did. This is the story of the Big Bang, not a loud explosion in space, despite its dramatic name, but a soft, steady unfurling of space itself. A moment so strange it gave birth not only to everything we see, but to the very space and time in which we see it. This idea that the universe is expanding was one of the great revelations of the 20th century. For ages, we assumed the cosmos was static, fixed, and eternal. But in the 1920s, a Belgian physicist named Georges Lemaitre had a curious thought. What if the universe was expanding outward from a single dense point in the distant past? Around the same time, the astronomer Edwin Hubble was peering through his telescope and noticed equally curious. The light from distant galaxies was redder than expected, not because they were blushing, but because they were moving away from us. This phenomenon, known as redshift, was a cosmic clue. It meant that space was stretching, carrying everything along with it, like raisins in a slowly rising loaf of bread. And if everything is moving apart now, it must have once been much, much closer together. Imagine playing the film of the universe in reverse. Galaxies rush toward each other, stars dissolve back into gas, matter folds inward, all collapsing into a tighter and tighter state until about 13.8 billion years ago, you reach a moment of almost unimaginable density and heat, a kind of cosmic seed, a singularity as it is sometimes called. Not a thing in space, but the point from which space itself began to bloom. This is what we call the Big Bang. It wasn't an explosion in space. There was no pre-existing void, no cosmic firework lighting up a black sky. Instead, it was the sudden, graceful expansion of space itself, the birth of time, energy, and the laws of physics as we know them. It's a bit like dots drawn on the surface of a balloon. As the balloon inflates, each dot moves away from every other, not because they are traveling across the surface, but because the surface itself is expanding. That is our universe, a balloon of space-time, slowly and silently inflating for billions of years. In the tiniest fractions of a second after this expansion began, the universe was a hot, dense, glowing soup of particles and energy. Temperatures were so high that atoms could not yet form. Protons and neutrons had not yet found each other. It was a shimmering sea of fundamental ingredients. But as the universe expanded, it also cooled. This cooling allowed energy to condense into the first particles. After a few minutes, these particles joined to form the first simple atomic nuclei, mostly hydrogen and a little bit of helium, the building blocks of stars. A few 100,000 years later, the universe had cooled enough for electrons to settle into orbits around these nuclei, forming the first stable atoms. And in that moment, something beautiful happened. Light, which had been trapped in the hot plasma like sunlight in a dense fog, could finally travel freely. This moment, when the universe became transparent, left behind a whisper, a soft, ancient glow that is still visible across the entire cosmos today. It is called the Cosmic Microwave Background, or CMB. It is one of the strongest pieces of evidence we have for this story of our origins. The CMB fills the universe with a faint, nearly uniform microwave signal. It is like a baby picture of the cosmos, frozen in time. Tiny, subtle fluctuations in this ancient light are the seeds from which all galaxies, stars, and planets would eventually grow. But even with all this evidence, the Big Bang model raises some tantalizing questions. For instance, what caused it? What force triggered that initial graceful expansion? And of course, the great mystery: what came before the Big Bang? This is the question that brings us full circle. Because if the Big Bang was the beginning of space and time, then the word before might not even exist in that context. There may have been no before to speak of, only an origin point from which everything else flowed. Still, some models propose that the Big Bang was not the beginning, but a transition, a bounce from a previous universe, or the birth of one universe among a countless many. We will explore those gentle possibilities in the chapters ahead. But for now, let us rest with this quiet, powerful unfolding of everything. A beginning not in fire, but in form. Not in a bang, but in a breath. The first slow breath of space itself. To gaze up at a sky full of stars is to feel a quiet question stirring in your heart. Where did all of this begin? You are not alone in that feeling. It is a question we have always asked in every age, long before we had telescopes to magnify the light or even names for the constellations. It is a deeply human instinct, this need to seek origins, to gently trace the thread of time back as far as it will go. And when we follow that thread all the way to its very beginning, we arrive at a place of profound mystery, a place where time itself may have had a first moment, a birthday. Let that idea settle around you like a soft blanket. The beginning of time itself, not just the beginning of our world or of stars or of atoms, but of the very flow of moments we call time. It's a bit like discovering that your watch did not just start ticking at some point, but that the concept of ticking itself did not exist before that moment. In our modern understanding of the cosmos, space and time are not two separate things. They are woven together into a single dynamic fabric called space-time. You can imagine it as a vast, invisible tapestry, and everything in the universe, from the smallest mote of dust to the largest galaxy, rests upon it. According to Einstein's theories, this fabric can stretch, bend, and ripple in response to mass and energy. That gentle warping is what we experience as gravity. But here is the most curious part of the story. That same fabric appears to have a beginning, and that beginning, as far as our science can see, is the Big Bang. This means that space did not expand into some pre-existing emptiness. Rather, space itself was born in that moment. And because time is woven into the same fabric, it too came into being. There was no ticking clock before the bang, no empty cosmic hallway waiting to be filled. There was no before because there was no time in which a before could exist. This idea softly defies our everyday intuition. In our lives, everything has a before. Before this breath, there was the last one. Before we fall asleep, we are awake. We are creatures deeply conditioned to think in a straight line of cause and effect. So when we're told that time had a beginning, it's natural to ask, yes, but what was before that? This is where we arrive at that gentle, curious paradox. To ask what happened before time began is like standing at the North Pole and asking, which way is north? The North Pole is not simply a place on a map, it's a boundary of direction itself. From that point, every step you take, no matter which way you turn, is a step south. The very concept of north has peacefully dissolved. In the same way, time may reach a boundary at the Big Bang, not because something is hiding behind a wall, but because the very concept of before loses its meaning there. Many physicists describe the Big Bang not as a moment in time, but as the moment of time, the instant that the flow of time became a meaningful concept. Before that, if we can even use such a word, there may have been a timeless, spaceless state, beyond the reach of our physics and our imagination. Some physicists imagine that the cause of the Big Bang was not an event in time, but a kind of eternal starting condition, a set of rules that simply are, like a game that begins with the pieces already in their starting places, the rules themselves being the true beginning. And here is another gentle twist. Not all physicists agree that time had such a sharp beginning. Some models dream of a universe that is more like a cycle or a bounce, contracting and expanding forever, with no true beginning or end. We will drift into those ideas later on. But for now, let us stay with this strange and simple notion that time emerged from the Big Bang, just like light and matter. That before the universe, there was not a clock ticking in a dark and empty room. It's a difficult thought to hold, because our minds evolved to keep track of sunrises and seasons, not the curvature of space-time. But in a way, it's a deeply liberating idea. If time had a birthday, then every second that has ever existed, including this very one right now as you listen, is part of a grand and graceful unfolding, a story that began 13.8 billion years ago and is still being written, star by star, breath by breath.
The soft rustle of your bed sheets, the gentle rhythm of your heart, all of it is part of time's fabric. A fabric that, according to our deepest understanding, did not always exist. So the next time someone asks you what happened before the Big Bang, you can smile sleepily and say, that is like asking what is north of the North Pole. And then you can drift into the kind of dream only the universe itself could imagine. Because time, like a great and silent river, had a source. And that source seems to have emerged not within time, but alongside it. The Big Bang. The name itself is a curious thing, isn't it? It feels so loud, so sudden, so explosive. It conjures images of a cosmic firework, a great detonation in the dark. But the truth of our universe's beginning may be far quieter, far gentler, and in its own way, far more profound. Understanding why can help us see the idea of nothing before in a soft, new light.
It is a quiet cosmic irony that the name was first spoken not in reverence, but in skepticism. An astronomer named Fred Hoyle, who favored a different theory of a timeless, unchanging universe, used the phrase on a radio broadcast. He meant it as a dismissal of an idea he found too simple. And yet the name stuck, and the theory, supported by waves of evidence, did too. But let us be clear, despite the powerful name, there was no bang in the way we usually imagine one. An explosion in our world happens in space. A firework sends sparks outward through the air. These events happen at a specific location, sending debris flying into a larger, pre-existing background. The Big Bang was not like that at all. The Big Bang was not an explosion in space. It was the expansion of space. That difference may sound subtle, but it is everything. Imagine taking a balloon and drawing little dots all over its surface. These dots are like galaxies. As you slowly inflate the balloon, you will notice the dots all move away from each other, not because they are crawling across the rubber, but because the rubber surface itself is stretching. That is what our universe is doing. Galaxies are not flying apart through some vast emptiness. The space between the galaxies is growing because the very fabric of the cosmos is stretching. And here is the key part. The balloon has no center on its surface. Every point is moving away from every other point. If you were a tiny being standing on any one of those dots, it would look as though you were at the very center of the expansion with everything else rushing away. But this is an illusion. Every other dot feels the same way. Our universe has no center and no edge, just a boundless, stretching space-time. Now, let us gently rewind this image. If we let the air out of the balloon, the dots get closer together. The surface contracts until it reaches a state of extreme density, a tiny, hot, uniform point. That is our starting point. But remember, in this gentle analogy, the balloon's surface is space itself. So when we rewind to that beginning, we are not zooming in on an object in space. We are watching the very fabric of space and time itself become smaller, denser, and hotter until it reaches a state where our current physics falls silent. In other words, the Big Bang was not something that happened inside the universe. It's the moment the universe, and with it, all of space and all of time, began its long, slow unfolding. And this brings us back to the idea of nothing, because if the Big Bang was not an explosion in pre-existing space, then there was no waiting emptiness for it to happen in. There was no cold, dark stage patiently waiting for a universe to arrive and start the show. There was no container, no backdrop, no space at all. This changes how we think of beginnings. The Big Bang suggests that time and space are part of the very thing that began. Asking what came before it or where it happened may be like asking what lies outside the canvas of a painting that is itself the entire canvas. If time itself is part of the story, then there may not have been a before in the way our minds usually frame it. Not because we are missing a piece of the puzzle, but because the very concept might not apply. This is why physicists tread so carefully when speaking of what preceded the Big Bang. Some propose the question is meaningless, like our North Pole riddle. Others believe it points to a deeper mystery, that our current models are incomplete, and that some new theory might one day give us a glimpse into a before we cannot yet describe. But one thing is certain. Calling it a bang paints the wrong mental picture. There was no sound, no shrapnel, no shock wave echoing through a void. There was no there. What there was the quiet, graceful unfolding of everything from a point of origin we do not yet fully understand. It was mathematically precise, and yet from it came everything. The stars and the sky, the atoms in your fingertips, galaxies, photons, black holes, and us. All of it has its roots in that unfathomable moment when space took its first slow breath. So you might now think of it not as a big bang, but as a big stretch, or a great unfolding, a calm, expansive beginning that left behind not a crater, but a cosmos. And in that stretching silence, we find not just a new way of seeing our universe, but a deeper understanding of what it means for nothing to become everything. Picture the quietest place you can imagine, perhaps a dark, empty room insulated from all sound. No ticking clocks, no rustling wind, not even the faint hum of a distant machine. A pure, perfect silence. Now, let your mind drift outward, far out, until that room becomes a patch of deep space, light years from the nearest star. No dust, no radiation, no planets or particles. You would be forgiven for thinking you have finally arrived at true nothingness. But in the strange and beautiful world of quantum physics, even that perfect stillness is a busy place. Tonight, we are going to take a slow, curious dive into the idea that empty space is not actually empty, that even in the absence of all matter and all light, the vacuum itself is brimming with an invisible, restless energy, a shimmering sea of possibility known as quantum fluctuations. To understand this gently, we need to visit the idea of quantum fields. It might sound intimidating, but the concept is beautifully simple. In the old way of thinking, the world was made of tiny particles, like microscopic billiard balls. But quantum field theory tells us that reality is far more elegant. It suggests that the fundamental reality of our universe is not particles, but fields. Imagine the cosmos as a vast, silent ocean made up of invisible layers of energy that stretch across all of space. There is a field for electrons, a field for photons, a field for every particle that exists. They are everywhere, all the time, like a deep and silent presence. Now here is the magical part. When one of these fields vibrates in just the right way, it produces what we perceive as a particle. An electron is just a tiny, momentary ripple in the electron field. A photon of light is a ripple in the electromagnetic field. It is like a single note plucked on an invisible cosmic guitar string. The vibration is the particle. But here's the key. Even when a field is perfectly calm, at its lowest possible energy state, it is never truly at rest. It hums and wiggles with a faint, spontaneous energy, a consequence of the uncertainty that governs the quantum world. These are quantum fluctuations. Because of the Heisenberg uncertainty principle, energy can be bracely borrowed from the vacuum, as long as it is returned very, very quickly. For the briefest of moments, pairs of virtual particles can flicker into existence from nothing, and then vanish back into nothing, like shy fireflies in the dark. So when we say the vacuum is not empty, we mean that even in its quietest state, space is humming with these temporary, jittery excitations. These fluctuations are incredibly brief and small, but they are real enough to have measurable effects. They can subtly shift the energy levels of electrons and atoms. They can create a tiny, almost imperceptible force between two metal plates placed very close together in a vacuum. And they may even be the source of the seeds from which all galaxies grew. But this is where the idea becomes truly fascinating and deeply relevant to our great question. Could this fluctuating, shimmering vacuum be the true origin of our universe? Some physicists believe it might be. Let's drift into this idea slowly. If space can never be truly empty, and if quantum fluctuations are always bubbling just beneath the surface of reality, then perhaps, just maybe, a fluctuation of the right kind could cause something very, very big to happen, something on the scale of the birth of a universe. One proposal suggests the universe could have tunneled into existence from nothing. not a philosophical nothing, but a kind of quantum nothing. A state with no classical space or time, but which still contains the potential to fluctuate because of quantum uncertainty. In this view, the universe was not caused in the traditional sense. It did not emerge from a command or a collision. Instead, it could have spontaneously appeared, a quantum fluctuation on a cosmic scale, an event made possible by the fundamental rules of quantum mechanics. This is not magic. In the quantum world, spontaneous events are not only possible, they are inevitable. Most are tiny and fleeting, but given the right conditions, a fluctuation could have been large enough to trigger the period of rapid expansion, inflation, that set the stage for the Big Bang as we know it. In this sense, the universe may have emerged from a vacuum state, not an absolute nothing, but a seething, dynamic field of pure potential, the kind of nothing that is actually, secretly, quite something. Of course, one might gently ask, where did the quantum fields themselves come from? This is a fair question. This idea may push the mystery back one level, but it does not erase it. Yet the beauty of this quantum vacuum idea is that it provides a possible bridge between nothing and something. It blurs the line. It hints that what we once thought of as a silent, empty void may be the very stage on which existence performs its quietest, strangest magic. And it feels right, in a way, that the universe would be born not from a loud bang, but from a gentle ripple, a flutter in the stillness, a whisper in the dark. So, as you lie there, letting your thoughts drift like particles in a warm and gentle breeze, remember that even the quietest, emptiest places in the universe are not truly empty at the quantum level. They vibrate, they shimmer, they dream. And if our vast cosmos was born from a brief, improbable flicker in that dream, then perhaps nothingness is not the end of the story, but the very beginning. The vacuum is not empty. It is just full of potential. Let us drift for a moment into the quietest silence imaginable, a silence not merely of sound, but of time itself, a stillness not of motion, but of space. No stars, no atoms, no energy, not even a black void to hold it all. Just the pure, profound absence of everything. And out of that stillness, a universe whispers itself into being. This may sound like the beginning of a beautiful bedtime story, and in a way it is. But in the curious world of theoretical physics, it is a serious and elegant attempt to understand how everything could have emerged from what we once called nothing. This is one of the boldest dreams in modern cosmology. The idea that our universe could have quantum tunneled into existence. It's a model gently imagined by physicists like Alexander Vilenkin, where reality itself flickered into being not from a divine command or a fiery explosion, but from a quiet, quantum possibility. Let us recall the strange logic of the quantum world, where the vacuum is never truly empty. It is always shimmering with tiny borrowings of energy that vanish as quickly as they appear. This idea that nature has a kind of flexibility, a quantum wiggle room, brings us to the phenomenon of quantum tunneling. In the world we see every day, if a soft breeze pushes a fallen leaf against a garden wall, it can go no further. It rests there, its journey ended. But in the quantum world, the rules are softer, more dreamlike. There is a tiny but very real possibility that the leaf could simply appear on the other side, not by breaking through the wall or flying over it, but by passing through it like a ghost, a ripple of possibility. This phenomenon, quantum tunneling, is not just a theory, it is a real process that allows the sun to shine through nuclear fusion in its core. It is how some particles gently decay over time, and it might just be how our universe was born. In the early 1980s, Vilenkin proposed that the universe could have tunneled into existence from a state with no classical space, no time, and no matter. from, in other words, nothing. But this was not the nothing of an empty room. It was the absence of all physical structure, yet still somehow held within the gentle, unwritten rules of quantum physics. In this beautiful model, the universe did not need a cause in the way we usually think of one. There was no clock ticking down to its arrival, no cosmic map to mark the spot. Instead, it was like that leaf appearing on the far side of the garden wall. Not because something pushed it, but because the laws of quantum mechanics granted it a tiny but non-zero chance to simply exist there. This is sometimes called quantum cosmogenesis.
A gentle question may arise in the mind. How can there be laws of physics in a place with no space or time to contain them? It is a delicate and beautiful point to ponder. Some physicists believe that these quantum laws are so fundamental, they do not need a pre-existing universe to be true. They are not like rules written down in a book. They are more like the blueprint of possibility itself. You might think of it like this. Even if there is no chessboard yet, the rules of how a knight can move still exist as a concept. Once the board appears, those rules define the dance of the pieces. In the same way, the pre-universe nothing may have had no board, no space-time, but it may still have been shaped by the quantum rules that determine what can happen. And according to this idea, what can happen is astonishing. An entire universe, complete with its own space, time, energy, and physical laws, can tunnel into being. And we may be living inside that gentle, improbable whisper. In Vilenkin's model, there may be no before in the traditional sense, but there is a mathematical space of possibility. The nothingness is not an empty box. It is more like a seedbed of potential realities, waiting for the right quantum moment to bloom. This idea of the universe as a spontaneous, probabilistic event might feel strange. We are so used to thinking of causes. But in the quantum realm, some events do not need a cause. They are simply allowed to happen by the laws of probability. And what is so lovely about this model is that it doesn't require any exotic ingredients. No mysterious pre-existing space, no divine spark. Just quantum mechanics doing what it always does, allowing unlikely, beautiful things to happen. Of course, this is still a dream woven from mathematics and theory. We have no telescope powerful enough to see before the Big Bang. But these ideas offer a tantalizing glimpse of how the universe might have emerged, not in a loud bang, but in a soft whisper, a whisper of possibility becoming reality. So, could this be the answer? It remains one of our best and gentlest guesses, an idea that the entire cosmos may have started as a tiny chance event, born from a rule book that does not need a referee or even a field on which to play. It is humbling, it is mind-bending, and it is strangely, deeply soothing. From nothing, or almost nothing, came everything. Not with a bang, but with a quiet quantum shrug. Let us take a quiet pause, a deep breath in the darkness, and drift back again, not just to the beginning of the universe, but to a moment just after. A moment so brief and mysterious, it makes the blink of an eye feel like an eternity. We are entering the era of cosmic inflation, a silent, powerful expansion that may have laid the groundwork for the Big Bang. It is a concept that helps answer some deep puzzles about our universe's shape and structure. But it also opens up new, wondrous questions, including what made the universe inflate and what was there before that.
Our journey begins with a curious observation. When we look out into the cosmos with our most sensitive instruments, we see that the universe is remarkably uniform. The ancient light from the early universe, the cosmic microwave background, has almost the exact same temperature in every direction we look. The smoothness is astonishing. But here is the riddle. How could regions of space that are now so far apart, so far that they could never have been in contact, even traveling at the speed of light, somehow have ended up with the exact same temperature? It's like two people on opposite sides of the Earth who have never met or spoken, deciding to hum the exact same note at the exact same time. How did they coordinate? This is called the horizon problem. And there were other puzzles too. The universe also appears to be geometrically flat, meaning parallel lines will stay parallel forever. For this to be true, the conditions of the early universe had to be balanced with almost impossible precision. The slightest deviation would have caused it to collapse back on itself or expand too quickly for galaxies to ever form. These puzzles were clues, soft whispers from the dawn of time, hinting that a crucial part of the story was missing. And in the early 1980s, a physicist named Alan Guth had a radical vision. What if, in the very first moments of its existence, space underwent a brief but exponential expansion, doubling in size again and again, faster than the speed of light, for a tiny fraction of a second? This is the theory of cosmic inflation, and it changed everything. According to this idea, the universe expanded by an almost unimaginable factor, perhaps 100 trillion times in less than a trillionth of a second. But because it was space itself that was expanding, no physical laws were broken. So what does inflation do for us? Well, it solves the horizon puzzle beautifully. Before inflation, the entire observable universe was once a tiny, minuscule patch, so small that it could easily reach a uniform temperature. Inflation then took that tiny, smooth patch and stretched it to cosmic size. The smoothness we see today is just the echo of that original shared beginning. Inflation also flattens space, like stretching a crumpled sheet of fabric until it is perfectly smooth. The more you stretch it, the flatter it appears. Inflation then is like a cosmic prequel. It is the quiet, powerful event that happens just before the hot, dense state we call the Big Bang. You might even think of the Big Bang as the moment when inflation ends, and all the energy stored in that inflating field is released in a warm burst of heat and light. This is called reheating, and it is the point where the universe becomes filled with the particles and radiation that would eventually become stars, galaxies, and everything else. So what could have sparked this incredible period of expansion? The answer is still a gentle mystery, but the leading idea is a hypothetical field called the inflaton field. Imagine this field as a ball resting on a high, flat plateau. While it sits there, its immense energy drives the exponential expansion of space. But eventually, the ball begins to roll down the hill. As it does, inflation ends. The stored energy of the field is converted into the particles and heat of our universe. The cosmos becomes warm, and what we traditionally call the Big Bang gets underway. It's a beautiful idea, but as always, it leads to even deeper questions. What existed before inflation? Was inflation itself eternal, endlessly spawning countless bubble universes in an endless cosmic foam? Some models suggest exactly that, a process called eternal inflation, where the inflating field never truly settles down everywhere. It continues in other regions, creating an infinite multiverse of pocket universes. Each bubble could have its own physical laws, its own history, its own unique possibilities. Our universe just happens to be one where the inflating field slowed down enough to allow stars, planets, and sleepy scientists to emerge. We don't know yet, but we are looking for clues in the sky. Tiny fluctuations in the cosmic microwave background predicted by inflation have already been seen. They're like fossils from the very first moments of cosmic expansion. For now, cosmic inflation remains one of the most elegant and powerful ideas in science, a moment of near infinite speed and profound silence in which the universe did not explode into being, but inflated into its potential. Not a bang, not a flash, but a breath, deep, fast, and utterly transformative, a silent boom that gave us the space to exist. Imagine for a moment that our universe, this entire vast and expanding cosmos, with its billions of galaxies and shimmering stars, is just one tiny bubble in an endless cosmic foam, one quiet pocket of space among a countless many, each with its own laws, its own history, its own unique possibilities. It's a humbling, almost dizzying thought. But according to a theory known as eternal inflation, this may be exactly what reality looks like on the grandest of scales.
Tonight, we are going to float calmly through this vast and mysterious idea, a universe of universes, a multiverse born not from a singular event, but from a quiet, endless process of cosmic bubbling. A process that, if true, would mean that the idea of nothing may never have existed at all. To begin, let us return briefly to that moment of cosmic inflation we just visited. In the more nuanced and, frankly, more intriguing versions, inflation does not stop everywhere at the same time. Because of the gentle randomness of the quantum world, the inflating field is not perfectly smooth. In some regions, its energy drops and inflation ends. That is where a universe like ours, a bubble of space-time, can begin to form. But in other regions, the field's energy might remain high, and so inflation continues. Those regions expand faster and faster, growing exponentially and creating ever more space between the bubbles. This leads to a self-replicating runaway process, eternal inflation. Think of it like a pot of water gently simmering on a stove. As it heats, little bubbles of steam form and rise. But imagine that instead of popping, each bubble becomes its own separate, self-contained world. Now imagine that the simmering never stops. More and more bubbles form endlessly, each one expanding and evolving in its own quiet way. That is the multiverse as imagined by eternal inflation. Each bubble in this cosmic stew represents a universe. Some might be similar to ours. Others could be profoundly different. And here is the truly staggering part. This bubbling is not just vast, it is eternal. Because in the regions where inflation continues, space keeps creating more room for new bubbles to form. These bubble universes are isolated from each other, separated by ever-growing expanses of inflating space. Together, they form an infinite landscape of universes, born not from nothing, but from a process that never stops. If this is true, it may suggest that true, absolute nothing never existed at all. There was never a blank slate, a moment of perfect stillness. Instead, there has always been something happening somewhere, a bubbling, stretching, inflating cosmos branching out forever. In this picture, our universe's beginning was not the beginning, but just one of countless moments where a region of space gently exited inflation and began its own story. The Big Bang, as we know it, was simply our beginning,
Now, this might sound like science fiction, and in some ways it is deeply speculative. We have no direct evidence of other bubble universes. But eternal inflation is not a fantasy. It is a natural mathematical consequence of the very inflation models that fit so well with what we observe in our own universe. It also helps to explain something very strange and wonderful about our cosmos. Why its physical constants seem so perfectly, so finely tuned for life. The strength of gravity, the charge of an electron, if any of them were just slightly different, complex matter could never form. But if there are countless universes, each with slightly different properties, then it is not so surprising that at least one, ours, happens to have just the right ingredients. It is not that we are uniquely lucky. It is that we exist in one of the bubbles where observers can exist to ask the question. This idea is sometimes called the anthropic principle. For now, eternal inflation remains a beautiful, compelling, and deeply speculative idea, but it leaves us with a new way of thinking about everything. Not as a singular event that emerged from a void, but as one chapter in a story that never ends. A story that has been unfolding forever, not in time as we know it, but in the boundless potential of space itself. In this vision, nothing becomes a kind of illusion. There is always something, a field, a fluctuation, a slow, eternal bubbling. It is a quiet, expansive thought that the cosmos may have no true beginning and no end, just an endless generation of possibilities, branching and inflating like foam on a quiet sea. And somewhere in all that infinite froth, there's us. One bubble with just the right balance, one flicker of light in an endless ocean of possibility. Perhaps the question is not, why is there something rather than nothing, but rather, why are we in this something? Why did this particular bubble, with these laws and this calm patch of sky, rise from the quiet sea of the multiverse? It's the kind of thought that doesn't demand an answer, but invites only wonder. And in that wonder, the bubbling continues. Let us begin this next chapter with a quiet image. Imagine the universe not as a straight line that begins and stretches forward, but as a breath, a slow, cyclical rhythm expanding outward and then contracting inward, only to expand once more. Inhale and exhale, over and over again. In this calm and curious rhythm lies the heart of a theory that challenges our assumption that the universe began from nothing. This idea, gently provocative and deeply elegant, is known as the Big Bounce, a model where our universe did not explode out of a singularity, but rebounded from a previous state, a cosmic contraction followed by a new expansion. In the standard Big Bang model, the universe begins from an initial singularity, a point of infinite density, infinite temperature, and zero volume. It's the moment where all our equations of physics break down. Singularities tell us that our understanding has reached its limit. This is where the search for a theory of quantum gravity begins, a theory that can unite the smooth cosmic landscape of Einstein's relativity with the jittery, uncertain world of quantum mechanics. One of the leading candidates in that search is loop quantum gravity. This theory reimagines space and time not as a continuous, smooth sheet, but as a woven, granular fabric. At the smallest possible scales, space itself may be made of tiny, indivisible loops, like an intricate quantum mesh. These loops are the very threads from which the cosmic quilt is sewn. Now, when this idea is applied to the entire universe, something remarkable happens. Instead of the universe shrinking into an infinite singularity as we rewind time, the theory suggests that as things get incredibly dense, quantum effects take over. They generate a kind of powerful quantum pressure that resists any further collapse. It's a bit like a trampoline that stretches, but ultimately pushes back with immense force. The result? Instead of a big bang, we get a big bounce.
In this model, our universe did not begin at a singularity. It began at a bounce point, a moment of minimum size and maximum density, where the fundamental graininess of space-time itself repelled the collapse and caused it to expand again. Before that bounce, there was a contracting universe, a cosmos that had been shrinking, perhaps for eons, before reaching that turning point and beginning to expand again, becoming our universe. It is a beautiful reversal. Instead of time having a hard beginning, it becomes a cycle. The bounce replaces the bang. The singularity becomes a bridge to a time before. This opens the door to the profound possibility that the universe has no beginning at all. In a bouncing model, there may have been many cycles, expansions followed by contractions, each one giving rise to a new phase of cosmic history, each bounce wiping the slate clean, or perhaps leaving behind faint, ghostly traces in the structure of space and time. Scientists are beginning to look for such traces in the cosmic microwave background. Interestingly, some bouncing cosmologies could also explain the smoothness and flatness of our universe without needing a period of inflation. In these models, the long, slow phase of contraction could have naturally smoothed out any irregularities, preparing the universe for a graceful, uniform expansion after the bounce. If the Big Bounce is real, it means that something came before our universe. Not a void, not a timeless potential, but a previous cosmos. It might have been similar to ours, or it might have been completely different. And if the bounce happens repeatedly, it challenges our sense of cosmic uniqueness. We may be just one era in a long, eternal chain of universal epics. No first cause, no singular creation, just an eternal cosmic heartbeat. Loop quantum cosmology is still a young field, but it offers a compelling alternative to the traditional story of our origins, one that removes the dreaded singularity, preserves time before the Big Bang, and hints at a much richer and perhaps endless history than we ever imagined. And it softens the mystery of nothing. In this view, there never was nothing. There was always something, a previous universe, or perhaps an infinite series of them, leading to the one we see today. No need to explain the emergence of everything from an absolute void. Just a continuation, a rebound, a cycle. And there is something oddly comforting in that, isn't there? The idea that our universe is part of a longer story, that time did not start with us, that before our beginning there was an end, and before that end, another beginning. A quiet rhythm, a cosmic breath. Inhale, expand. Exhale, contract. And again and again. Let us now take a gentle step into an even more wondrous and abstract dream, a place where the fabric of reality is not woven from particles and fields, but from the quiet music of tiny vibrating strings, a place where the dimensions we know might be just a fraction of the whole story, and where our entire universe could be a single membrane floating in a much larger, unseen cosmic sea. Welcome to the strange and beautiful world of string theory. Now, do not worry if this sounds like a flight of fancy at first. The idea is bold and mathematically rich, but at its heart, it is a serene and elegant attempt to find one single, unified description of all the forces of nature, to understand the song that the universe sings to itself. In the physics of our everyday world, we think of particles as tiny fundamental points, electrons, quarks, photons. But in the beautiful dream of string theory, these particles are not points at all.
They are unimaginably small, one-dimensional loops of vibrating energy. Each one hums a unique note in a silent cosmic symphony. The way a string vibrates determines the particle it becomes. A gentle hum might be an electron. A more energetic vibration could be a photon of light. In this vision, all of reality, all matter, all light, all forces, is a grand, harmonious orchestra of these tiny vibrating strings. But for this beautiful mathematics to work, the theory requires something extraordinary, extra dimensions of space. Not just the three we move through and the one of time, but perhaps 10 or even more. So, where are these hidden dimensions? The theory suggests they are curled up, compactified, woven into the fabric of space at a scale so small we can never perceive them directly. Imagine looking at a tightly wound thread from across a room. It appears as a simple one-dimensional line. But as you get closer, you see its intricate, coiled three-dimensional shape. In the same way, these extra dimensions may be curled up within every point in space, like secret, hidden passages in the architecture of reality. And this is where the dream deepens, and we arrive at the idea of brain cosmology. In some versions of string theory, there are not only strings, but vast, higher dimensional surfaces called brains, short for membranes. Our entire universe, with all its stars and galaxies, might be one such three-dimensional brain, a vast sheet floating in a higher dimensional space we call the bulk. Imagine a silent, dark ocean with great sheets of silk drifting slowly through it. We are creatures living on the surface of one of those sheets, unaware of the others floating in the deep. And here is the most exciting thought. Sometimes these brains can drift toward each other and collide. In one model, the ekpyotic universe, our Big Bang was not a beginning from a single point, but the energetic yet gentle collision of two such parent brains. As they touched, their immense energy was released, creating the heat and matter of our universe. But unlike the traditional Big Bang model, this beginning doesn't start from an infinitely dense singularity. It starts from a graceful geometric event in a higher dimension. Not a violent crash, but a soft universe-creating touch. And this event doesn't have to happen only once. In some of these models, the collision is cyclical. The brains drift apart after they touch, then are slowly drawn back together again by gravity, leading to another collision, another bang, and another cycle of cosmic history. It is not a singular beginning, but an eternal dance of dimensions. This vision, like the Big Bounce, imagines a universe that has existed forever in some form. But here, the bounce is a collision in a higher dimensional space, one that is invisible to us, but essential to the choreography of creation.
And what about nothing? In this framework, absolute nothing may never have existed. Instead, there may have always been this higher dimensional space, this bulk, with brains moving through it like silent cosmic clouds. Our universe's beginning was not the emergence of everything from a void, but the transformation of potential energy into the reality we know. Of course, all of this remains a beautiful speculation. We do not yet have direct evidence for extra dimensions, strings, or brains. But some researchers are listening for the faintest of clues, perhaps a unique pattern in the cosmic microwave background, or a subtle signature in the gravitational waves that ripple across the cosmos, a whisper from that higher dimensional space. Until then, brain cosmology remains a profound and lovely possibility, that our universe is just one piece of a much larger, grander structure, that reality includes hidden dimensions and invisible spaces. And maybe, just maybe, our Big Bang was not the sound of an explosion, but of two universes brushing past one another, like silk sheets in a dark and quiet room. So as you drift off tonight, let your thoughts wander across these hidden dimensions. Picture the universe not as a singular event, but as part of a graceful, unseen dance.
a choreography of strings and brains and gentle collisions in a space beyond our own. In that vast quiet, the music of creation still plays. Let us imagine now that we are sailing gently across a calm, endless ocean. There is no land in sight, no stars above, just water stretching smoothly in every direction. You might wonder, where does this ocean begin? Where is its edge? But as you keep drifting, you begin to realize there is no edge, no sharp cliff to fall from, just an unbroken, continuous surface curving softly beneath you. Now, replace that ocean with time itself. This is the essence of one of the most beautifully subtle ideas ever proposed about the origin of our universe, the Hawking-Hartle no-boundary proposal. Dreamed up in the 1980s by the physicists James Hartle and the legendary Stephen Hawking, this model offers a radically different way of thinking about beginnings. Not with a bang, not with a bounce, but with a gentle rounding off. No singularity, no edge in time, and no need to ask what came before. In the classical picture of the universe, time begins at a singularity, a point of infinite density where all our known laws of physics break down. It is a mathematical wall. For many physicists, including Hawking, this was deeply unsatisfying because it meant that our theories had lost their predictive power at the most important moment of all. So Hawking and Hartle asked a bold question. What if the singularity never existed? Their answer is rooted in the strange world of quantum cosmology, where the fuzzy rules of quantum mechanics are applied to the universe as a whole. And when they did this, something surprising emerged from the mathematics. At the very earliest moments of the universe, near what we think of as the Big Bang, time may have behaved differently. It may have behaved less like a straight line and more like a dimension of space. Instead of starting from a sharp point, time curved gently into space, forming a smooth, finite geometry with no edge, no corner, and no singularity. This is where our ocean analogy returns. Imagine you are standing at the South Pole of the Earth. Now ask yourself, what is south of the South Pole? The question is meaningless, not because there is a wall there, but because the very concept of south ceases to exist at that point. The surface of the Earth curves smoothly. There is no edge, no boundary. Hawking and Hartle suggested that the beginning of time might be like that. Not a singularity where everything suddenly starts, but a kind of South Pole of time, a place where the direction of before loses its usual meaning and blends seamlessly into the fabric of space. In this model, the universe is finite but unbounded, just like the surface of a sphere. It has a size, but no edge. It has a history, but no hard starting point. In this picture, there is no before the universe because time itself does not extend past that smooth, curved origin. The question, what came before the Big Bang, becomes as meaningless as asking, what is south of the South Pole? The universe did not pop out of nothing. Instead, its origin is a region in the geometry of space-time where our usual ideas of before and after gently dissolve. In the no-boundary proposal, the universe is self-contained. It simply is, with no sharp beginning that needs to be explained away. Its laws, its structure, and its history all emerge together, rising gently like the curved surface of a globe from its southernmost point. It is a beautiful proposal, though still unconfirmed. But even if it does not turn out to be the final story, it has changed the way we think about beginnings. It reminds us that edges are often illusions, and what seems like a hard boundary might, on closer inspection, be a soft, gentle curve. And there is something quietly comforting in that. The idea that the universe did not begin with a violent jolt or an infinite wall, but with a graceful rounding off, a smooth start, a natural, peaceful unfolding. It invites us to think of existence not as an event that had to be caused, but as a whole, timeless at its core, yet filled with all of time.
So, as you lie back tonight, picture the early universe not as a flash in a void, but as a softly curving landscape. No cliffs, no before, just the elegant bend of time giving way to space. And in that graceful geometry, the cosmos quietly begins. Let us take a gentle detour now, a quiet meander away from the elegant equations of physics and into the soft, flickering candlelight of philosophy. For while science asks how the universe may have begun, it is philosophy that whispers the deeper question. Why is there anything at all? What does it truly mean to speak of nothing? The idea of nothing has haunted human thought for millennia. It lingers behind every question we ask about beginnings and endings. And though it may seem like a simple concept, the absence of everything, philosophers have shown time and again that nothing is anything but simple. Our journey begins, as it so often does, in ancient Greece. One of the first to face this question was the thinker Parmenides. He made a profound and stubborn claim: nothing cannot be. In other words, non-being, true nothingness, is an impossible thought. For Parmenides, only being exists, a single, eternal, unchanging, and perfect whole. Change, motion, and emptiness were just illusions of our senses. But in contrast to this great stillness, there was Heraclitus. He saw reality not as a rock, but as a river. "You cannot step into the same river twice," he famously said, "for everything is in a constant state of flux, a dance of opposites, a cosmic fire." For him, what is could not be understood without what is not. A few centuries later, the atomists, like Democritus, dared to imagine a universe made of tiny, indivisible particles moving through empty space. For their theory to work, they needed nothing, quite literally, a void in which matter could travel, combine, and create the world. Plato's student Aristotle, however, argued that nature abhors a vacuum. He believed that every region of the cosmos must be filled with something. And for more than 1,000 years, his vision of a full and vibrant cosmos held sway. Then came the scientific revolution. Thinkers like Newton began to see space not as filled substance, but as a vast, empty geometric stage. Slowly, the idea of the vacuum became not just possible, but necessary for our understanding of physics. But it was not until the 20th century that the question returned with its full, haunting power through the philosopher Martin Heidegger. He asked what may be the most fundamental question of all: why is there something rather than nothing? Let that question hang in the quiet air for a moment. Feel its weight. Why is there anything at all? A universe, a star, a single thought, a single breath, instead of the pure, perfect, and eternal stillness of non-being. Heidegger believed that we are usually so lost in the business of living that we forget the astonishing mystery of being itself. And just behind that mystery, he said, lies the void. Not a physical vacuum, but the existential possibility that none of this had to be. And yet, here we are. He urged us not to solve the riddle, but to stand before the void, and in its presence, to feel the profound fragility and wonder of our own existence. And perhaps that is the most profound insight philosophy offers us about nothing, that it is not just a technical term or a background state. It is a question, a haunting presence, a kind of silence that echoes behind every thought, every breath, every star. When science asks how the Big Bang happened, philosophy whispers, why did anything happen at all? And while we may never find a final answer, perhaps that is not the point. Perhaps our task is not to solve the riddle of nothing, but to dwell in it. And in that quiet, empty space, to feel the wonder that anything at all exists. Let us sit back for a moment now and simply wonder. We have drifted through so many ideas, bounces, brains, and beginnings that may never have begun. But perhaps it is time we ask something a little more fundamental. Does the idea of nothing even make sense? It may sound like a strange question. After all, nothing is supposed to be the very absence of sense, of structure, of being. And yet, we keep trying to describe it, to hold it in our words and theories. But maybe, just maybe, nothing is not a feature of the universe. Maybe it is a feature of us. Let us approach this idea gently, beginning with our own human language. Language helps us draw lines in the world, to label things and give them meaning. Take the word darkness. It sounds like a thing in itself, but what is it really? It is only the absence of light. Or think of cold. It is not a substance, it is the absence of heat. The word nothing works in the same way. It is a relational concept, a way of talking about the absence of something we expect to find. And here's where it gets even stranger. At its most fundamental level, physics does not seem to have a place for absolute nothing. Quantum field theory tells us that even the lowest energy state, the vacuum, is not truly empty. It is fizzing with potential, humming with fluctuating fields. Space-time itself is not nothing. It has shape, it can stretch and ripple. It is a thing, a something. So where in all of nature can we find this perfect nothing? Perhaps nowhere. Perhaps the universe, by its very nature, abhors it. Some scientists even suggest that true nothing, the total absence of space, time, laws, and structure, may be logically impossible, because being in some form seems to be built into the very logic of reality. In many theories, nothing is not the default state. The default state is something: a minimum energy field, a fluctuating vacuum, a quantum foam. It may be that we only conjure the idea of absolute nothingness because of how our minds work. We evolved in a world of some things. Our brains are wired to see patterns and opposites. So it is only natural that we imagine nothing as the alternative to something. But just because we can imagine it does not mean the universe can. Some philosophers argue that nothing is a semantic illusion, a ghost in our grammar. When we say nothing happened, we are treating nothing as a noun. But we really just mean that no particular thing from a list of expected things occurred. When we ask, why is there something rather than nothing? We are assuming that nothing was a valid option on the cosmic menu. But what if it wasn't? What if something is the only possible way for reality to be, and nothing is just a beautiful mirage created by our own thoughts? We are left with a deep, quiet mystery, one that invites not an answer, but a kind of surrender, a willingness to admit that nothing might be a beautiful illusion, a shadow cast by the brilliant light of being. It is not that the universe came from nothing, it is that there may have never been a nothing to come from. And maybe that is why we keep circling this question, not because we expect to solve it, but because it points to the very edge of our understanding. It is a question meant not for solving, but for stretching our sense of wonder, like a deep, slow breath held in the quiet just before sleep. So as you lie there, eyes heavy, consider this. Perhaps the universe did not begin out of nothing. Perhaps it began as it has always been, as something. And perhaps nothing is just the quiet place our thoughts go when they try to find the end of the thread. Let us ease now into a possibility that may feel paradoxically both immense and deeply peaceful. The idea that something, perhaps subtle, perhaps strange, has simply always existed, not created, not born from nothing, not sparked by a collision, but simply there, an eternal, unbroken presence. In this vision, there is no bang, no bounce, no great event, just a steady, quiet hum that has always been huming, long before anything like us was here to notice it. So much of our search for origins comes from a deeply human instinct. In our world, everything has a beginning. Fires are lit, seeds sprout, lives begin. So we naturally assume the universe itself must have had a starting point. But what if that's just the story we tell ourselves, born from our fleeting perspective? What if existence itself does not require a moment of creation? One gentle possibility is that the laws of physics themselves are eternal, that even if our particular universe of stars and galaxies had a beginning, the underlying principles that allowed it to begin, the rules of quantum mechanics, the logic of mathematics, have simply always been. They are not things that were created, but are the timeless grammar of reality itself. Or perhaps something more tangible has always been here, a quantum sea of potential, an endless, shimmering foam, always bubbling with possibility. In this view, our universe is just one wave that rose from the surface of that eternal ocean. It was not born from nothing. It was born from something that is always coming into being. Or consider the multiverse we dreamt of earlier. If space itself is eternally inflating, constantly generating new universes, then there is no starting line, just a never-ending process of creation, like a great tree that is always growing new branches without ever having come from a single seed. Our universe came not from nothing, but from something that is always coming into being. And this leads us to a profound philosophical turning point. We have spent so much time asking, why is there something rather than nothing, as if nothing were the natural, peaceful, default state, and something is the strange intruder that needs explaining. But what if our assumption has been backward all along? What if existence is the default, and nothingness is the peculiar, difficult idea? After all, we have never, in all our searching, observed true nothingness. Nature, as far as we can tell, does not know how to be off. Perhaps something is the rule, not the exception. This turns the old question on its head. Instead of asking how the universe came from nothing, we might quietly ask why we ever expected nothing in the first place. And maybe this eternal something is not just plausible, but inevitable. These ideas all share one deeply calming theme: continuity, a reality that never had a start, and so never needed one. In many ways, this idea is profoundly calming. It relieves us of the vertigo of finding a first cause. If something has always existed, then the universe is not a riddle that must be solved, but a mystery that unfolds, layer by layer, moment by moment, from an eternal, quiet presence. You might think of it as a melody with no first note, a song that was always playing, waiting for listeners to emerge. Or a flame that has never gone out, lit not by a hand, but by the very nature of light itself. So as you drift off tonight, perhaps let go of the question of beginnings. Let your thoughts settle not in the tension of how did it all start, but in the gentle peace of, what if it didn't? What if there was always something? Something that does not need a cause, something that does not ask for permission to exist, something that flows beneath all our tidy stories of start and stop, quiet, patient, and eternal. If that is true, then our universe may not be a miracle pulled from a void. It may be, instead, a single verse in a poem that has always been reciting itself, waiting in some far corner of space and time to whisper itself into your dreams. Let us take one last curious detour now into a world less of stars and space and more of screens and code. Tonight, we drift softly into the glowing, pixelated dream of simulation theory. The idea that our universe, with all its galaxies, particles, and ponderings, might actually be a kind of cosmic computation. It is a strange thought, made all the more plausible by our increasingly digital lives. We simulate worlds every day, so it is not such a great leap to wonder, what if someone, somewhere, did the same with us? This is not just a quirky idea from science fiction. It has been considered seriously, if playfully, by thinkers who wonder if our reality might be the output of some vast, unfathomable computational system. If that were the case, what would that mean for our great question about nothing? Imagine that our universe is running on a kind of cosmic computer. In this model, what we perceive as space, time, and matter are not fundamental. They are data structures running on a deeper substrate of logic and rules. The laws of physics are just the underlying code. Quantum particles are probabilistic pixels. Space-time is the grid on which it all runs. In this view, the universe is computed into existence, like a video game that feels real only as long as the console is turned on. If everything is part of a simulation, then what is nothing? In the world of computing, nothing could be a blank hard drive or a screen with no signal. But even these are not truly nothing. A blank drive still has structure, memory cells, and circuits. It is not doing anything, but it could. It is silence with the potential for song. So if the universe is a simulation, the ultimate nothing might be no computation at all. But even then, we find ourselves presupposing a deeper reality in which that computer could exist, or not exist. We are still left with something. What if the simulation has always been running? An eternal process, perhaps, forever spawning new realities like an infinite game engine that procedurally generates worlds, each with its own inhabitants, each asking their own questions about where it all came from. In this version, the beginning of our universe was simply the boot-up sequence for this particular instance. The server flickered to life, the data loaded, and reality began. But the system itself, the deeper architecture, may be timeless, always running, always humming just beyond the reach of our senses. This leads to a peculiar thought. Perhaps we are not the base reality. Perhaps the beings who coded our universe are themselves simulations, living inside a deeper simulation, and so on, a great digital nesting doll of existences. In this scenario, nothing becomes less of a cosmic question and more of a technical setting, an absence of input, a world that has not been rendered yet because no one is looking at it. This sounds uncannily like some interpretations of quantum mechanics, where particles do not have definite properties until they are observed. Could quantum uncertainty be a computational shortcut, a clever bit of code that saves on processing power? It is a charming and untestable idea for now. If we are in a simulation, every tool we have is part of that simulation. But it reminds us that our idea of nothing is always shaped by the context we imagine. If we are code, then nothing is the absence of process. But even that presupposes something deeper, a meta-reality, a silent server rack in a higher plane of existence. And so we find that whether we imagine the universe as a quantum field, a colliding brain, or a running server, there seems always to be a something, a ground on which the story rests, an operating system for reality. So, could our world be a simulation? Perhaps. And if so, perhaps nothing was never a real possibility, just a line of unused code waiting to be compiled into a cosmos. As you settle down tonight, you can picture the code of the cosmos not as flashing numbers, but as a gentle, unfolding lullaby sung by an ancient and unseen machine. And in that rhythm, perhaps there is no such thing as nothing, only the silence that waits to be filled with song. It is late. The room is quiet, and the world outside is soft around the edges. Your thoughts are beginning to drift, like boats on a calm, dark sea. We have followed this thread of nothingness together, through quantum fields and ancient philosophies, through universes that bounce and branch and dream. And yet, after all of it, a final, quiet question may be hovering in the air.
why does any of this matter?
In the morning, the sun will still rise. We will still make our coffee, and the small routines of our lives will greet us. And that is a beautiful thing. But our hearts and minds still return to these great, quiet questions. Why? Perhaps the answer is woven into the very fabric of what it means to be human. We are a species that looks up at the stars and wonders. Asking these questions is not about solving a puzzle. It is about finding our place. It is about stepping back so far that we can see the whole of our lives nestled within something immense and ancient. It pulls us out of the small loops of worry and routine and reminds us that we are temporary passengers on a very old, very beautiful journey. When you remember that time itself may be eternal, a traffic jam might feel a little less heavy. A quiet moment of stillness might feel a little more sacred. The rhythm of your own breath becomes a tiny echo of a cosmic pulse. Because you did not have to exist. And yet, here you are. Not just as a collection of particles, but as a conscious being, capable of holding in your mind the possible past of everything. That is an extraordinary and beautiful thing. There is also a deep comfort in zooming out this far, in recognizing that the universe has been here for billions of years and may continue for billions more. The problems we carry, while real and important to us, are small ripples in a much, much vaster sea. The deadlines, the worries, the gentle anxieties, all of it is held by the immense, quiet backdrop of a universe that does not judge and does not rush. The universe asks nothing of us, and yet we ask everything of it. And in those questions, we come into contact with our own fragility and our own capacity for wonder. You do not need a degree in physics to feel awe. You just need a quiet moment and a willingness to sit with a little uncertainty. And perhaps the most important gift these questions give us is the peace of not knowing. There is a quiet courage in letting the mystery be. There is a deep comfort in admitting that we may never have all the answers. In that humility, there is a surprising kind of freedom, a freedom from needing to solve everything. When you let go of needing a final, perfect answer, you can simply fall in love with the question itself. You can wonder and dream, not to arrive at a destination, but to expand your own sense of what is possible. So why does it matter? It matters because it reminds us that we are part of a story so much bigger than ourselves. A story that may have no beginning and no end. It matters because it shifts our gaze from the mirror to the sky. It matters because asking what is nothing helps us appreciate the gift of everything. And it matters because at some deep level, it reminds us that we are not separate from the cosmos. We are the cosmos thinking about itself. And that, quietly and gently, is enough. And so, here we are, at the quiet end of our long journey together. We have drifted through fields of quantum foam, tiptoed across the rounded edge of time, and wandered through the beautiful dreams of philosophy. We have asked whether nothing ever truly existed, and now we arrive at a place not of final answers, but of peaceful rest. Because after everything, after bouncing universes and vibrating strings, we are left with something unexpectedly soft, the possibility that not knowing might be the most honest and the most beautiful place to be. At the beginning of this journey, we asked a simple question. Did nothing ever exist? Now, after our slow and thoughtful exploration, the answer may still feel just out of reach, not because we missed it, but because the question was never about finding a finish line. It was an invitation to widen our perspective, to look at the universe and ourselves with a little more wonder. Maybe nothingness never existed. Maybe reality has no edge, no first moment. Maybe the laws of existence have simply always been at work, humming quietly through an infinite stillness. Or maybe, just maybe, a true, deep, unimaginable absence did come before everything. And from that nothing, something arose, a flicker, a ripple, a breath. We may never know which story is true, and strangely, that may be the point. There is a quiet courage in being able to sit with mystery, to let questions remain open. The universe does not rush to explain itself. It simply is, and it allows us, these little thoughtful beings, to look up and wonder. And asking is beautiful in itself. Even if we never find out for sure, the act of wondering shapes us. It keeps our minds open and our hearts soft. It connects us to the whole human story, to that quiet part of us that simply wants to understand. The mystery of nothingness is not a flaw in the universe. It is a feature, a space left open, like a pause in a piece of music, a place for us to rest, to breathe, to marvel. The fact that we do not know does not make us small. It makes us part of something far greater than we could ever fully grasp. So, wherever this universe came from, whether it tunneled from a quantum vacuum or rebounded from a previous cosmos, here we are, alive, aware, and able to ask. And that is enough. To be a preacher capable of wondering what existed before anything else, that alone is a quiet miracle. A star becoming conscious of stars, a ripple in space-time asking what made the water stir. So, as you drift fully into sleep now, let these questions linger, not like burdens, but like soft, distant lanterns. Let them glow, not with urgency, but with peace, because the beauty of the universe is not just in what we know, but also in what we don't, in the vast, silent spaces that lie between every explanation. Perhaps the line between nothing and something is not a line at all, but a dance. And either way, it is okay not to know. In fact, it is more than okay. It is what makes being alive in this strange, vast, and beautiful universe so quietly magnificent. Not knowing is not a weakness. It is an opening, a beginning, a soft-lit doorway to awe. And so we rest here at the end of our journey through nothing and find that we are surrounded by everything. And that, in the end, is what makes it all so incredibly beautiful.
Hello there, and welcome to the Midnight Scientists.